It's my pleasure to introduce Dr. Walter Koroshetz, who will start the formal introduction to the meeting. Dr. Koroshetz is the director of the National Institutes of Neurological Disorders and Stroke. Dr. Koroshetz.
Thank you very much, and I want to welcome everybody here from NIH in general. NIH is the nation's leading biomedical research institution. It funds research across the country in pretty much all different types of health disorders, and our goal is to try and understand the fundamental knowledge about the body and to use that knowledge to develop treatments for people with disorders and reduce the burden of disease. And so, as people in this room may know, NIH made a strong commitment, led by Dr. Collins, who will talk to you tomorrow, to basically throw all the weight that NIH has scientifically at this very vexing problem of trying to understand how ME/CFS occurs and how we can best treat it. And so we're really excited to have people here today to talk about the work that they're doing. The people here at NIH are listening closely to try to use that information to help us plan for a brighter future. And I'd also say it's my pleasure to work for Vicky and Joe, who really are the leaders in this area for NIH, and we've been really blessed with really good support staff to go out to the community and get this research going. So just to say a couple of things about our institute. As you can see here, as I mentioned, the NIH mission, our mission is parallel to that, but it focuses on the brain, the peripheral nervous system, muscle, and we're trying to understand fundamental knowledge about how these things work and then use that knowledge to develop better treatments. And what we find, we've had some successes for sure in terms of treating neurological diseases, but we've also had lots of failures, and the failures are usually due to the fact that we made assumptions going into the clinical trials that we just didn't really have the fundamental knowledge, and there were these gaps, and we jumped across an assumption that turned out to be a fatal flaw. And so trying to understand the basics of what is going on in a disease is absolutely critical. Until you really understand it totally, anytime you go into a clinical trial, you're running into a risk of a failed clinical trial. So we have to always try and take advantage of what we know and see if it can move into a clinical trial to help, but at the same time try and build this fundamental knowledge so that the success rate of the clinical trial goes up and up and up over time. We also are very cognizant of the fact that science occurs in a stepwise fashion, and that the work that's being done now oftentimes we'll see tremendous fruition 10, maybe 20 years from now. And what that means is that critical to the general effort is to train the workforce that's going to work in this incremental fashion on ME/CFS, hopefully with more promising treatment options as time goes on. But without that workforce, things will stall. And so we're really excited yesterday to have a tremendous group of early stage and mid-stage investigators in ME/CFS, and we're working hard across the NIH to kind of help them flourish, but also we need to bring many more people into this field. We don't have the workforce that we need to take on such a major health problem at this point in time, but we're hopeful that we can move into that space with an expanding, really dedicated, talented workforce. So in our institute and in many institutes across NIH, we fund research that goes from basic discovery all the way to clinical trials. In general, we don't do clinical trials on brand new medicines that are developed by the pharmaceutical companies, but we do a lot of research that de-risks that process and makes it more attractive for the pharmaceutical industries to test therapies, because we provide the science that gives them a sense of what their chances of, their probability is that those clinical trials will be successful. And we actually also in our institute will run first-in-human trials of drugs that are owned by pharmaceutical companies because they're not going to be able to get the resources without a package that shows that it's hitting its target in humans. So we go at least as far as that, as well as we have grant mechanisms where we can bring molecules or small molecules, biologics or devices to the point where they can be ready to go to the FDA to get clearance to go into clinical trials. So we've tried to fund across this whole spectrum of research, and toward the end we have a lot of interactions with the industry partners who are the ones who are going to bring therapies to patients. Now, so I'm a neurologist. I'm from NINDS. I have a very brain-centric view of things. I think the brain is really, really important. I think the immune system is good because it helps take care of the brain, but the heart is good because the brain can suck blood out of the heart. So just a caveat there, a very brain-centric person. But clearly we know from ME/CFS, talking to patients, that there are a lot of neurological complaints, deficits, so cognitive difficulties, called brain fog, fatigue. Fatigue is a mental state, and so it has a brain circuit that underlies that state. Many people talk about hypersensitivity to sound or touch, and that is a brain circuit that starts in the periphery where you have sensory receptors, goes into dorsal root ganglion cells, into the spinal cord, up to the brain, and at all those sites you can mediate, you can turn the gain up and down on the sensation, and then how it's perceived in the brain is sometimes very difficult to get at, but we clearly know that there's a detector system and then there's a perception system, and they are connected, but they are also working separately. So how you react and the emotional component that goes with a sensation, these are all things that we're studying very intensely, not just at NINDS, but in many of the neuroscience institutes. And when you think about fatigue or exertional intolerance, from a neurologist's point of view, we would say that the brain is doing a calculation all the time. Every time you act, there's a calculation that goes on in the brain about what's the effort that's required to do and what's the reward for doing it. That's a very simplistic view of how the brain works, but it holds true in many different instances. And so, and we know from just our own experiences that that set point about when the brain makes those decisions goes up and down. When you are really refreshed and energetic, then there's a particular gain that you are working at, and you can take on things that when you're been up for 14 hours, you're not going to be able to do anymore. When you exercise, you are running at top speed when you get off and going. But after a couple of miles, the idea of sprinting is like, no, that's not going to happen. And that's a calculation that's going on in the brain based on the sensations that are coming into your brain. And so trying to understand even the basic knowledge of how the brain makes those decisions could be very important to us. So what NIH has been doing over the last couple of years is really trying to galvanize across the institutes to bring in the best science and attack ME/CFS. And this is done with what we call the Trans-NIH ME/CFS Working Group. And this group meets regularly. It has representatives from almost all the institutes and centers at NIH. And together, the group decided that the best thing we could do to get things, trying to get, kind of launch a much more significant effort in ME/CFS was to actually develop a collaborative research center and data management coordinating center group. And the idea here is that this is not the everything about where ME/CFS research is done. This is just kind of establishing a beachhead where we can get a coordinated effort going, and the hope is that this will branch out and research will start to come from many, many different areas. But in looking at what happened in the past, we think that trying to coordinate the research and the data findings is incredibly important. If we're left with multiple different reports from multiple different groups that are doing things differently, the progress is going to be really slow. So we really need to always go from that next step, which we call discovery, to the point of validation. And to validate things, you really need a group to do it together. And that's what we think this group has the opportunity to do for the first time. So we're really looking forward to what it does. But we're hoping also it'll put a much brighter light on ME/CFS research, and it will develop research at many, many more institutions across the country. So the centers, which you'll be hearing about from today, are 3 currently, and they are coordinated by a data management coordinating center at RTI. The principal investigator there is Linda Brown, who came from the National Cancer Institute, so she knows a great deal about how NIH works. And so there's the Cornell Research Center, which is up at Ithaca in New York City, and also collaborating with Mark Van Ness at the University of Pacific, Stockton, California, for its clinical pieces. Ian Lipkin's group is at Columbia, and they've been working with the clinical groups and the samples that were developed by Sue Levine in New York City, Dan Peterson in Nevada, and Jose Montoya at Stanford. And then Daria Unitmatz at Jackson Lab in Connecticut, working with Cindy Bateman at the Bateman Horn in Salt Lake City. So we have, these are really serious ME/CSF investigators, and they have their hooks into different clinical sites for samples and patients, and so we really have really high hopes that this group can do really quality work at their institutions, but more so to actually come together and do things together. So in this program, we reserve funds for a joint project that they have to agree upon and do jointly. And that, I think, was our, kind of heavy-handed approach to say no more, little experiments here and there, but really try to go to that next step and we're happy to fund that next step to a validation of the initial findings. For folks who are interested how this is going, RTI has a website that will continue to be updated and let the community know about how the work is going. I would also say, importantly, that NIH developed what's called a council working group for ME/CFS research, and so there's a group that's formed and has been doing really a lot of soul searching, a lot of heavy investigator work to come up with recommendations on how best we move forward to the next step in ME/CSF research at NIH. This is currently attached to the NINDS Council, but that's just a formality. Their reports will be circulated to all the trans-NIH working groups and all the councils that take part in ME/CFS research. And so the extension for information on, we have a request out publicly soliciting input on how best to advance ME/CFS research. And as you can see the website here, the deadline to get this in so they can get into the report for the working group is May 1st, 2019. So please, if you have thoughts, particularly after this meeting, on what we should be doing, please put your ideas into this request for information on the web. And with that, I'd just like to say we're incredibly anxious and looking forward to the discussions that are going on over the next couple of days, and hoping that we can, see through the fog and see some real opportunities that we can finally get to solutions for patients. So on behalf of the other NINDS directors, I want to thank everybody for coming, and for the people who are doing the work and the patients who are participating. It's really a tremendous effort, and we really appreciate it. Thank you very much.
Thank you, Dr. Koroshetz. It's my pleasure to introduce the next speaker, who also provides some introductory comments. So this is a trans-NIH effort, is reflected by Dr. Koroshetz and NINDS and myself and others at NIAID, in Allergy Infectious Diseases. And in that spirit, I'd like to introduce Dr. Hugh Auchincloss, who's the Principal Deputy Director of NIAID.
Good morning. My name is Hugh Auchincloss. I'm the Principal Deputy Director of the National Institute of Allergy and Infectious Diseases, and I'm here to welcome you and to thank you for coming to this important meeting. When I walked down the hall to come into the auditorium, I saw signs to the NIAID conference on ME/CFS. That's a technicality that the signs were printed that way. This was a totally trans NIH, indeed trans community effort to put together this important meeting. There have been input from all the institutes at NIH and from the scientific community at large and from the patient community. So this is not strictly an NIAID undertaking. I also want to echo Walter's comments about the event yesterday, which I think is almost as important as this event, which was the workshop for young investigators who want to enter the field of ME/CFS because they are the future, and that's the young talent that we need to proceed ahead. Now, the mission of the NIAID is to perform basic and applied research in the areas of immunology and infectious diseases. It's very hard for me to imagine that as we learn more about ME/CFS, that we're not going to find that one or both of these fields is intimately involved. Therefore, our institute was enthusiastic when Dr. Collins committed the NIH to a renewed effort on this syndrome, and we immediately became active in participation in the Trans NIH ME/CFS working group that Walter has told you about. We've supported some of the applications that have come in from investigators, and we're co-funding the CRCs, the collaborative research centers that he just told you about. And we have our own intramural investigators who are participating in NDS-led ME/CFS clinical research. In addition to our efforts as part of the Trans NIH group, NIAID is committed itself to further studies of ME/CFS. We have our immunologists, we have our infectious disease scientists who are participating. We're doing single-cell analysis. We're looking for infectious etiologies. We're looking for biomarkers of the syndrome. And we're bringing the most modern tools of genomics, transcriptomics, and others to the study of this important syndrome. I show you in this final slide just several of the papers that have come out recently related to this syndrome from some of our best and most established scientists, including Mark Davis's group, Ian Lipkin's group, and you'll be hearing from these scientists during the course of these 2 days. So we're deeply committed to this research. We're enthusiastic about this 2-day symposium. Thank you, all of you, for attending. Thank you, particularly from my institute, to Joe Breen for your effort in organizing this. Thanks a lot.
Thank you, Dr. Auchincloss. So I mentioned there was a large group of people who helped organize this, and there was a slide earlier of an organizing committee that contained a really diverse group of people to help develop this program. And when we met as a group, we decided we really should start off with an introduction to ME/CFS just to make sure everybody was on the same page. And there really weren't too many people that could do the kind of job that you're going to see in a minute, from Dr. Cindy Bateman, who runs the Bateman Horn Center out in Salt Lake City and has been seeing patients and doing research. She can tell you for how long, but we're very pleased that she's here to tell us about her view of ME/CFS 101. Dr. Bateman?
Good morning. It's a pleasure to be here. It's an honor to be here and to represent the many, many patients suffering with ME/CFS and also the clinicians who take care of them. Just by way of disclosure, we are doing 2 clinical trials at our center right now, pharmaceutical trials that will not be discussed in this presentation. I may discuss off-label use of medications and would describe it as such. And the Bateman Horne Center is a 501c3 nonprofit, and I am employed by the nonprofit. I think for MECFS 101, one of the important aspects is how in the world do people get involved in this illness? And so I thought it might be worth looking at my journey a little bit as an example of how people come to embrace and become very enthusiastic about studying this illness. I went to medical school at the Johns Hopkins School of Medicine and my residency back in Utah. When I came back to Utah to do my residency, my older sister, who'd been very healthy and dynamic when I left, was sick with an illness that no one had been able to figure out. So at the very beginning of my residency training, I was exposed to this illness and was really the only doctor who stood by her side as a family member and a friend to help her through her journey of MECFS. I practiced 10 years in private practice as a general internist, and during that time saw many, many, many patients with chronic fatigue, widespread pain, and other unexplained illnesses. And after 10 years, I kind of decided that really it was time to decide if I wanted to make a significant contribution. I felt like I didn't know very much after doing all that, and I still feel that way. It's a daunting task to try to understand an illness when the science is so sparse and to know how to take good care of patients. So I closed my practice. I had 3,000 patients and opened my door as a fatigue consultation clinic, not because I knew everything about chronic fatigue, but as an opportunity to learn and to focus my attention on this group of patients only. And it has been an amazing experience. We started doing some clinical research. We did the Ampligen trials. And 4 or 5 years ago, I decided that we needed to have a more sustainable model to be able to move forward, because it's very difficult to stay in private practice with such a time-consuming illness as our major subject. So the Bateman Horne Center is the answer to that, a model that, hoping we can model a clinic, a center of excellence, where we can have clinic, do research, and to develop good provider education to be able to move this illness forward. So MECFS, a chronic, disabling, multi-system illness of unknown cause without established biomarkers. I decided the best way to teach you about MECFS was to introduce you to a couple of patients. So we'll talk with the first case. This is a young woman who's an identical twin discordant for MECFS. She became sick when she was 17. She was active and healthy, an above-average student. She was on the cross-country team. And her junior year, after the fall competitions, she took some time off because she had a stress fracture. And this is another example of MECFS 101. Sometimes the history is lost. We really don't know what happens when people become ill because studies aren't done, time goes by. But when she tried to go back to running in January, she couldn't run a mile without becoming exhausted and having stiff, heavy legs and electric pains going down her legs. And for almost 9 months, she had nausea, unexplained nausea and vomiting. Her senior year, for a long time, she tried to stay with the track team, but she could never run more than a mile after being a cross-country runner. And while some of her symptoms were present intermittently in the beginning, pretty soon she couldn't tolerate any exercise. And after trying to exercise at all, the heaviness and exhaustion worsened and affected all of her routine activities, even walking around. She forged forward. There was no answer for it. She went to college. She was able to complete her schoolwork. She got lots of assessments. Her healthy twin was by her side, succeeding and doing much better. And she was able to graduate and become a preschool teacher. She was never able to work full-time, so she worked part-time, still ill. But at age 24, she developed a respiratory infection with a severe cough that took her to the emergency department. And the treatments they gave her there made everything worse. She developed severe insomnia after taking oral steroids. And then her periods became abnormal. And the next year was a horrible year for her. She was in the emergency room 6, 7 times throughout the year, exhausted, ill, multiple unexplained symptoms. She had horrible experiences with numerous medication trials, mainly to treat insomnia, anxiety, and pain. And she was diagnosed with schizoaffective disorder. She was diagnosed with borderline hypothyroidism and put on supplement. And by this time, she was unable to maintain any work due to her fatigue, exhaustion, upright activity intolerance, post-exertional malaise, severely dysregulated sleep, occasional sharp pains in her legs and her upper arms, shoulders to her elbows. And on her worst days, she was unable to read and comprehend. This was about the time she came to my clinic. And in her intake, we did some bedside orthostatic measurements. And you can see, oh, I get it. So supine measurements, her blood pressure was 130/80 and her heart rate 80, very normal. By the time, and when she stood up at 3 minutes, her blood pressure had dropped significantly and her heart rate had jumped. This was really before postural orthostatic tachycardia syndrome was a common term. And she went for tilt table testing, and as you can see, her blood pressure dropped precipitously, and she became symptomatic during the trial, demonstrating neurally mediated hypotension. And during the tilt test, her heart rate went from 67 to 131. She had cardiopulmonary exercise testing with a very low VO2 max of 16 and an anaerobic threshold that was 20% of predicted. And at that time, and you're going to get used to this term that I use, we really try to measure activity by hours of upright activity, and that's the amount of time spent with feet on the floor, including sitting, was about 2 hours in 24 hours on average. Currently, she remains very ill. Her twin has gone on to get married, which was very difficult, as you can imagine, for twins. Move away and have a baby. And leaving the ill twin at home, she spent some time in her own apartment, but pretty soon had to go back and live with her parents. Severely disordered sleep, pain in the arms and legs, headaches, achiness. Over the years, she's ranged from 4 to 6 hours of upright activity tolerance in 24, but more recently closer to 1 to 2 hours. Up 15 minutes at a time all day long to average those numbers. She had antibodies supporting celiac disease, but got no better on a strict gluten-free diet. She has thyroid autoantibodies and is adequately supplemented for hypothyroidism. As part of the CDC multi-site study, she came in very recently for a 10-minute orthostatic test, a lean test, the NASA lean test. And you can see her measurements here. This is kind of a busy slide. But lying down, a blood pressure 130/86, heart rate 52. I would note that she's on several medications. She's drinking 2 liters a day, wearing compression socks, taking a small dose of propranolol, which is why her heart rate, I think, is low, and on midodrine. And yet she didn't last more than 5 minutes. Once she stood up, her blood pressure dropped to 90/84. Heart rate went up to 109, meeting criteria for systolic orthostatic hypotension and for POTS. And typically POTS is not associated with a large drop in pressure as well. I'm going to save a next piece on her, for our clinician panel tomorrow, so I could tell you a little bit more about some of her treatments. Okay, the second case, and I tried to pick some common presentations that represent some big groups. This is a woman who became sick at age 47 with ME/CFS. Looking back on her history, as a teenager, she had pneumonia that caused her to miss about a quarter of the school year. So again, it's hard to know exactly what happened. When she was 18, after having multiple episodes of pharyngitis, she had a tonsillectomy. But she was well enough to work part-time during high school. She worked 25 to 30 hours a week in college. She married just before graduation with a degree in finance. In her 20s, she had 2 sons and suffered some postpartum depression after the deliveries, but basically recovered. She had a hysterectomy, but kept her ovaries, so she had continued to have hormone support. She went back to work. She was a little bit overweight and was diagnosed with obstructive sleep apnea and was very compliant with her CPAP. She had iron infusions for iron deficiency anemia when she was 42. And then again, when we're trying to understand what happens to patients, we don't always know what these pieces of historical information might mean, but they did discover a source of carbon dioxide in their home that had been present for at least a year. But the problems really started when she was 47, when she developed severe bronchitis that went on, and she just never recovered from the fatigue of the bronchitis. And within a short time, within the next month or 2, she developed quite significant cognitive impairment and worsening fatigue. And by that fall, she had developed a severe, persistent headache, a migrainous headache that was present for more than 6 weeks without relief. They were finally able to bring it under control with topiramate, a drug that causes cognitive impairment. She started to feel better, and in January, on a good day, she got in her car, went shopping, and did some errands, but that amount of activity created a severe post-exertional malaise and relapse, and she developed total widespread body pain. Her headache came back, and she was bedridden for 3 days. A few months later, she was seen and evaluated in my clinic. She came in a wheelchair. She had profound exhaustion, difficulty getting around the house, mostly homebound, barely able to do anything without escalation of symptoms. She had widespread pain, severe cognitive impairment, nausea, poor appetite, blurred vision, noise sensitivity, constipation, reflux, many, many symptoms that were creating her misery. She had an average of 2 hours in 24 with feet on the floor, and she was only able to shower once a week with assistance. And she was managed primarily by a psychiatrist who kept adding medications to try to improve her depression, which was easily remedied once we knew more what was going on. So these are some of the standardized questionnaires we do in the clinic. The HADS is the Hospital Anxiety and Depression Scale, and she really barely met criteria for mild depression. Her Epworth Sleepiness Scale was normal. She had a very high Fibromyalgia Impact Questionnaire score of 69. When you look at the SF-36 scores, I've highlighted these, sorry to be annoying, but because there's a lot on these slides to sort of point out, but the yellow are the physical functioning scores, and low is the severely abnormal score. And you can see that her physical functioning, role limitations due to physical health and vitality are the very low scores, and with relatively preserved mental health scores. We, by routine, do orthostatic testing. So we laid her down on the bed, her supine blood pressure right there, 120 approximately over the 60s, and a heart rate of 64. And we've started looking at pulse pressure as a kind of a quick indication. And the pulse pressure is the difference between the systolic and the diastolic pressure. As soon as she stood up, you can see that her blood pressure drops precipitously, and her heart rate actually had an abnormally slow response to, I think, that drop in her blood pressure. And at 7 minutes, she became cognitively impaired and really looked like she was going to faint. So her blood pressure dropped to 91 over 79. Now these are hand measurements, so it becomes very difficult to understand, to really feel it. But if those were true, then her pulse pressure had dropped tremendously to near 10. About this time, was just about ready to pass out. We were able to recreate her cognitive impairment many times by doing upright testing. Her physical exam was relatively normal. She had fibromyalgia tender points, and she was a little wobbly on her Romberg and tandem gait, but not necessarily ataxic. She had her sleep apnea was well treated. The only thing we found in her labs was an elevated pyridoxine level, again, of uncertain significance. She was heterozygous for MTHFR mutation at 2 loci. She had a stress echo that was normal and normal carotid Dopplers. We tried to include her in the NIH study, and she was willing to do it, but she was just decided she would be completely unable to travel, to come here, to stay in a hotel, and her husband, and this exercise testing she was willing to do, but it was terrifying to her that she would do cardiopulmonary exercise testing. And because her husband couldn't take time off work to accompany her, she ended up not being part of that study. We've tried everything to help this woman. And she's basically had paradoxical responses to almost every medication we've tried. We gave her very low doses of midodrine, which is a peripheral vasoconstrictor in the limbs and an alpha agonist, and it was as though I'd given her a dose 100 times. I mean, I've dosed this medicine many, many times. She developed urinary retention and became so cold that she had to get in the shower. She couldn't stand 30 minutes when she wasn't taking midodrine. And when she took the midodrine, she had to stand in a hot shower for 30 minutes to get the shivering to stop. We tried her on fluticasone, pyridostigmine, valacyclovir, Adderall, Enlite, and low-dose naltrexone, and nothing seemed to alleviate her symptoms. We also tried her on desmopressin, and it didn't even change her vital signs, particularly to put her on a significant dose of desmopressin. So this is a woman who has been in this state despite good medical care for the last 3 years. She's homebound, mostly bedbound, severely ill with ME/CFS. She has good family support and access to medical care. She's motivated, and depression is not playing a primary role, although, as you can imagine, she has times when she becomes very discouraged. And because she's very immobilized, she's developed new problems, like sciatica and trying to lift and move herself. She's getting shoulder problems. So she's hanging in there, but I think this is an example of someone who's severely ill and could be very severely ill, but I think fortunately she's been able to have a lot of good support, and at this point her illness is early. So I don't want to spend too much time on historical background except to say that the term myalgic encephalomyelitis dates back to the 1950s. And we've used terms post-viral or post-infectious fatigue syndrome through the years. The term chronic fatigue syndrome dates from 1988. I'll talk about that a little bit more in a minute. And many patients remember the term chronic fatigue immune dysfunction syndrome or CFIDS, that was used by the patients to avoid the term chronic fatigue syndrome. ME/CFS is not a new illness. It's worldwide and multicultural, but comparable illnesses, although they have been documented for centuries, it's very difficult to make historical comparisons just because of the rate of change in medicine and our knowledge. Again, this is a brief slide, but the initial term chronic fatigue syndrome came from a paper in 1988 by Holmes, and really was an attempt to replace the term that was in use, chronic Epstein-Barr, chronic EBV, and it's actually worth a read. All of these papers that talk about these case definitions, I think, are very helpful to read. And they basically said, we'll call this a chronic fatigue syndrome. And this was intended as a research diagnosis, short-term, to try to understand how this kind of post-infectious syndrome might, what it might represent. Within a few years, because of the number of people involved and the extent of people who might meet these criteria, a consensus process, a collaborative group of researchers, clinicians with patient input, kind of expanded and changed these criteria for what we know to be the Fukuda criteria. And this was also a research case definition. And a research case definition is really not very useful in a clinical setting because it doesn't allow you to make the diagnosis in the presence of multiple comorbidities. The Canadian consensus criteria were published in 2003, and this was clinical experts, medical consensus panel. This is a really good document to understand the presentation of symptoms, and it does a really good job of describing the many aspects and systems that can be impaired with this illness. And this was intended to help clinicians make a clinical diagnosis. Unfortunately, and this is just my opinion, it was published in a journal that was not easy to access. So although people in the field had access to it, the general medical community really did not and never really understood the significance. There were the international consensus criteria that tried to update the research, but in 2015, the Institute of Medicine did an evidence-based review and published proposed clinical diagnostic criteria. So just quickly, the Fukuda criteria required thoroughly evaluated unexplained fatigue, 6 months in duration. And the things that are most frequently missed are that this definition did require a substantial reduction in previous levels of activity. But the problem was that only 4 out of the 8 symptoms in this list were required to make a diagnosis, which created some problems. Number one is that post-exertional malaise was not required to make a Fukuda diagnosis. And as a fibromyalgia expert, I would say that most patients with fibromyalgia meet Fukuda criteria if they have a significant amount of fatigue, and I think most of them do. Also, some people feel that patients with undiagnosed depression or atypical depression could meet the criteria for Fukuda, especially because sometimes depression is associated with achiness and certain kinds of stiffness and pain. The Canadian criteria pushed substantial reduction in activity and post-exertional malaise to the top of the list as required criteria for diagnosis. And I think that was the most important message that came forward, along with, and you can see here, sleep dysfunction, various types of pain, neurocognitive manifestations, and then at least one symptom from autonomic, neuroendocrine, and immune from 2 of the following. This is also a great read, as are the paper that came out with the international consensus criteria to really begin to understand the clinical presentation. So the Institute of Medicine published their evidence-based review and recommended a new name, systemic exertion intolerance disease, long story. The name was not adopted by federal agencies, by CIFSAC that sponsored the review. And I want to make the point that the IOM committee advised that the term chronic fatigue syndrome be abandoned in the report because of the many problems surrounding that name. And the report also said that the findings of the report were really preliminary and that another evidence-based review should be completed before 5 years. There were many really great papers that came out after the evidence-based review for the IOM criteria. So these evidence-based clinical diagnostic criteria, I think, have been oversimplified, but I think if you understand them, they're really very strong. The core criteria required for diagnosis must be moderate to severe and present more than 50% of the time. Impaired function, post-exertional malaise, disordered or unrefreshing sleep, and then at least one of the following: cognitive impairment and orthostatic intolerance. And also clearly outlined in the report are additional common but not core symptoms. So symptoms that were common across the ME/CFS population but didn't occur in everyone at all times of their illness: chronic pain, immune inflammatory manifestations, infection manifestations, neuroendocrine manifestations. And the IOM report really is very digestible. Just read the two chapters that outline these main core criteria, and it's very, very helpful. There are no exclusionary criteria detailed, but it's expected that a differential diagnosis, appropriate workup of symptoms and treatment, referral to specialists will be directed by healthcare providers. All other identifiable illnesses should be diagnosed and treated, including supportive care, observation, reduction of risk factors, and a working or provisional diagnosis of ME/CFS can be made at any time in that 6-month period, and supportive care and management should be provided from the beginning. This is straight out of the report. So this is my diagram. We have the big world of chronic fatigue and chronic pain. We have fibromyalgia that describes general hyperalgesia, the development of hyperalgesia, pain amplification. Fukuda was more broad. The IOM criteria have kind of honed in better. But because not all the symptoms are required, I think there's still a smaller, more ill group described by the Canadian criteria. And we may be looking at phases of illness or all kinds of things. But it's very important that we have a narrow group to study, because what we're narrowing this down to are the most ill, most impaired patients that need our help more than any other. I don't think we're going to have time to go through these in too much detail, but I just wanted to quickly say these major criteria, say some things about them. But the impaired function and fatigue is profound. It negatively impacts normal function, and this is one of the most useful diagnostic signs, and it's really more severe than most other chronic illnesses. Illness can range from mild impairment and difficulty maintaining a totally normal schedule, all the way to bedridden, severely able to move or speak. We use hours of upright activity commonly to quickly assess people's functionality. And most of us, spend 14 to 17 hours with our feet on the floor in a 24-hour period. People with chronic illness, particularly like fibromyalgia, for example, may be reduced to 10 to 12 hours. They spend more time sitting. They're not getting around as much. But ME/CFS patients, and of course there's exceptions when people get better or whatever, but really the range of hours of upright activity tolerance is more like 0 to 8, with 8 being the mild patients. 8 hours of upright activity, people who might be able to maintain part-time work, might be able to do their job, like one of my patients with a work day from home in the middle of the week, and all hours she's not at work, she's in bed with her feet up. And down to, I used to have 1 to 8, and then I got a bunch of emails from patients saying, 1's not low enough, you have to have 0, because there are people who can't ever get out of bed. Post-exertional malaise is a relapse of symptoms or an escalation of symptoms after physical, cognitive, emotional, orthostatic, and other stressors. It can last for days, weeks, or months, depending on a number of factors, and it's been objectively measured. Patients with ME/CFS are generally unable to replicate the test parameters if cardiopulmonary exercise testing is conducted 2 days in a row. This was first shown by Van Ness and his group in 2006 with a small study showing that patients were unable to replicate their VO2 max. And then in a really great paper, Betsy Keller showed in 2014 that many parameters, whoa, I didn't mean that. I don't know if I can go backwards, there we go. That many parameters, so the dark line is test 1 and the light bar is test 2, test 1, test 2, test 1, test 2, with multiple measures in cardiopulmonary testing were reduced in the second test. Sleep is very abnormal in this illness, and polysomnograms really don't show, there's a higher rate of primary sleep disorders, but there is an intrinsic disruption of sleep cycling and the nature of sleep, pretty much like we see on all polysomnograms, because it's really hard to sleep in a sleep lab. So this is a key part of the illness, and some patients really just let their sleep determine its own cycles. The neurocognitive manifestations are significant in many patients, mostly slowed information processing, but it makes consolidation of memory and executive function difficult, and it may be one of the main reasons people don't do well in the workplace. This is a graph from the IOM report from one of Dr. Jason's paper. If you rank the system, these cognitive symptoms of at least moderate severity and at least half the time, you can see that compared to healthy controls, they're just vastly different in the number of cognitive complaints that they have. This is just one paper. I wanted to take a moment, and I know my time is short, but this is one of Dane Cook's papers, and I wanted to use it to illustrate cognitive issues. They used an exercise stressor to do a study looking at functional MRI, and they also had a cognitive stressor. And the cognitive stressor was the paced auditory serial addition task, or the PASAT. There were 15 patients, 15 controls. They did 30 minutes of submax exercise. They had functional MRIs during the fatiguing task, and their symptoms went up. You can see from this, this is just total symptoms the day after participating in this study with the ME/CFS patients on the right. But I want to show you this. This is the total errors on cognitive testing. And the ME/CFS patients are red. So the cognitive testing was done 3 times, 1, 2, 3, before the exercise, and 3 times after the exercise. And if you look at the gray bars, the normal controls had fewer errors every time they took the cognitive testing, and the ME/CFS patients had more errors just from doing the cognitive testing before they even exercised. Orthostatic intolerance is a simple description of development of symptoms when standing upright and sitting upright in many cases that are relieved by reclining. And the orthostatic intolerance, we presume, creates symptoms due to cerebral underperfusion and peripheral cardiovascular signs. And it's worsened by many, many situations. Tilt table testing and bedside testing can pick up these orthostatic syndromes in many patients, and some patients have orthostatic intolerance without meeting a syndrome criteria of orthostatic intolerance. So we have a disease that affects more than 1 million Americans. The loss of productivity and high medical costs is staggering. By far, the majority of patients with ME/CFS have not been diagnosed. Those who are diagnosed often take up to 5 years or more to get a diagnosis. This illness complex is not taught in medical schools very much, and when it is, it's often very outdated and inappropriate information. But the worst thing is many patients with ME/CFS report being subject to neglect or hostile attitudes from their healthcare providers. And I can tell you this is still true, and there are still physicians who will say, I don't believe in that illness. So we have a chronic disabling condition, a medical mystery in the age of modern medicine. How has this illness been overlooked all this time, and why? And that's why we're here, of course, but I would just say that this is an illness spectrum that involves the least understood and least developed areas of clinical medicine. So viral illness, immune inflammatory systems, neuroendocrine system, the central and autonomic nervous system, genetic, epigenetic factors, environmental exposures, cellular metabolism defects. And we lack diagnostic tests and established treatments in most of these systems for many of the illnesses. And we need researchers and clinicians to think broadly across systems and combine their knowledge so that we can conquer and understand this illness better. Thank you.
Thank you, Dr. Bateman. Thank you very much for setting the stage, really, for what we're going to talk about the rest of today and certainly tomorrow. So I wanted to remind everybody, now that we've heard some really compelling stories of ME/CFS patients and really reflecting some of Dr. Bateman's experience, we're going to move into metabolomics and metabolism of ME/CFS. And really that fits with the goal of the meeting, is really to present high-quality science, and at the core of it, which relates to what Dr. Koroshetz mentioned and Dr. Auchincloss, is really to better understand the state of the science and the disease and help really drive the field forward by identifying gaps and opportunities. So I think we have tried to identify speakers who can show us some really interesting new data and help us draw conclusions from really some quite diverse aspects of ME/CFS. So it's my pleasure to introduce Dr. Bob Navio from UCSD, who's been studying metabolism, mitochondria for some time, and of course has published some landmark papers in ME/CFS as well. It's a great pleasure to introduce him, and again, I would remind people there's 30 minutes by design here, so there should be a little bit of time for questions. There's microphones in each aisle. If you're not comfortable with the microphones, we do have note cards, and if you have a note card, we'll have someone bring it down to Vicky Whittemore here in the front, who will collect them for questions. So I'd like to introduce Dr. Bob Navio.
Thank you very much, Joe. It's really an honor to be here today to talk to you a little bit about our work. And last time I was here in the Masur Auditorium was over 20 years ago in 1998, when we had just founded the Mitochondrial Medicine Society, and Steve Zello had organized the first NIH symposium on mitochondrial medicine. So we've come a long way since that time. So I want to thank the organizers for giving me a chance to come back. So I'll be talking to you about metabolic features of chronic fatigue syndrome, but really using it as a lens to see the hidden connections to other chronic illnesses, which I think is, a major challenge for us today. So here's my conflict of interest page. So I'm an unpaid advisor for the Autism Research Institute and the Open Medicine Foundation and MitoQuest. And a drug that I'll be talking about today is Suramin. It has no approved uses in the United States, and it's illegal to import Suramin for human use without FDA and IRB approval and an IND. So the talk will be organized into three main sections. One is actually on the healing cycle of pathogenesis and treatment of chronic illness. We'll say some words about purinergic signaling, Dower, healing blocks, ME/CFS, and some new work that we're just publishing on Gulf War illness. I'll finish with a brief description of the proposed Suramin ME/CFS trial, and then I'll end with a slide that we were asked to include as part of the talk, which is research gaps in metabolomics. Okay. So for more information, I have some papers. If you're going to choose one, choose the Metabolic Features and Regulation of the Healing Cycle that was published last year. It actually is the #1 most downloaded paper in the journal Mitochondrion. The #2 most downloaded paper in Mitochondrion is a paper called Metabolic Features of the Cell Danger Response, which has actually been in the top 3 for the last 5 years since it was published. We've recently combined a lot of our work to show how incomplete progress through the healing cycle is a cause of the aging process itself. And if you want additional information, you can go to our website at naviolab.ucsd.edu. So this is a fundamental aspect of science that we all face every day, and that is that we cannot see what we cannot imagine. Okay, so here's a little cartoon of a street light and some scientists looking for answers under the street light. But what I really want to point out is the light is in fact our imagination. Okay, so what we can conceive of is what we see. And sometimes we don't see an aspect of nature just because it hasn't been part of our model of how disease works. So I believe we need a paradigm shift to better understand all chronic illnesses. And a fundamental division occurs between the tools we use to treat acute illnesses that are brought on by infectious disease, toxin exposure, or physical injuries that we've become very good at treating. Okay? That leads to symptomatic treatment. But chronic illness is more about the body's response to those injuries than the injuries themselves. And so I would say whereas for the last 5,000 years, we've relied on book 1 of medicine, I think we need a book 2 now to be able to treat chronic illness. So in August of 2016, we published our paper on the metabolic features of chronic fatigue syndrome. Within 1 week, a cartoonist had come up with this, this nice little cartoon that points out that CFS leaves a telltale signature in the blood. And within a month, Dr. Koroshetz was calling me and doing his fact-finding mission for this new trans NIH initiative that he was setting up. And within a few months more after that, in March of 2017, we have today the Trans NIH ME/CFS Working Group. So really, my hat's off and gratitude to Dr. Koroshetz and the whole team for putting all this together. Nothing in biology makes sense except in the light of evolution. There was a quote by Theodoros Dobzhansky, a Drosophila geneticist and evolutionary biologist in 1973. Nature does not, nature utilizes good ideas in many different forms in life, and that frequently we can only understand biology by seeing how it allows a species to connect with its ecosystem. Okay, to connect with its ecosystem. Okay, so acute and chronic illnesses are as different as apples and oranges, and I will make this proposition that eliminating or treating a trigger of any chronic illness will not cure that illness if you have not addressed the blocks to the healing cycle itself. And so by unblocking molecular steps in the healing cycle, I think we'll open a new chapter in medicine that will lead to actual cures of chronic illnesses that previously were only treatable. So why can't we cure any chronic illness if we can't cut out or burn out the cause? Okay, so we can treat diabetes with insulin, but insulin never cured anybody with diabetes. We can treat hypercholesterolemia with statins, but statin never cured the underlying propensity to develop dyslipidemia. We could go on with every medicine that's used today, just about, with the exception of antibiotics that get rid of an infectious illness. And I would say that we've been using acute care methods unsuccessfully to cure chronic illness for the past 50 years, and that we'll have the same results for the next 50 years if we don't change our model, the imagined model, what we use to guide our experiments. So success in the treatment of why is that? Well, it's because success in treating acute illnesses is habit forming. We get used to using the analytical scientific approach to help mitigate symptoms in chronic illness. It's more of an engineering approach. But in the second book of medicine, we have these responses to acute illnesses or acute injuries, like traumatic brain injury leading to chronic traumatic encephalopathy, or UV light leading to melanoma, or Epstein-Barr virus associated with ME/CFS, or a gunshot wound for PTSD. In each case, just removing the trigger does not cure the illness. So what we're really trying to get at is what are the governing dynamics in chronic illness? We've done a great job in modern medicine and systems biology to define very deep silos of knowledge. So here are nearly a dozen different specific disorders: autism, ME/CFS, Gulf War, PTSD, traumatic brain injury, Lyme, pandas, suicidal ideation, aging, and Alzheimer. And we've done all the blue-colored disorders are disorders that we've studied. We've done clinical studies in metabolomics to try to identify common features. And the point that I'm going to try to make is we can know absolutely everything there is to know about each one of these individual silos and still not be able to cure that disease. Why is that? Because I believe that the diseases share this hidden common feature of the inability to heal from those initial injuries. Okay, so what are some essential facts to understand in the talk? Mitochondria have 3 developmental forms that undergo programmed interconversion when the cell is injured. M2 mitochondria are those that are specialized for OXPHOS. That's what you're taught about in biochemistry. But M1 mitochondria support metabolic features of a cell that has gone glycolytic and that is pro-inflammatory. You need M1 mitochondria in order to mount a defense response against microbial attack. M0 mitochondria are those that are specialized for aerobic glycolysis that are necessary to support biomass replacement and cellular proliferation when cells have been lost. Okay, so the cell danger response coordinates all the mitochondrial functions after injury. And the healing cycle is a programmed ontogenetic sequence that has 3 main steps. It has a beginning, a middle, and an end. And it's coordinated by metabokines that then leverage proteins that then change gene expression. All right. So, let's see if I can. Oh, okay. All right. So we go from a state of health to a state of chronic illness through usually a perfect storm of many factors for any chronic illness, okay? So sometimes it's a collection of genes that predisposes us, that primes us to respond unusually to an exposure to a pollutant or to an infection or a heavy metal or poor nutrition. But we get to chronic illness through a number of different paths. These different paths to illness were never programmed into our DNA, okay? Those are the result of environmental factors that change throughout our life history. So this process of understanding how these different factors lead to chronic illness is pathogenesis, from the Greek word pathos for suffering, illness, or abnormality. And what we know is that if we identify and remove pathogens, if we still have a chronic illness, those treatments lead to palliation, not cure. Okay? So there is a different path that we have to follow in order to get from chronic illness back to health. That path is genetically programmed. Okay? That path is the result of millions of years of selective pressures that have led to a gene pool that can adapt to environmental injury. Okay? And the important thing to understand is that there is there's a beginning, a middle, and an end to this process. And a lot of times, physicians and scientists are taught to think in snapshots, not in dynamics. So thought to think in statico rather than in video. Okay, so it turns out Darwin recognized that that when there are cycles, life cycles within a given species, that there can be carryover effects from inefficient or abnormal completion of one cycle. I wish I could point. Okay, so if there is an abnormal initial phase, there can be carryover effects that lead to abnormalities in the subsequent phases of the cycle. Okay, this becomes an essential point to understand. So the other thing that's important is to understand that, let's see, that oftentimes if we don't have a name for something, we can't study it systematically. Okay, it kind of gets lost as a mist, as a fuzzy concept. And so Salus was a Roman goddess of personal health, welfare, and safety. And that in order to get back from chronic illness to health, there's a process that involves salogenesis, which is not just the removal of the pathogens that brought you to that illness, but now the addition of factors that will promote progress through the healing cycle. Okay, so instead of just focusing on pathogens, which we need to in order to even prevent disease epidemiologically, but once you have it, we also need to talk about salogens and having a systematic pharmacological search for medicines and natural products and interventions that can relieve checkpoint abnormalities that have resulted in repeating diseases that are repeating cycles in each one of these different stages of healing. Okay. So this is just to point out that we start with health, we have injuries, we use the basics of first aid to treat symptomatically, and then for thousands of years, physicians have relied upon the extreme reproducibility of this process buried underneath this black box. Okay, that process is called healing. Okay. But in a changing world that has more pollution, rewounding, crashes, and molecular blocks, we find ourselves in this repeating loop of chronic illness where 30% of children and 60% of adults are caught in chronic illness. And maybe a way out of that is to unpack this healing process and to understand the molecular details of going from one stage, CDR1, CDR2, CDR3, back to health. And then maybe if we do that, we could start having cures of chronic illness. So if ME/CFS is a response to a problem, the question, what causes it, can be as complicated as what causes hibernation or what causes dour, okay? Because it's a syndromic evolutionary response to a problem, it has many causes. So here's some work that we've done looking at what causes dour, okay? So dour is an energy reallocation program, an alternative pathway for the little worm C. elegans that will go from an early stage of development to this alternative dour stage, which allows it to live for 4 months instead of its normal 2-week life cycle. What are the triggers? Well, you can trigger it with overcrowding, caloric restriction, hypoxia, predator stress, dehydration, heat stress, parasite, microbial infections. Okay. And so when we look at the metabolomics of eggs and all the different stages of C. elegans, if we apply stress, we can enter into this dour phase, and then we can exit the dour phase and see what metabolic and chemical changes are required. It turns out that the path back to health, to young adults, is different than the normal path that got you to health. Okay? And it's also not a reversal of the pathway that got you into dour. So here are a lot of different points about dour, and I'm just going to jump to the bottom, which is surprising to many, is that the worms in dour have hypersensitivity with increased cutaneous chemoreceptors that will result in a refractory period after a stimulus that is, you could think of as looking at like post-exertional malaise, where they will, after they have been touched or stimulated, they will not be able to respond to that, for a long period after the stimulus until they recover. Okay, so here is a metabolomic analysis of the different stages of development in the C. elegans from L1 through adults, and looking at how a different specific metabolites change from Dower to recovery. Okay, and so in some cases in acetylcholine, Dower has lower levels and must rise. And other metabolites like 3-methylhistidine, it has a higher level of 3-methylhistidine that must decrease. Hypoxanthine is a purine base that starts out very, very low and has to increase. I'll leave it at that for this. And this is just to point out that Dower is just one example of an highly evolved reprogramming of metabolism that allows different organisms to survive environmental stress. So in bacteria, for example, Lyme and TB both have persister cells where they decrease their metabolic rate to make them resistant to environmental stresses or antibiotics. Other phenomena that you can look up are diapause, hibernation, torpor, estivation, tune in the tardigrade. Dower is what we study. But it leads to these very same core metabolic pathways of energy reallocation for survival. Okay, the fact that healing is a process, an ontogenetic sequence, not a state, is so fundamental that you will make mistakes if you forget this. Okay, so we studied a mouse called the MRL mouse that had very unusual healing properties. If you used an ear punch to identify the animal, it would heal that up in a month, replacing nerve, cartilage, muscle, sebaceous glands, every one of tissues that are derived from the 3 primordial germ layers. And when you injure it, this is a Western blot that shows mitochondrial protein concentrations. Immediately post-injury, mitochondrial protein translation is dramatically decreased. And then 10 days afterwards, it's restored. Okay, so here is this healing cycle that we normally go through for wakeful activity and nutrition intake. Our cells will release a certain amount of extracellular ATP that's metabolized to adenosine, which we need to initiate sleep. And when that is consumed, then we wake up again, and we normally cycle through there. When there is a more significant injury, then we enter into the very first stage of the healing cycle, which is involved in containment and innate immunity that involves glycolytic metabolism. Let's see. Once the healing cycle is complete, the extracellular ATP has been reduced, and we go back to the health cycle again. The underlying metabolic features of each stage allow for the steps of that stage to be completed. So we have to have glycolysis before aerobic glycolysis, before oxphos, and before a reblending of all of the different metabolic states during circadian rhythms. And chronic fatigue syndrome and autism appear more to be a block toward the end of CDR3 in the work that we're doing. Okay, so here are mitochondria. In health, mostly in oxphos M2. During inflammation, they go glycolytic, become M1, rise to M0, and then those fall as the cells have been replaced and stem cells have been recruited, and then M2 mitochondria are restored. So those go under names, but inflammation, proliferation, and remodeling. But the key concept here is that if you are a metabolic lab and you look at a disorder that is in, let's say, an inflammatory disorder that it's in this stage, and you're comparing it to healthy controls, you forget that you can't go from CDR1 back to health. You actually have to proceed through the other two steps. So knowledge of where a person is stuck doesn't actually tell you exactly the path to recovery. Okay? That has to be, that's part of this hidden biology, the root causes that underlie virtually every chronic illness. And now I'll make a couple more points as we finish. So the context of exposure to a CDR trigger dramatically determines the outcome. This happens to be a slide that indicates the odds of coming home with Gulf War illness if you've been vaccinated either before deployment, which is this gray line, or received the same vaccinations after deployment. So it turns out that there's a 5 to almost 20 times increased risk of coming home with Gulf War illness if you receive those vaccinations, in this case, more than 6, after the stress of the war theater was encountered, okay, compared to those that received the same vaccinations before. All right, so here's a nice figure. This is a genetically modified mustard plant, Arabidopsis, that will fluoresce when free calcium is released. And here's a little cricket bite. And if you add either glutamate or ATP, that injury is signaled to the rest of the plant. Okay. So why ATP and glutamate? They have very high concentrations inside the cell, but very low concentrations immediately outside the cell. So that when a cell is injured and releases these molecules, it's a very clear signal that there has been damage. So this is a summary of Gulf War metabolomic pathways, metabolic pathways compared to chronic fatigue syndrome. There are some shared pathways that involve sphingolipids, phospholipids, and branched-chain amino acids. But it turns out that in Gulf War illness, those typically are increased standing pools of these metabolites and are decreased in chronic fatigue syndrome. The only thing that was the same were that purines were decreased in both. We've done a validation study of our first study of chronic fatigue syndrome that has identified, again, fatty acid oxidation, ceramide and glycosphingolipid metabolism as being very important, and purine metabolism, also bile salt metabolism, and microbiome, and sphingomyelin, SAM-SAW. Many of these are the same players that you've seen before. So we went looking. Turns out every stress cell releases ATP and other metabolites through stress-gated channels. In this case, I've illustrated Pannexin P2X7 that are opened under increasing oxidative stress, but specifically by converting free thiols to disulfide bonds, and then also by changing the biomechanical properties of the lipid rafts in which the transporters exist. So mitochondria talk to the nucleus through a short path retrograde, and they coordinate. There's also a long path retrograde signal that involves the release of these molecules that can be traced to mitochondria and bind to receptors that then change gene expression. So we asked this question: if there's a dissipative loss of ATP from the cell, what would happen if we had a drug that might be able to block that release of ATP from the cell? There would be more ATP that could be used inside the cell for purposes of growth and healing. And it turns out recently there's been an identification of a P2X4 receptor that is, upregulated in chronic fatigue syndrome patients compared to controls. So when we went looking, there was one drug. That drug was Suramin that could be an inhibitor of extracellular ATP signaling through several of the 19 purinergic receptors. And that, just to illustrate this, I have a little video. So we did a clinical trial of low-dose Suramin in 5 boys with autism and 5 controls. It's a 100-year-old drug that's been used to actually treat African sleeping sickness. It's no accident. Sleeping sickness is actually an infection-related chronic fatiguing syndrome, related to a persistent infection. Here's a cartoon of a neuron with a nucleus and mitochondria and channels that allow for ATP release and for and receptors that bind to ATP that triggers the cell danger response. And the neurons will then go into a survival mode. If you treat with Suramin, the idea is to block the ATP production and to then allow the cells to maintain more of that molecule in order to heal. So we've had this IND approval, FDA approval for a Suramin ME/CFS remission recovery trial for 3 years, and it's only in the last year that we have the ability to that we have new Suramin and a new sponsor that is going to help with funding this. And I'll just give you a brief idea that we'll randomize into 2 different arms. There'll be 2 doses over 2 months, and then we'll look at outcomes before and after. So that is the end of the main talk. And then this last part is just a discussion of analytical and biological gaps in metabolomics that is something important for the field to develop. And I know I'm 5 minutes over, but I will maybe just save this for question and answer later, and some of the people doing metabolomics can really get into the nitty-gritty of these. And then I want to say thanks to all of our supporters. This work has been supported by over 2,000 grassroots supporters all around the world, and a number of private foundations, including the Open Medicine Foundation. And most importantly, I'd like to give thanks to a little girl named Christine Shimizu who had Lee syndrome and died in 1998, whose life and memory has inspired every discovery we've ever made over the last 25 years. So, thank you.
I'd like to continue our session on metabolomics and metabolism of ME/CFS. So next we're going to hear from Dr. Oliver Fien, who's at UC Davis, where he is in the UC Davis Genome Center, and he's the director of the West Coast Metabolomics Center. Dr. Fien works closely with the Columbia Collaborative Research Center that Dr. Koroshetz outlined earlier, and is part of the effort that began at the end of 2017. And today he's going to talk to you about informatics tools for investigating metabolomic dysregulation in ME/CFS. Dr. Fien?
Thank you. Thank you. So we had a great introduction from the West Coast of the United States, San Diego, Bob Navio. It told us all about how important metabolism is to understanding energy dysregulation, and talked also about systemic effects and the similarities between diseases that we should more focus on, and not just one disease, but also the comorbidities, and he focused on the healing process. So that's a great prelude to what I want to say, because I have similar punchlines in a way. So first of all, let's have a look at metabolism. So that is what we study when we are undergrads, right? So we look at the major inputs and outputs in terms of energy metabolism, fats, proteins, glycolysis. And you see that they are linked. There are many ins and outs. It's much more, if you can actually look more closely, then there's all of a sudden lots of shunts, lots of exit routes, lots of more network effects than what you have studied when you were younger. So that while metabolism in this broad view is of course important, it's not the only one. So that is metabolism, what I show here, the metabolism of building and burning of energy and building macromolecules. But there's also a much more important, maybe, metabolism of regulation. So let's assume now that we have lots of data. And we have lots of data from humans. And then in aim 3 of any of our grants throughout the NIH, we say, we take all the data and we integrate the data and we make fantastic new tools to improve our understanding of the disease. And we have a patient cohort of X number of patients that we have thoroughly looked at with controls. If we are good, we have even a good study design. To me, a good study design is a longitudinal study design, but since this is our first grant, we do a cross-sectional only because. So that's the classic NIH grant because, right? So the problem is there that we want to achieve a systemic understanding, and usually we then say we will look at genes and proteins and metabolites, but all these parts of the system, they work on the cellular level. And what we get from patients are usually not biopsies. We usually don't get a lot of muscle biopsies or other types of organs, say brain biopsies. We get some body fluids. And most often we get blood. And if we look into blood, you see, as you see on the left-hand side, you know, that is the big interstate of transport between organs. So to try to read what is going on in the different cells under different conditions, and you only look what is happening on the interstates, it's a hard task. Specifically now, if you then want to look also at genes and where you get the genes from, maybe from erythrocytes, from white blood cells. So some other cells that are not even remotely similar to where the disease is located. And that is why this is complicated in terms of informatics, just because our study designs do not often look at the cause or where the symptoms are or the cause of diseases, but we look in blood because we are working here with patients, and that's the easiest access point. So let's have a deeper look. So this is the state of California, and we see here Sacramento is the capital of the state, so that's where the influx is of water, and also politics, I guess. And then you see San Francisco, that's where the pentose phosphate pathway, so they make a lot of money there. So then they sent it down, all the energy down to San Diego and Los Angeles, where the mitochondria reside. And as we have learned, mitochondria are really important, Hollywood, and they make more money there in terms of ATP and NADH. So this is all very important and tells us about sugars, fats, and amino acids if this was glycolysis and primary metabolism. It looks actually very similar. Now, the point is there is a lot more traffic in California. There's lots of roads and even streets in cities. And they tell us a lot more about regulation of fluxes of metabolism and more than just looking at the interstates. And these are, some of those compounds have been mentioned before by Bob Navio. For example, ceramides, sphingomyelins, they have very active roles in many diseases, but also oxylipins. They are clearly important in inflammation resolving, but also in many other physiological actions. These are usually very low abundant metabolites at nanomolar concentrations or even lower. We used to only look at hormones and cytokines, but now we need to understand that in biology, everything can be used as a signal, a systemic signal that travels across the body and then triggers responses elsewhere. So we should not just look at the very abundant primary metabolites, we should also look into novel metabolites. That includes, for example, microbial metabolites that get into the vascular system, but also like bile acids. We now understand bile acids have lots of secondary functions and bind directly to receptors. FAFAs are involved in diabetes, and so on and so forth. So this is the reason why metabolomics is more than just fats, sugars, and amino acids. All right, and that's why at the West Coast Metabolomics Center at UC Davis, we use different assays. So on the one hand, we use so-called untargeted assays. These are both hypothesis-driven and, at the same time, hypothesis-generating. We usually do relative quantification, and we move towards absolute quantifications for these untargeted assays as well. We usually have 150 to 600 identified compounds per assay. So for example, in lipidomics today, we would have 500 identified lipids. In primary metabolism, just 150. For biogenic amines, which are TMAO, carnitines, betaines, oligopeptides, nucleosides, and similar compounds, we would have maybe 300 identified compounds. So that we overall, in metabolomics, by these assays alone, we get something like about 1,000 identified compounds in a specific tissue or blood or so. Then we also get a lot of signals where we don't know what they are. We can do statistics with them. We can annotate them by chemical classes, and as I will show you today. But we don't know the exact chemical nature of those yet. That means they might be involved in diseases like ME/CFS, but we don't know yet. And then again, we have targeted assays. Targeted assays are only hypothesis-driven. They're always given in absolute or molar concentrations. Usually these targets are 10 to 80 compounds per assay, for example, steroids or short-chain fatty acids or oxylipins. Many of those have already associated diagnostic roles. But we need to get to them in a targeted assay because they're usually very low abundant and sometimes also require very sophisticated types of cleanup tools, sample pretreatments. So what my lab really does is we try to find everything we can from a specific assay. So we produce a lot of databases and tools. Some of them I want to show. For example, MS-Dial is a tool that is everything is freely available, open access for untargeted assays, including the identification of unknowns. Oh, okay. Well, there. Ooh. By spectral matching. So this is one mass spectrum you see. And the identification works best if we have a giant database behind it. So where do we get giant databases? Well, there are some that can be purchased. For example, NIST-17 is an affordable library that we can buy from the National Institute of Standard Technologies. But today, most researchers make their spectra freely available. For example, from HMDB, that was already mentioned by Bob Navio, where they have 4,000 spectra available, GNPS in San Diego with 16,000, Mass Bank from Japan with 48,000. And for my own lab, we have added maybe 60,000 spectra that were not reported before. So we put them all together in a big mass bank for everybody to download to basically help people who have untargeted assays to identify those compounds. So when we then compare between those databases, we see that we get here about 8,000 novel compounds experimentally done that have never been shown in commercial libraries, whereas NIST 17 is clearly still the best and best also curated database that people get now. Now we say that with every single new library or database, we get novel compounds for specific compound classes. And this is how we present those compound classes. And then we see when we compare those that some of them are really better in NIST 17 and others like lipids are better or polyketides using our database. So we say that is a concerted effort and we should not disregard any of them. As I said, usually we get a lot of spectra in a profile, but many of them are unknowns, and usually we don't like to talk about those unknowns, so we recently published another paper where we said if we add more informatic tools, including the new NIST hybrid search, but also new databases like Carniblast, we get annotations across the board for every single spectrum, so that at least we know the compound class. And we do this by basically using the NIST hybrid search and asking, well, what could happen to known compounds? They could be methylated, hydroxylated, phosphorylated, acetylated, or other types of modifications can happen to molecules. And when we do a hybrid search, we move those ions around to known compounds, then we are able to annotate them. We wouldn't know exactly where the hydroxylation or the acetylation happens, but at least we have a good feeling of what type of compounds are these unknowns. And we can use them in, for example, big classes and use these classes for statistics, for enrichment statistics, so that we see in a certain disease or a certain phenotype, we have an enriched class of dysregulation, say in benzenoids or in organoheterocyclic compounds beyond the known classic compounds. All right. So next thing, what we did is we said, look, if my lab is doing good work and Bob Navio's lab is doing good work, that's all fine. But then we publish, and then people have to recover those data from publications. That is incredibly hard. We need to fill databases, and we need to do this in a validated and harmonized way. We can standardize a lot of things, but we will not be able to standardize the actual machine that people will use, because in capitalism we like competition, so there will be different companies offering machines. We used here the same 155 human plasma samples and first published the biology, and then we published method validations on top of them. We repeated the same analysis 9 times with 9 different mass spectrometers from different vendors. And what you can see here on the right is principal components analyses of these treatments. This is before and after a certain intervention, and the different colors are different subjects. And then we had a longitudinal design, and we see that the overall phenotypes, the metabolic phenotypes, was always retrieved very accurately for each of those subjects, with no matter which mass spec we used. So that is one of the criticisms that have been raised in metabolomics in terms of validation. We can validate it. We can move, even with untargeted analyses, further and fill databases so that we can better address what is normal and what is a dysregulated state. The next thing is we also run often very large studies. Now in ME/CFS the sample sets are very small, maybe 50, 100 or 200 subjects, but very, very small. In other cohort studies, we easily run 5,000 samples or 10,000 samples. And what happens then is the machine would give us errors based on the machine cleaning or we would need to change maybe a column or buffers, or we would somehow handle the physics of the machine, and then you get a different response, and this has to be normalized. And classically, this has been normalized by locally estimated scatter plot smoothing, but as you can see here, some of that method was over-normalizing so that we still got residual variance in the data set. That is bad because it increases the technical error, and therefore we lose statistical power. That's bad. And so we use now different methods, random forest machine learning methods that works great on large cohorts and also stabilizes, again, the idea it validates metabolomics to be used in filling databases. So what else needs to be done? So far, reviewers in NIH grants only look at, has this investigator published? Has this investigator good mass specs? Oh yeah, this is an expert lab. Now this is not good. The NIH needs to change some rules in terms of reviewing grants, because if we want to compare results apart from manuscripts, if we really want to fill in data into databases, we need to have a lot more quality controls to systemize and normalize data. In our lab, what we do, we have NIST reference standards. We have pools from the cohorts that we analyze. We have blanks and commercial pools. You can also add, and some other labs would use mixtures of external compounds, up to 1,000 compounds I have seen. So these are different ways to do it, but as you can see now, we have here 4 types of injections before we then do 10 samples. So this is important, and the point is, if these data are not uploaded, I cannot compare and contrast the data and validate data across different laboratories. So this is not required right now, and it needs to be required both for databases as well as for grant reviewing. Next time you review a grant, please look for that. Okay, so next thing is we have seen by Bob Navio the use of MetaboAnalyst. And MetaboAnalyst only looks at known compounds and known pathways. Specifically the KEGG database that's behind it. KEGG is a database in Japan. Now, biochemical databases are incomplete. It relies on the definition of pathways. You ask 10 people, and they all have different definitions of pathways. So therefore, the statistics behind those pathway definitions is different. The MetaboAnalyst uses an inappropriate statistical design. Also, of course, the background database for what is the metabolome is not defined, and you lose many identified compounds that are not found in biochemical databases. So instead, we use the chemistry itself. We put compounds into chemical classes, for example, unsaturated triacylglycerides, and then we get very similar results in terms of the differential regulation of metabolites, of phenotypes or metabotypes. But it's not depending on a specific biochemical database, because it's only depending on did we identify the compound or not. So if we then have a final result, we need to convert this result to regular people, and that is often what we show. So that is actually from ME/CFS patients in the beginning. So we'd say, well, we know about serotonin. It's an important neurotransmitter. And so there's a breakdown of methoxytryptamine, but also tryptophan is broken down to indole lactate. So, we see these 2 compounds. They might refer to that pathway. And that is a legitimate way to talk about data in a pathway or in a study. We can also talk about cytoplasm versus mitochondria, where we see, some vitamins were increased and TGs were increased versus PCs were decreased in ME/CFS. So we saw that, and we can talk about it, but then, we sometimes have confounders. We found, for example, ME/CFS patients have higher intake of vitamins, and that would easily explain the increases in pantothenate and nicotiniamide. So there is the cellular view that needs to be confounded by what we know from the metadata. We can't just do the statistics. So instead, we now do the text mining to link phenotypes to metabotypes. So we now say, instead of relying just on databases, we need to rely on everything that has ever been published. Okay, NIH is very much involved in this because we use NCBI tools here. And here we first ask the question, what do we know about blood anyway? What compounds are in blood and how many? What has been reported in the last 150 years? So we downloaded 38 million abstracts and 8 million full research papers, including supplements. We looked at 4 million Wiki sites and many other tools to say, well, what is known in blood? And that is what we know. So in 1 million publications, we found that metabolites were analyzed in blood. And there are 3,000 compounds that have been found more than 100 times. So these are very likely, the classic metabolome that we should look in the blood. But there's also 21,000 compounds that have been published at least once in blood. Many false positives will be in here, but not only false positives. So that gives us the first time the idea of how big the metabolome is. We then used in the first test 50 cases versus 50 controls, and we published that last year. And so this is the different types of metadata we got. But you see, we don't get a lot of history. We now understand that there's always a trigger. That could be an infection trigger, could be a stress trigger, could be many different triggers for different patients. We don't get a lot more, information. For example, the duration of upright activity that Dr. Bateman told us about. So that is not something we got here, so we can't do the statistics on it. And more importantly, what are the controls? How can we really compare these controls? So these are really important questions that we right now can't address. So we used both we used 3 of our assays, or 4 of our assays, but we also, with Ian Lipkin and Columbia, used then fecal bacteria and looked at if there's commonalities that can we integrate this, for diagnosis, for example, can we learn about it? And we then did the enrichment statistics analysis that I showed you before, where we saw that PCs were decreased, TGs were increased. So that's similar to what Bob Navio found. Increased also ceramides. These are the biofunctional lipids. And a couple of others, of course, individual compounds that were different, but not systemically across all the compounds in a certain chemical class. And then we also looked into how is it confounded with IBS, because a lot of ME/CFS patients have also IBS, so we need to be distinguishing, is it specific for ME/CFS or is it systemic also across IBS? And then we can basically refine these, and we see that it's also still the TGs and the ceramides were still different, for example. So then we can display this through chemical mapping, just because it's a little clearer than a table. I mean, it's the same information as a table, but we see now clearly that the lipid regulation is different, including LPCs. So these are partial degradation of lipids in terms of getting at one acyl group. TGs higher. So overall, that might indicate a problem in lipase activities. But which lipases? There are many lipases. We don't know which ones right now. We see the ceramides and sphingomyelins here dysregulated here. We see also changes in acylcarnitines. Acylcarnitines are also a good marker for mitochondrial activity in terms of overload of mitochondrial activity, and here we see that they are downregulated. So a lot of this can be already discerned from such kinds of overviews. When we now integrate bacterial information from stool samples, we see that in the integration, we get better recognition than by either of these omics tools alone. So the metagenomic and the metabolomic tools together were better able to distinguish the controls, which are in yellow, from the ME/CFS patients in red, no matter what type of lens or bioinformatic view you would take on this data. So we, since we published that, we continue that in CSF fluids because it's closer to the disease. We see clear differences depending on which kinds of controls we use. We haven't published that yet, but I think it's ongoing. And so you will learn more about that, and my time is kind of up. So I want to tell my last 2 minutes or so about how I see it, and Bob Navio also thankfully did a little bit on that. I really think that metabolomics has to become more standardized so that we can better communicate across. For that, we need kits of internal standards to do absolute quantifications, just like Bob Navio said. We need single software, and my lab does this through cloud computing that is able to take in any data from different laboratories through the same type of data processing. We need to be faster. So we opened a secondary lab in Sacramento to offer 2 weeks turnaround time, and eventually, at least for UC Davis, 24-hour turnaround time so that we can actually do this cheap. We also need to be cheaper. So we lease instruments, we go for robotization. So that's all data acquisition. But in terms of linking to population health, we need a much bigger databases to tell, what is a normal population? What do we see normally, not only in these few controls that we picked here randomly, but really across the population? And we don't know that yet. And we need to link to text mining instead of genetic and genomic databases, because the best of what research has done over the last 50 years is found in papers. We need to get it out of the papers in order to do complex interpretations. So overall, we have, I've shown you some of the tools that we have developed and how they can be used. Some initial lessons we learned from plasma differences, similarities and differences to what was published before. And we see that we can integrate data through multiomics, but we also see that it's not exactly easy to do. But there are tools from literature text mining, metagenomics, and other types of multiomics tools that we can use to better interpret and also diagnose subjects. So overall, I'd like to thank you for your attention, and specifically I'd like to thank Professor Ian Lipkin and the ME/CFS consortium that he leads, and the NIH for funding. Thank you for your attention. So that's okay to a couple questions because the timer is a little different than in the morning. Are there questions? Yes.
Hi. I was just asking myself if the quality control would be improved by not only sharing data, but also the software used in papers and so forth, and how available has that software? Your ChemRich and Exposome are posted, including source code.
Yes, absolutely.
I just wondered if you could comment on.
Absolutely, I'm fully with you. We need to have transparent and open science, and I urge also vendors to open their data and their raw data, and I urge also all scientists to use open access and open source informatics tools, as long as these ones are better than commercial tools. And interestingly, so far, all open tools are better than commercial tools. So then we can have competitions. We can use the same data and use different tools to dig deeper. And if people only use their own little homemade and home-based solution that we cannot really share, but here is the idea, well, that doesn't help anyone. Nobody can replicate. Nobody can control. So I think in the 21st century, we should have a different model of doing science.
as both a patient and a researcher, sort of building off of that, I really appreciate how accessible you've made this, combining different data and one tool across many. But the side of being a patient and the many patients here, will this include accessibility to help work with how to access the data, how to make sense out of the accessions and what the different forms are in terms of what's documented and answering questions that are submitted?
We try. We try to be systematic and using ontologies where people can use regular terms that are immediately recognized instead of fixed terms that are only used by specialists, right? So that's one of the things that we need to do in informatics, to use layman's terms and regular syntax. And in California, especially in San Francisco, we have the Silicon Valley with Google and so on, and it's amazing what comes out of that. So I think we need to embrace that more clearly, these types of regular syntax and regular orthologs. We also did it for chemistry. We have a chemistry translator, CTS, the Chemical Translation Service, because chemists use different terms for their molecules, right? And that's what we published 10 years ago, right? So yes, I'm fully with you. It has to be understood by regular people and researchers alike.
Thank you. And just a thought to end that is it would serve a great need if you could add to what you've already done as a huge amount of work, an interface that patients can have a say or ask questions to.
Yes, we will try. I will repeat. I will repeat. Yes. So the question is, sometimes we see certain metabolites in subjects, but not in the controls. There might be missing values then. Statisticians cannot deal with missing values very well. And also there are 20,000 different ones. How can we even help other laboratories to find the exact same compounds? So this has therefore two answers, and then I'm done. So first thing is, in terms of making sure that different laboratories can find the same compound, that is again normalization, but also making spectra available, including methods available, including retention times and so on. Also for the, we need to make in silico spectra, we need to predict how the mass spectrometer will act on a molecule. So that's for the enabling to even find the same compound. Then for missing values, there don't need to be missing values. Every instrument has local noise values. And so in all our samples, there are no missing values. We immediately go in the data processing workflow. If we find a molecule and we are sure the molecule is there, but it's in the next sample, it's not reported, we go to the local noise and look at the local noise and use the local noise and replace the missing value, right? So we say, we have a limit of quantification, limit of detection. We give that, so if we then say, well, it's below the limit of quantification, that means it's noise, but at least statisticians can work with that, so that they don't have to come up with fancy tools to imagine how would a value look like if we had measured it. And there are lots of statisticians who try to do that. Okay, thank you so much.
Thank you, Oliver. So our next speaker and the final speaker in this session is Dr. Jonas Bergqvist from Uppsala. Dr. Bergqvist is a professor of analytical chemistry and neurochemistry, and he has a specific interest in clinical neuroscience, and I think you'll see that. His title is Biochemistry to Support the Evidence of Neuroinflammatory Involvement in ME/CFS, another topic that I know we'll return to during the conference. So it's a pleasure to introduce Dr. Berquist.
Thank you so much, Joe. And it's a great pleasure to be here. And I'm very honored to be, I think, the only faraway foreigner actually giving a presentation today. So I will bring you over to a place where it's a bit dark and cold still, but we are improving. And we are going to Uppsala, which is a small city in the north of Stockholm, in the country of Sweden. So what made me come to this place and give a presentation? Well, there are different reasons, and some reasons are in the audience, actually. I will get back to that soon. But one thing that I would like to start with is to announce the very good news that we got, and we actually are making public this week, is that the Open Medicine Foundation has agreed to fund a third research collaboration center at Uppsala, together then with the two collaborative centers here in the United States. So Ron Davis Center at Stanford and Ron Tompkins and Wen-Chong Chow at Harvard University. So that's a great honor and pleasure for us in Uppsala to have the chance to collaborate around ME/CFS with these great teams in the United States. So then, what makes Uppsala special? Well, I had to think a bit about that. It's a very small place. We are not that many people in Sweden, and in Uppsala we are not that many people either. So it's a very old university. It started in 1477. It's among the top 100 universities in the world, apparently to some scores. It's a very small city. 25% of the whole capital or city population is students, and we have a very integrated research center and university campus. And I think that's one of the keys why we have actually been very successful when it comes to developing methodologies and tools and things to use for measuring things. So we have a close collaboration with the clinics, with the preclinical departments, with the research and technology development departments around the city. We actually have one part of the university on an island in the Baltic Sea, which is actually this Campus Gotland here, which we adopted just a couple of years ago to become part of Uppsala University. We have some famous names that came from Uppsala, and you will probably recognize a few of them. So Olof Rudbeck, for instance, who discovered the lymphatic system. And that evolves a bit to what I'm going to talk a bit about today, the immune system and the nervous system when they collaborate or don't collaborate. Carl von Linné, I think you know, and the Celsius, Ångström, Tobin Bergman, Scheele. And we have 8 Nobel laureates coming from Uppsala, and thinking of that as a small city, a small university, that's rather impressive, I would say. We also have some pretty famous former students that comes out from Uppsala University. And Jöns Jakob Berzelius, or Berzelius, was one of the students, and he made his basic studies in Uppsala. But then when he was supposed to defend his thesis, Uppsala did not approve of that, so he actually moved to Stockholm instead. He became a very famous chemist in the end, and was the father of chemistry to many of us. He discovered 4 elements, among selenium and silicon and thorium and some other elements. And he also gave name to proteins. The protein name came from Jöns Jakob Berzelius. He also was one of the leaders to start the Royal Academy of Science in Stockholm. And as you know, Royal Academy of Science, they hand out the Nobel Prize, and that made Uppsala very upset, I think. And now, you know, the Nobel celebrities are held in Stockholm instead of Uppsala. And, well, it's not so far away to go down to Stockholm, but it's a bit a pity, we think. Anyway, he also wrote the first book in clinical chemistry. He wrote it in Swedish, and he named it Lectures in Animal Chemistry. And since it was printed in Sweden and in Swedish, it did not spread around the world so much. But he actually touched upon a very, very interesting subject to me and to some of you in the audience. And it was the idea of looking into different body fluids. And in this book, he presents the body fluid called, in Swedish, brain water, hjärnvatten. And he actually describes this water very, very delicately and and it realizes the content of this liquid then that surrounds the central nervous system. And I will teach you some Swedish. Denna vätska är vanligt gulaktig, stundom något stickande i grönt. Har en söt, sliskig smak, saltsmak. So it means it's normally clear liquid, sometimes a bit yellowish, even sometimes green. I think that's not really what we see normally. The taste is a bit salt-sweet. So that's what he used as a detector. Luckily, we have other tools today. And he also realized that if you mix alcohol into this liquid, it actually gets, you get precipitation of proteins in there. So there's protein present in this liquid. So how do we study the brain today in Uppsala? Well, we don't taste the samples normally. We use other tools. And we have been quite successful of developing new methodologies for sampling the central nervous system in alive patients. And that's some of the tricky parts of getting to the central nervous system. Of course, imaging is a fantastic tool. And I will just say that. We haven't mentioned that in the lecture otherwise. But combined with that, we use, for instance, filtration technologies called microdialysis. Some of you know it from animal models, but we use it in intensive care unit as a standard procedure for monitoring traumatic brain injury patients, for instance. It's a small device you put into the tissue, and then you can filter out metabolites or even larger proteins nowadays to look at what's happening in the central nervous system. We work quite a lot with one part of the brain that is actually something we can see, so that's the eye. And we monitor things in the eye, for instance, in aqueous humor, which is a liquid you can get to by sampling the frontal part of the eye here, just on top of the lens, basically. We do isolation of extracellular vesicles. One thing we have been struggling quite a lot with is to get specificity and get enough clean vesicles to do monitoring of biomarkers for certain organs, but that's something we work with. We'll work a lot with cerebrospinal fluid, and we'll get back to that in the data sets. We do autosurgery and do microprobing through autosurgery. So when there is a surgery going on through the ear, we actually can get samples collected from brain with a small microprobe that we have developed. We do biopsy material and autopsy material, of course. And then we also do things in blood and dry blood spots, which is, of course, something that is more available than many of the other devices that we have here. So for analysis, normally we do shotgun or targeted proteomics using mass spectrometry, or metabolomics that we already heard very nice presentations about. So I won't dwell into the technology in itself, but very, very advanced separation, multi-dimensional separations connected with very high resolution mass spectrometry, with tandem mass spectrometry as the feature where we do sequencing on all the molecules we get. And that leads to a lot of data, and data handling, as we learn, is a complex thing that we struggle with sometimes. Today, I will just tell you what we are doing right now. So how did we explore ME/CFS? And actually the reason is I like skiing, and there was a neuroimmunological conference in Vail many, many years ago. And Vail is a nice place to do skiing. But also we can meet some people that are very interested in neuroimmunology. And Steve Schutzer is in the audience. He was one of the reasons why ME/CFS came onto my table and into my interest. And I will show you later what we did. So you know that the immune system and the central nervous system is communicating in a very, very delicate way. And in many ways, it's a very good way of controlling what the development of the central nervous system is doing, but also the central nervous system controls the immune system, and the communication is super important. But sometimes things go wrong. So for instance, in autoimmunity, we have problems with that the central nervous system is affected by our own immune system. We have problems with dysregulation in the gut. We have problems with immune targets that are affected by the central nervous system and vice versa. So that makes it very, very intriguing to look at, but it also makes it very complex to understand in great detail. So we're trying to get into this and also look for ME/CFS biomarkers in this area. So that led to this paper. Actually, it started with a collaborative work with Steve, where I collected a lot of healthy individuals in Sweden for cerebrospinal fluid, and then we matched and we monitored the healthy control proteome of cerebrospinal fluid in collaborative work. And we followed that up in 2011 with this paper. It's still one of my most downloaded papers, I have to say. And Ben Nathelson, I don't know if you are actually in the audience. I think you were supposed to come to the meeting, but I hope to see you here anyway. Came with his ME/CFS patients, and we compared them with cerebrospinal fluid patterns from post-treatment Lyme disease patients and with my controls then. And what we could monitor at that time with high or deep proteome technology that has, of course, developed since then, was a large set of proteins and potential biomarkers in the cerebrospinal fluid. So what you see on this Venn diagram is just that we have a fairly large overlap here of what is expressed in all the patients, in all the controls. And then we have unique features for the normal individuals, for the chronic patients, chronic fatigue patients, and then we have for the post-treatment Lyme disease patients. And what could we tell from this data? Well, we could actually tell in very short that we have a low-grade inflammation that we can monitor with this technology in the central nervous system in both ME/CFS patients and in post-treatment Lyme disease patients. We have a significant increase of synaptic plasticity and neural migration activation. So that could be something positive sometimes, but it also can be a reflection of a neurodegenerative process that is happening and that we try to get rid of or solve. And then what we could see specifically in the ME/CFS patient group was problems with axonal regeneration and repair. So that was the findings from 2011. What we are now doing, and the data I will present now, is just a follow-up on what we have been working on for quite a while, and it's been quite a lot of methodological and technological development going on for making this possible. This targeted proteomics, where we have selected a number of interesting markers that we would like to follow, and we do it, in this case, not with mass spectrometry, but with immunoassay-based methodology called proximity extension assay, as I will show you. So the technique is a development of a breakout from the University of Uppsala, and a company is called Olink now, and it's partly based in Uppsala. Let's see if I can turn off my sound here. So what it does is it can, from a very small sample volume, less than 1 microliter actually, if it's a protein-rich sample like blood, collect biomarkers of different kinds. And what you use is a pair of antibodies that bind selectively to your target. And on the antibody you have an oligonucleotide that can ligate, and then you can do extension assays of that. If you have 2 binders to a non-target molecule, you won't get the hybridization and you don't get any signal. So then you extend the ligase with DNA polymerase, and then you do PCR, quantitative PCR on those amplifications. And then you get a qPCR readout from the signal. And in each panel we have used, there are 92 protein biomarkers, and you run it on a 96 well plate format, so you get the data for your selected panel then. Of course, you need to know what you're looking for, and you need to select the panel. And then you can do multivariate data analysis or principal component analysis and sort your patients based on their fingerprint or protein panel readout. So we have done this in 2 steps. We have done one study design where we had used 24 ME/CFS patients with matching cerebrospinal fluid and plasma samples. We have used 24 fibromyalgia patients, and we have used controls. They are all sex and age matched, and all collected at the same, following the same strict protocol. And we have used QC and QA samples included. And this is supported by Open Medicine Foundation, by the Swedish patient organization. Olink has also been contributing with their methodology and helping us improving the methodology, and a collaboration then with the pain clinic in Uppsala and with Kaja Gottfrieds in Göteborg University. And for the first set, We run one panel only for 92 selected neuroinflammatory markers. And that's still a lot of proteins that are supposed to be measured quantitatively. And the readout from this still non-published data is that we found 25 CSF proteins that were significantly different between the 3 different patient and control groups. So between the fibromyalgia, the ME/CFS patients, and the controls. And we could see that there is a general increase of neuroinflammatory markers in both fibromyalgia and the ME/CFS patients. Only 7 plasma proteins were found to be significantly different, which was a bit discouraging. So cerebrospinal fluid is much more rich in specific signal. That's what we think of. And of course, that is a backdraw since it's more invasive to get the cerebrospinal fluid. The second study that we just got the data, actually I got some of the final data this week before I left onto the airport. We have done a screening only using very small cohorts, 7 ME/CFS patients, 7 first attack relapse remission multiple sclerosis patients, and 7 healthy controls. So 21 samples in all, which is a very, very small study. But we selected these patients with great care to be able to use them for a set of validations just for checking through all the panels available. Still 6 age-matched controls and all samples collected following the same procedures. And this is also supported by Open Medicine and the Swedish Patient Organization and O-Link, and in collaboration with Kai Gottfrids in Göteborg. At this time, we had the possibility to screen through actually 13 different panels. There are all the panels available today, so it's about 1,200 targeted proteins then that could be related to neuroinflammation, cell damage, and repair. And you see the names of the panels. They reveal somewhat what they are containing, not perfectly, but you can understand that some of them are more directed into neuroinflammation, some of them are more into cardiovascular, cell repair mechanism, and so on. About half of them were possible to detect in cerebrospinal fluid in more than 50% of the sample. So we set a cutoff there. But I mean, most of the proteins were actually detectable in some point in some of the material. We can also see that the distribution of the samples are fairly well spread over the different panels. So there's no bias on specific levels. You see that the controls on the ME, the green ME patients and the blue MS patients, they spread similarly across the different panels. And we just selected a few of the significant hits we had, and this is just a preliminary data set now, where we have the controls in pink, I guess, the ME patients in green, and the MS patients in blue. And you see, you have significant differences, and what is fairly easy to see is that the MS patients, they protrude out, they're more significantly affected, and you see more inflammation and so on. But in total, 53 different proteins were significantly regulated between MS, ME, and controls. And you also see an interesting tendency, and we see that in many of the proteins, that ME comes somewhere in between the controls and the MS patients, which is telling us something. But you can also see some examples where the ME patients, they differ quite a lot from both controls and MS patients. So we're now looking into this, and based on these 13 panels, we have selected 43 CSF patients that actually comes out as very interesting for the ME/CFS patients specifically. Generally, we can say they still are increased markers for neuroinflammation, cell damage, and repair, and it sort of tags along with what we found in our early studies. And there are both similarities and differences between the ME/CFS patients and the MS patients, which we expected a bit. So summary of what we are doing in Uppsala right now is that we have been able to see these significantly elevated levels of neuroinflammatory markers, both in ME/CFS and contrast patient groups. Cerebrospinal fluid is our target, and we have used untargeted and targeted proteomics for these approaches. What I don't have time to tell so much about today is the other ongoing studies that we're conducting in Uppsala right now, where we, for instance, look at the disturbed steroid pattern, steroidogenesis, that we can find in the ME/CFS patients. And then we target plasma samples, so more easily to access. The signal that we see in the steroid cascade is related to potentially mitochondrial dysfunction, so I think that is an interesting lead. We also, by the help of Solve-ME, set up a new thyroid hormone mechanism method for analyzing all the patterns in the thyroid hormone regulation. And our initial data looks that we find a significant change in the ME/CFS patient when it comes to thyroid hormone regulation. We have also been able to verify and repeat some of the studies that have been done by Carmen Scheibenbogen in Berlin, where we find these significantly elevated autoantibodies against adrenergic and muscarinic receptors. And we find them in the ME/CFS patient plasma. We don't find them in the cerebrospinal fluid, so they are not what we think intrathecally produced antibodies, at least, so that could be good when it comes to potential treatment to remove these antibodies. And then in collaboration with Simon Carding's group in UK, we have done a small metabolomic alteration finding in gut of severe ME/CFS patients. And Daniel Vipond in the audience is a PhD. Well, I can say you're a PhD now, right? He was formerly a PhD student. Now he has actually today got a note that he's approved. Congratulations, Daniel. They compared with household controls, which is very interesting as a control group to follow. So by that, I would like to stress the need of being curious. I think this field of research is driven by curiosity from my point of view and from many of you in the audience also. I think we need to think about what to look at. And Bob presented very nicely. We have the tools to look at certain regions. We have to be curious enough to explore regions where we have not been able to go before. Maybe by having some invasive sampling going on, like cerebrospinal fluid collection. We need to continue to explore. So we need to explore what we can get when it comes to the biomarker panels and biological reasons for this disease, to be able to explore and explain and potentially also come to a treatment in the end. And of course, the methodology. The methodology is developed all the time. Back in the good old days where you had to taste your sample or look at the color of the urine of the patient, it's long gone now, and we have all these fancy equipments, but we also have to use them with great care and with understanding that complexity when it comes to instrumentation and analytical techniques also can lead to false discoveries and problems when it comes to data handling. So have that in mind. So I will end up with just thanking all the contributors to the research, and also very warm thanks to Linda Tannenbaum, the CEO of Open Medicine Foundation, who have been tremendous helping us with setting up the research center. So thank you, Linda, very much for that. The Swedish RME patient organization for their support, Solve-ME/CFS initiative, Ramsey Award there, and Invest in ME in UK. And our clinical colleagues, Kai Gottfrieds, Per Julin, and Simon Carding in UK, and all the patients and the healthy controls that contributes to the research. And thank you very much for your attention. And I have time for a question. Yes, you.
Very nice talk, thank you. I have a question about, you mentioned that you carefully selected controls for some of your metabolomic study, and that's a theme that seems to be recurrent for all three talks about metabolomics and proteomics approach to identifying differences in ME/CSF. Can you say something about controlling for factors such as being recumbent more time during the day, medication, things like that? Has that been studied?
I mean, we try to get the controls, first of all. Early on, the cerebrospinal fluid controls has normally been patients that have been disclosed as non-patients in the end. They've been collected cerebrospinal fluid from due to something, unexplained headache or something like that. We try to avoid that kind of controls nowadays because we now know that they are not perfect controls. So instead we use clearly healthy individuals that volunteers to do a spinal tap. Medication-wise, always difficult to totally exclude influences of medication. We have very good records in Sweden, so that is helping us to try to avoid bias things. And especially when we do these small cohort tests, we have to be very careful with the inclusion criteria. And then I think also it's good to use contrast patient groups as maybe not controls, but as contrast groups, so we can actually look at differences and also similarities between the different disorders.
Have you or others compared freshly isolated versus frozen cerebrospinal fluid, and do we know whether frozen material will be useful?
Yes, we have actually done quite a lot of that during the years, and the freezing process is very important to consider when you are going for long-time storage of samples. So we are following a very strict protocol when it comes to removing cells, for instance, from the cerebrospinal before freezing, because then when you freeze the sample, you will have lysis of the cells. So that contributes a lot to protein background and so on. And also, if you keep them frozen and not freeze-thaw them until the final analysis, actually they are quite stable in deep freezing, -80 or liquid nitrogen. Fresh sample is, it's unpractical to be able to do fresh sampling all the time. But when we do, for instance, if we have possibility to do ventricle cerebrospinal fluid in patients with a drain tube from the ventricles, then we can also monitor this production of fresh cerebrospinal fluid over time. And we can see that it's fairly stable actually over time. So that's interesting to see. Thank you.
Hello, thank you for the presentation. Exertion changes the symptoms of the patient, but certainly also the metabolomics. So are there ways to control the changing state when you make your sampling, like before and after exertion? So would you think that would be important or possible?
It would be important. It sometimes depends on what sampling we are doing. If we do a less invasive sampling, then definitely. But to do cerebrospinal fluid before and after exertion, it would be super interesting if it would be possible to do. I'm not totally sure how we would do that, though. And also, I mean, it depends on the severity of the patient, of course, what is tolerable. So.
Yes, I'm Janet Flint. I'm a patient with NECFS. Thank you for your presentation. It's not my field, so I didn't capture a whole lot of it, but I appreciate the work that you're doing. I was wondering, there's the machines, the magnetic resonance spectrometers. I don't know if I said it right, but as a patient, being poked and prodded, having an invasive implant in my brain, kind of, I'm squeamish, and I think, can't we do something non-invasive to capture it and move the field forward without all the need for maintaining samples and controls, and maybe even in a dynamic way? Is that like too far afield, or is that within the realm of possibility? Because I know they're doing it with brain tumors. Yeah.
And I think there will be presentations later this meeting actually about imaging, and that's absolutely, as I said initially, fantastic way of monitoring things non-invasively and looking at dynamics also. So I think we will have presentations later during the meeting.
But is it close in the time horizon, or are we looking further out?
It's happening right now, actually.
Okay,
so,
great. Thank you.
Thank you.
Quick question, your targeted proteomics. You mentioned that there were, I think I heard you say there was only 1,200 proteins available on panels today, or something like that. That's really just scratching the surface of all the protein chemistry in the body. Can you make a comment about how relevant are those 1,200? Are we missing, thousands through the analytics and,
If we consider that the whole proteoisoform pattern would maybe reveal there will be 1 million different proteins, right? These 1,200 proteins are very, very carefully selected for specific functions. So it's not the experiment is not to try to monitor all proteins or random proteins as we do with untargeted proteomics. These markers are selected from a very, very specific point of view. So that's why we are using these 1,200 markers. They probably will develop into more panels depending on what the requests are.
So is it safe to say that these are what we believe are the most relevant 1,200 proteins for those different panels?
Yes. So far.
As far as we know today?
Yes, exactly.
All right, thanks.
Okay, thank you.
This is the immunology session. If you don't know where you are, you're in an MECFS science meeting. All right. Our first speaker needs no introduction because it's Jose Montoya, who's been a leader in our field for a long, long time, Stanford University, and he's going to talk about cytokine networks and genetic regulation.
Thank you, Nancy. Thank you, Joe and Vicky, for putting this meeting together. Today, I would like to share some of our data new from last week about estimation of cytokine networks, and then also some of the alleles in the type 1 and type 2 HLA groups that we have found that appear to correlate with ME/CFS per se, but also with severe severity. All of this, I don't have any conflicts of interest to disclose. I think that in terms of ME/CFS research, we are slowly leaving the dark places behind, and now it has become a narrative of an unfolding story of discoveries that I think will result in targeted treatments for what appears to be the theme that appears to be emerging is this chronic incapacitating inflammatory syndrome. It seems like the data from various angles and various groups seem to be pointing in the same direction. This is one of our teams at Stanford. Present here in this meeting are Dr. Keegan Moneghetti, is also Tulia Liep, our research coordinator, Dr. Lily Xu, Jacqueline Penner, who was one of our interns in the summer, and Art Mirin. And we have been able to, from these core teams, to successfully reach out to various specialties and subspecialties from systems, immunology, neuroradiology, all the way to various specialties. And it's very important because specialties, have the tendency to create silos, and originally were based on anatomy, then physiology. Now it's based on tools that we have to interrogate the body. But I think that it's important to decrease our own biases from whatever specialty we come from by obviously integrating all these specialties. So these are the studies that our Stanford CFS group, one of them, is carrying on. We have this case control study where we have approximately 200 patients and 400 healthy controls. The specimens, the blood from these individuals had been already collected for PBMC, serum, plasma, DNA, RNA, and there we are doing immune responses studies that the cytokine work with the network analysis that is completely new will be presented for the first time here. And then we have the HLA. Tulia Liep already presented the herpes infection important point. And then with Ian, we have a paper on the works that we owe him back the next draft. And then with him, we are also doing part of his U54, the exercise and immune profiling that is executed by Keegan and Tulia. And then we have another one with Ron and Mark. There is a validation study. We are very excited about this one because we reported that there was an abnormality in the right arcuate fasciculus, and we are currently, as we speak, in the halfway trying to validate that finding. We are also excited about a study trying to see microglial inflammation with a new marker that was discovered and carried out by our faculty, Dr. Michelle James. So today, we'll focus on cytokines and especially the network analysis. I will dwell few slides on the findings that we already reported, because it's that there is one new way of looking at them that I kind of got excited last week, one early morning, but we'll see. I'll share it with you and see how you react to it. And nothing of this would have been possible without Mark Davis, who created that vision of systems immunology, having a center where we all could look at the immune system as a broad thing. And also his partner in crime is Holden Macker. Marcelo Fernandez from the HLA blood bank. Without him, there is no way we could have done the HLA work. And Dr. Tyson Holmes, who is our statistical director, computational person in the way of statistics, and Don Garber, also our statistical and programmer. So none of this would have been possible without their contributions. So one of the central questions that begs to be asked is really an abnormal immune problem that is either central in the pathogenesis of ME/CFS, or is it one of the main things contributing to the pathogenesis of ME/CFS? And partly coming from the disease itself, the symptoms, the patients often complain of flu-like symptoms. They have lots of inflammatory complaints. And also there is this striking hypersensitivity to even minor stimuli, noise, smells, food, sound, that suggest inflammation. And several papers have pointed that innate and adaptive immune responses are abnormal. And then we have recent studies on cytokines pointing a correlation with disease severity and duration. Surprisingly, the traditional measures of inflammation, sedimentation rate, C-reactive protein, and CRP is nothing more than IL-6 are seldom elevated. And unfortunately, lots of people in medicine have used that argument that these two tests are normal to say that there is no inflammation, and that's really a very short vision of the immune system. And this is something like the efforts at Stanford by Mark and Holden to allow us to look at the immune system beyond just one single measure is allowing to create a different picture. But don't be surprised that many will say that there is no inflammation just because those two tests are normal, and that's far from a good science. So the first set is this study where we have the approximately 200 patients, 400 healthy controls. They were carefully recruited, and everything that was drawn from them was handled the same way. So they come from a very specific geographic location. The blood was drawn from a very specific times of the day. The match was, I would say, perfect in terms of age and sex. And then they went into the study in an intercalated fashion. So it's not that we just recruited the patients one time and the controls from another, or the controls didn't come from the blood bank. They were carefully putting them intertwined so that they would be subject to the same influences, even seasons and weather and days of the week. And then everything from the time that the blood is drawn to be stored, and when the blood is thawed for the assay, to all the way to the performance of the assay was exactly the same. And furthermore, we mix them in the plates so that there will be also very little or no bias in terms of the batches or the plates. So this is what we got. We have cases around 192, 392 controls, and you can see that we were able to successfully do the age and the sex matching. The race was uneven. There were more Caucasians in the cases, but that allowed us to then, in the linear regression analysis, to enter that as a variable. And then we also observed that despite that we used the Fukuda criteria, close to 100% had the unrefreshing sleep and the post-exertional malaise that is part of the SAID criteria. And the vast majority actually did have, in fact, chronic fatigue syndrome. And the first thing is that it was surprising that although we measured 51 cytokines in both groups in almost 600 participants, we found surprisingly only 2 cytokines to be clearly different between the cases and the controls. And one of them was the transforming growth factor beta. TGF-beta is a heavily pleiotropic cytokine that has many impacts in many cells, primarily produced by monocytes, macrophages, and Th17 cells. And fascinatingly, has been found to be elevated in CFS in 5 of 8 studies. So I think that this is one of those things that another aspect of meeting like this is that we need to start to agree on certain findings that we can catalog as like, this is part of the illness. You know, there are things that are difficult to adopt because of the sample size, because the findings are not clear. But I suggest that as part of this meeting's efforts, we start to create like a repository of like, this is what has been found in X study or Y study that appears to be there as part, and then we build from that angle. And TGF-beta also has been found to be key in the promotion and non-Hodgkin's lymphoma. And as we know, CFS patients after a certain age are at risk of non-Hodgkin's lymphoma. So maybe the biological connection between the illness and the lymphoma. We also find the resistance to be low, but more than simply lower is that it has this funny inverted U behavior. The other cytokine that had that behavior that is inverted is U inverted is intercellular adhesion molecule 1, ICAM1. And there is something there that we just don't seem to grasp what it is, but there may be some important feature, biologically speaking, that is telling us that we just don't seem to grasp it at this time. Part of it, you do have biological correlates of this in other areas of medicine. For example, if a patient has hepatitis, and the hepatitis is mild, the liver enzymes will be low. And then when they get more severe, like moderate levels of hepatitis, the liver enzymes go up. But there is a point where if it's too severe, they go down because of pure exhaustion and pure cell death, that they cannot make more. I'm not suggesting that that's what's happening, but what I'm saying is that there are correlates of this funny behavior from mild to severe that happens in medicine. What was striking was that we found this strong correlation between the levels of 17 cytokines and severity. And as you know, already in the x-axis, we have the first group is the controls, mild, moderate, severe CFS, and the mean fluorescent intensity, the signal for the strength of the levels of the cytokines are in the y-axis. And you can see this remarkable trend. And the other thing that makes you kind of pause is that when we average them, then they are the same as the controls. So another thing that I would suggest is that data that we looked at for CFS probably needs to be always looked at by severity, because you may have findings, but they are perhaps disappear by this phenomena thing that we found here, and make us think about, for centuries we have used comparing cases with controls as a tool to identify what is abnormal in a disease, but perhaps certain diseases create a different reality where comparing to controls may not be useful any longer, and that perhaps by adjusting by other things, duration, severity, certain realities or biological aspects of the disease will emerge easily. The other thing that comes across by looking at the association with severity is that of these 17 cytokines, 13 are heavily pro-inflammatory. And many of them are so-called class 1 cytokines that have a 4-helix bundle structure, 3-dimensional. And it's interesting that they share that 3-dimensional homology. But other things that come looking at the cellular origins and the target cells and the immunological functions of these cytokines is that they have innate immunity capacity, adaptive immunity, and some of them, like IL-17, that recruits neutrophils but also is important in T-cell differentiation, appears to be important in crosstalk between the innate and the adaptive. The other aspect that makes us reflect in those 17 cytokines is that they involve Th1, Th2, Th17, So, it would have been neat. It would have been easier if it would have been all Th2 because it would have made sense with the allergies and the easy reaction, that the hypersensitivity that the patients have to symptoms. But no, it did not become as easy as to us. So Th1, Th2, and Th17 are there. The other important finding is that leptin was found, and Jared Younger has found leptin correlating with severity of fatigue in longitudinal studies, so that was a nice additional correlation with that. And leptin has been postulated as a perpetuator of inflammation, so could be leptin one of the things that perpetuates ME/CFS. Also may explain the predominance in females and leptin. And in our group, Tulia Lieb was the one who pointed us to us. Leptin may be one of the reasons patients develop neuroinflammation, since in animal models disrupt the blood-brain barrier and allows inflammation to go to the brain. The TGF-beta finding may be connected to the non-Hodgkin lymphoma in ME/CFS patients. But the other thing that we got excited about, but again, we are presenting and sharing it with you because we don't know if it has relevance or not, but it may, is that out of the 17 cytokines that correlated with severity, 10 can be produced, constitutively produced by or induced by mast cells. And so when that kind of thing came to us, and then went to review this fantastic paper by Steve Galley, who's one of the world authorities in mast cells, and happens to be based at Stanford. And we were able to clearly, like a abacus, like counting one by one, and we were surprised how many of the cytokines we found that appears to be coming from many places seem to be some home connection with mast cells. And those are the 17, and 10 of them clearly are connected to the mast cell. And mast cells have important interactions with microglia, also potentially influencing neuroinflammation. So it's a question: could a central fissure in ME/CFS be a dysregulated mast cell? It's a question. And this is just for me, it was like an eye-opening when I saw mast cells back in medical school and during internal medicine residency. It was mast cells, very few, not much known about it. And I found this from Steve Galley's group again, what they call a highly simplified overview of how these cells have so diverse capacity of responding to different stimuli. So this is what they call highly simplified. And they have, the receptors that are various for different things. They have the ligands in pink. They have the activating pathways in red, the inhibitory pathways in blue, the migration chemokines in purple. And what is important to us is that they have these black arrows with the black boxes where they have the cytokines that are produced by the mast cell, either constitutively or by induction. So it's a question and it's a thought, but it will have major potential therapeutic implications. As a side note from our work with the cytokines, there was a discovery made that there was a glitch in the Luminance assay measuring the cytokine, and our statistical director, Dr. Tyson H. Holmes, who really was the one who discovered this, he was looking at residual data that most people don't pay attention in linear regression analysis, and most people consider inconsequential. He paid attention to that, and he found something really important that needs to always be corrected every time that you have Luminance data. So he and us decided to have made this available for free. It's a novel utility that corrects for plate-associated variations and non-specific bindings. And our hope is that the more rigor we apply to the methods, the better data we'll have that will be hopefully closest to the biology that we are trying to unveil. So next is new. This is what we call cytokine network analysis. So we got all that artifact-corrected data from the cytokines, detrended by age, sex, race. And then the key part is that these are undirected weighted graphs. Undirected because you are not paying attention much to the direction of the information, but more about the amount of information that is flowing between the cytokines. And that amount of information, that mutual information, is a general measure of association between two cytokines. Then Tyson applies what is called maximum relevancy, minimum redundancy algorithm that allow us to see which associations of the cytokines are stronger and more direct between them. That lead us to create what is called a minimum spanning tree. That is the path of fewest and strongest direct connections that connects all cytokines. The analogy that he gave me, which was really cool, is like if you are given the task to go to a town and deliver milk to 51 houses, 51 cytokines, the algorithm will create something that will allow you to go to all the 51 places but with the fewest trips, and then obviously in a more efficient way. So these are the trees that you're going to see for cases, and we decided to show today the severe ones because the time constraints. So we're going to show you how those cytokines 51, and you remember that they correlate with severity, the central backbone, like the skeleton of their connections, and as an approximation for their first order of approximation. So this is how 51 cytokines looks in 392 healthy humans. And you can immediately see that there is a central highway, if you will, and there are certain points where certain cytokines have lots of access to other interesting places. And that appears to be, perhaps, I hope you agree, that one of the ones on the central highway that has most connection is leukemia inhibitory factor, LIF. And this is a cytokine that is fascinating because it has lots of implications in hematopoiesis, but also neuroprotective. Neuroprotective. And you can see, for example, a direct connection with nerve growth factors. So kind of like we may not be far from biology, since it's like when you look at all the organs of the body, the brain is the one that has like a helmet made of the skull, like protecting the brain. Or when Cindy Bateman tells us that patients with OI faint and they drop to the floor, the drop to the floor is a way to get more flow to the brain. It's a defense mechanism. So that's kind of the skull. The fainting is the equivalent of having this LIF cytokine here, centrally located with so many other connections in healthy people. So that is something that becomes obvious. And then if we create heat maps that also looked at how strong is the association of a cytokine with the other ones, it becomes obviously that LIF has this, the more red the dot, the stronger is the connection with the other cytokine, and the more white is lower or weaker. And LIF is here, and obviously this is LIS as well, because it's with itself. So in healthy people, LIF plays a central role in terms of connections with other cytokines and in terms of strong associations. The other cytokines that I hope you will agree when we look at is granulocyte macrophage colony-stimulating factor, GM-CSF. It's important in the differentiation towards granulocytes and macrophages. And transforming growth factor alpha, TGF-alpha, that is key for epithelial biology. And again, makes you think the epithelial cells are placed everywhere in the body where we interact with the outside, and therefore is another perhaps important cytokine that has been developed by evolution to be placed there because of that central important first defense. Now, look at what happened with severe ME/CFS. That LIF goes to a much lower level of prominence, still has the connection with nerve growth factor, but now talking about ME/CFS, possibly inflammatory, possibly affecting the brain. Now that LIF that was supposed to be a fence, I don't want to use the word wall, it's supposed to be a fence to protect the brain, that LIF there suddenly loses importance. And you can see how in healthy controls, the LIF that I showed you earlier, in the heat map has all these connections, and now in the severe, much less mutually shared information. So in summary, by this estimation of cytokine networks, we take LIF from a very central role in healthy people to a much peripheral role, less important role in ME/CFS. GM-CSF shifts like to no connections here when it had all this here. And the epithelial biology implicated cytokine TGF-alpha also migrates to a very peripheral role. So I'm sure that several of you are asking the question, so these are the cytokines that are lost in ME/CFS or shifted, rather, to a much lower central role. I'm sure you are asking what are the ones that now shift in the other direction. Which cytokines in healthy controls go from very peripheral role to a much more central role? And they are IL-5, like you can see here, almost terminal, and suddenly IL-5 in ME/CFS takes a central, the most central aspect in the NU3 for severe disease. And the same thing happens with interferon gamma here, and the same thing happened with MCSF here. So it's like shifting from neuroprotection, epithelial biology, to inflammatory, allergic processes. So what we appear to have learned, and again, this is totally new from last week, so we haven't even sit down to write the manuscript yet, is that in healthy controls, LIF, GM-CSF, TGF-alpha played a big role. And then in severe LIF, IL-5, interferon gamma, MCSF take central roles. So this supports the role of inflammation, and perhaps we plan to do in silico experiments where if we perturb IL-5 down and LIF higher, and you can block ILF with antibodies now, and you can increase LIF now, perhaps you could change the graph. So can in silico give us the candidates for perturbations that could result in helping out the patient? So this is the algorithm that I cannot go into details, but the idea is can we perturb, for example, here IL-5 in the areas that are still safe to change the tree to the ones that now is associated with health. And the last one, and I have, I think, just 1 minute or less, is on HLA. This is done by high-throughput next-generation sequencing. We have 167 patients, and that we will be sharing this information and discussing it with Ron's group. And Marcelo allowed us to compare that with 2,000 plus Caucasians. And the bottom line is after the Hardy-Weinberg equilibrium was fulfilled, we compare cases with controls, and within cases, we did it with severity. And this is the bottom line. We found that DRB4, which is HLA type 2, 0101, increases the risk for ME/CFS. And DRB4 0103, that is only one nucleotide, one amino acid different, decreases the risk of ME/CFS. This is really fascinating that one thing can do such a big difference, but there is precedent for that in medicine. And DRBR4 has been implicated in autoimmune diseases, and you can see the list here. So ME/CFS, again, other a point of information pointing to inflammation. And lastly, we found that the severity was associated with A301 and A3301. And curiously, these two alleles have been associated with cerebral malaria when compared to uncomplicated malaria. And we are found here with severe CFS that have more brain involvement compared to the controls. So I think that we have evidence for cytokines perhaps playing an important role in ME/CFS with potential implications for cytokine-based therapy, and the genetics may be another window that will allow us to see this disease better. Thank you.
Thank you. My name is Lila Rosenthal. I'm a family physician in Colorado. Thank you, Dr. Montoya. We actually have a mutual patient that you take care of. And I'm so pleased you brought up mast cell activation. I'm part of a community of physicians around the country who have really taken a hard look at mast cell activation as an important mechanism in CFSME and are actively treating it, sometimes with drugs as simple as H1 and H2 blockers, sometimes daily or twice daily use of loratadine or, famotidine. I mean, these are really basic, cheap, safe drugs that can really help patients to some degree. And in some cases, mast cell inhibiting drugs like oral cromolyn are also very helpful. I know we're going to hear more from Dr. Levine about it all tomorrow, but I just wanted to let you know that I think that's a vein of research that really needs to be more robust, and I'm really glad your colleague is working on it. So thank you.
Thank you. And yes, it came to us as something that we had not seen before, honestly, until last week. And I just reached out by email. Steve Galley, we'll see if we can excite him to join us. That's still on the way, on the works.
It's wonderful. And I think it's really important to mention, too, because there is so much discussion about how there are no active biomarkers right now to test for CFSME, but mast cell activation disorder syndrome and CFSME are basically concentric circles with a lot of overlap. And there are absolutely biomarkers, both serum, urine, that, if handled properly, often specimens need to be frozen to get an abnormal result. And they're, commercially available and should be in more widespread use. So thank you.
Okay, we are really out of time. Can you make your question like a 2-second question? Yeah.
My question, sure. I just want to say that because Dr. Montoya has been talking about severity, and thank you for the work for the talk. In our study, some of the very severe CFS people never go to a clinic because their circadian rhythm is so affected that they cannot wake up sooner than 3 to 8 p.m. because your participants have been giving blood around early morning. I was just wondering that could you kindly explain more about the severity definition in your study?
Severity came from the MFI-20. So it's a questionnaire for severity that gave us that. We regret to not have had access to those very severely ill patients. I feel bad about it. There was no funding back then to do it. Now we have corrected that, and in every of the 7 studies we have a provision for funds where ambulances go to the house. Tulia Lieb often goes to the patients' houses. So I feel bad about it, but we have responded to that important methodological point. Thank you.
Thank you.
Well, that was an excellent talk. Thank you very much, Jose. That's fantastic. Our next speaker is Mark Davis, also from Stanford. He's speaking on the potentially important T-cell activity in ME/CFS.
So I'm also very grateful to Joe Bream and NIH for sponsoring this meeting. It's a really timely meeting, and I think the meetings like this haven't been common enough and help to mobilize people and get them thinking and interacting in very useful ways. Now, I came to this area in a kind of unusual way, which is that we've been very concerned with the lack of useful tools, precise tools in human immunology, and taken on a mission that Jose mentioned in terms of our overall effort at Stanford, but specifically develop tools to understand T cells and other kinds of cells that are important in immune system in both health and disease. And one of the really useful tools that we developed, and it'll become clear why it's useful, is a few years ago a really nice single cell T cell method that could produce T cell receptor sequences. And for those who don't know, a T cell receptor is like an antibody-like molecule on T cells. So it has a vast amount of sequence diversity that it gets by rearranging V and D and J regions, just like antibodies. And then this is what's on the surface of T cells and allows them to distinguish self from non-self antigens. And This method Arnold Hahn developed is really very efficient way. You can just have a few T cells and you'll get these sequences, and you can tell things like, are they clonally expanded? Now, one of the primary features of a lymphocyte response is that you create this vast amount of diversity through this gene rearrangement method, and in general, each cell expresses a different receptor, and you're just expressing every possible receptor. And then if the right antigen comes along, it can trigger those cells. And then the particular cells that have a specificity for that virus or whatever it was will divide and create many more daughter cells that have exactly the same sequence. So just looking at that, those expansions, those what we call clonal expansions in immunology, tells you something about what cells got most excited about this particular thing. And if it happens to be a viral infection, then they're going to be most excited about viral antigens that have been coming in. In autoimmune diseases, there's a downside, which is they're going to be excited about self-antigens, which is not what they're supposed to, but that's because of a problem with regulation. And that's, I go back to this title here, the subtitle, which is this an autoimmune disease? Because actually, what Jose just told you in terms of this correlation with inflammatory cytokines, and also a correlation with particular class 2 HLA molecules, this is a hallmark of autoimmune diseases. And typically, ME/CFS is not thought of as an autoimmune disease because there's some other, there just hasn't been that much work in it. But this has been what it increasingly looks like to us, and I'll take you through our data in terms of how what suggests that. So let me just tell you that this is we have this methodology and created a whole series of methodologies with our colleagues at Stanford to explore the immune system of human beings in much greater detail than was previously possible. And one of the funny phenomena, and as mentioned earlier, curiosity. I mean, this is, again, sort of the PhD world is that we see things that we don't understand, and we try to do experiments to understand them. So another great idea Arnold had was to look at celiac disease. And celiac disease is the only autoimmune disease where we have a very sure knowledge of what the antigen is. Namely, it's gluten. And so if you go on a gluten-free diet, generally, although not always, you can cure the disease and everyone's happy, mostly. But it's also, you can do studies with gluten. You can ask celiacs on a gluten-free diet to take gluten as part of an experimental study, and that's what we did. And like other studies have shown that 6 days later after consuming gluten, we could see gluten-specific CD4 T cells in the blood of these patients. It's kind of like there's a local response, and then cells divide, and then on the 6th or 7th day, they come out into the blood, and you can examine them in great detail, and they're generally enriched for specificity. And so that's all well and good. That's what happened here in the CD4 category. But what was surprising and piqued our curiosity completely was that we also saw CD8 cells and gamma delta T cells. And these are other flavors of T cells that do quite different things than CD4 T cells. Particularly CD8 cells are famous for killing virally infected cells. Gamma delta cells are a bit of a mystery in the immune system. But anyway, this whole panoply of different T cells coming out with the gluten was completely surprising and not on anyone's radar screen in terms of this autoimmune disease. And so we thought, well, is this something that people have missed in other autoimmune diseases? And the easiest thing to do here was to look at one of the several mouse models of autoimmune disease, and this is one called EAE, where you induce disease with a particular myelin protein called MOG and some complete Freund's adjuvant and other terrible things to stimulate an autoreactive response. And sure enough, around day 10 or so, these mice develop a demyelinating disease. And this has been a very popular model for multiple sclerosis for many years now, decades, in fact. So long story short is we saw exactly the same thing in EAE, which is that we saw a spike of CD4 cells together with a spike in CD8 cells together with a spike of gamma delta cells. And then as a special bonus, we saw a week later, we saw a spike of exactly that same trio of cells. So this says that that this is something much more general than just a peculiarity of celiac disease. But there was more to the story, and that came about when we employed this single-cell T-cell receptor characterization method, and we could sure enough see clonal expansion in the blood and in the central nervous system with CD4 cells, and also especially CD8 cells and also gamma delta cells, that not showing here. So that's good, and that told us these are the cells to look at. These are the ones that are the most active in the disease, and we should follow up on asking what do they actually do and what do they recognize. And these have been some of the central mysteries of autoimmunity and a lot of things associated with human immunology. So long story short is, I should say, neuricosaligrama, the picture I showed before, is that one really did most of this work. And basically, if we transplant the T-cell receptors that we derive from these sequences into reporter cells, we can see that all the expanded CD4 cells that we analyze all recognize the MOG peptide, which is fine. That's how you induce the disease. It makes sense that the pathogenic T cells are that, as other people have talked about as well in this model. But what was interesting was that the CD8 cells, also very expanded, didn't recognize MOG. None of them did. These are controls over here. And not only didn't they recognize MOG, they didn't recognize any other myelin proteins. And this is strange because in viral responses, the CD4 cells and the CD8 cells recognize the same molecules, and definitely molecules from the same virus, because they have to work together to kill the viruses. So this was something pretty much off the track. And so long story short is we isolated peptides from that stimulated these CD8 cells, and we put them in with the MOG peptide mix that induces the disease, expecting we're going to stimulate CD8 cells. They're going to make the disease worse because they're going to be cooperating with the CD4 cells to kill myelin cells and cause this sort of demyelinating disease phenotype. But in fact, what happened was that we cured the disease, and 7 of 10 mice had no disease whatsoever, and 3 of the 10 had a very mild form. This is the clinical score here, and if you just do the regular thing, you get 10 out of 10 mice that have a pretty severe clinical disease. But this is what happens when we put in these CD8 peptides. So that's something. Or really what it says is that we're seeing something very different than what we see in an infectious disease response, which is we're seeing that the clonally expanded CD8 T cells in this mouse model actually suppress the disease. And could this be true in human autoimmune diseases? And if it is, then finding the ligands for those CD8 cells in autoimmune disease might be a drug. So we've been hot on the trail here in MS, and particularly collaborating with a group at UCSF that has a really nice study of MS patients, and particularly was able to get us almost 20 patients of recent onset that had not been treated. There are many immune modulatory drugs for MS, and these are just people just coming into clinic, so we didn't have to worry about the effects of those drugs. And what was remarkable is that compared to healthy controls, which sometimes show a bit of clonal expansion, but other times don't, we could see almost every MS patient had a massive CD8 clonal expansion in their in the activated blood cells. So that suggests there could be those same things going on in this major human autoimmune disease. But you're asking, this is a symposium on ME/CFS. Where's that? Where's the beef? But this is just the introduction to get you warmed up to thinking T cells might be really important. But are they? Are they really? Most people haven't paid any attention to T cells in this disease. So this is where the accident hallway conversation between my graduate student, Jacob Glanville, and Dr. Montoya, who you just heard from. And Dr. Montoya had a lot of T cell receptor sequences from both patients and controls that he was looking for someone to tell him something about, because it's not really obvious a lot of times what you can do with a whole bunch of T cell receptor sequences, especially just from one half of the receptor, the beta chain. And Jake, being ever optimistic, took this on as a kind of side project, and sort of immediately found that there were a lot of similar T cell receptor sequences in the patients, but not in the controls. And he came to me and said, oh, this is a project. We got to find now some single cells. And so that's what we've been doing. And we particularly went back to that cohort. We could see that a bunch of them had the most prominent, most common class 1 MHC that went along with these shared sequences. And so we collected half a dozen people and started to work on their T cell receptors. And in fact, we could tell that all of them had clonal expansions of the CD8 cells. We've subsequently seen some clonal expansions in healthy controls, and we're trying to figure out what that means. But still, this was quite striking and encouraged us to move on and take the now pairs of expanded T cell receptors and do something with them. But what can you do with them? Well, so this is another segue here where Jacob, in his day job, actually did something very remarkable in the world of T cell receptor sequences, which is he figured out some basic rules for clustering T cell receptors that could predict specificity. And a long story short is that by sequencing T cells brought in with a particular specificity, he could find common sequences and sequence motifs that turned out to be, in structures, turned out to be the contact points between the T cell receptor and the peptide in the groove of the MHC. I'm sorry I didn't show you an overall picture of a T cell receptor. This is the business end of a T cell receptor, and this is its ligand, which is a peptide in these curlicues here, which is the tops of the MHC or HLA molecules. But anyway, these were conserved because they were the contact points. That's always more conserved in a protein-protein interaction. But the important thing was that he was able to use this data to develop an algorithm called Glyph, and that this algorithm is a way to scan through thousands of T cell receptor sequences and to find ones that share specificity. And why is this important? Well, the sequence diversity of T cell receptors is so vast that even identical twins share almost none of their sequences exactly, but yet they share a lot of specificities. And so what's biologically interesting and important in any disease is what is the actual specificity versus, yes, there are 1,000 different sequences that can have this same specificity, but really it's much more important to find specificities. So this is what we're able to do. And the proof of the pudding of this algorithm was the fact that we could take almost 6,000 sequences in a TB study that were TB-specific, we thought, CD4 T cells in latently infected people in a South African cohort, and that we could see many dozens of glyph groups, the specificity groups, and particularly the ones that were most popular are these 5 here that were shared by 4 or more people. And we could immediately see that they tended to share a particular class 2 MHC allele, which is important because it enables you to understand, okay, what the likely MHC allele is, and that's important for all the efforts to find what specificity is. And indeed, it helped us to find the specificities quickly, and we could find all 5 of these specificities. They all recognize a different TB peptide in a different class 2 MHC. So that says the algorithm is actually quite accurate at predicting specificity groups and organizing sequences that are otherwise almost impossible to organize coherently. And so these are some of the sequences, groups that have come out now of these patients that share the A2 allele. And this just gives you a flavor for the different specificity groups. And highlighted are the central parts, the motif parts that are shared, and what we imagine to be the contact points. And so what do you do now? Well, you now can use this great methodology developed by Chris Garcia downstairs at Stanford, who has been able to engineer particular MHC molecules onto yeast, and then to put as many as a billion different peptides into that one MHC molecule, such that each yeast is making a different peptide, and then you can screen that yeast library with particular T cell receptors in a multimeric form, and on a good day come up with a peptide. And that's what we did. Unfortunately, we made 10 different T cell receptor pairs to screen. This work of Santosh Kumar, who was a postdoc in the lab, and we only got one hit that came out. This one here, and this is the result of multiple rounds of selection. But anyway, that's what happened. We have this one peptide, and now let's look at this peptide. Well, the same peptide came out of different libraries, but long and short of it is that by making reporter cells of this T cell receptor, we're able to see and making peptides that were similar to library peptides. We could find a hit in this peptide from this molecule FGF2, and another hit actually here, FBRS, and other ones are somewhat shaky, but there's no obvious neurological or immunological connection here with these two major hits, but anyway, we went with them further. But what was particularly interesting was, did any of these look similar to pathogenic peptides? And indeed, we did find not only similar sequences, but activation pattern is shown here. These are good activators here, very robust. And 2 of them were from mycobacteria. Another one was from Citrobacter. And then there's this other one, lupinus, whatever that is, so lupin. A fish, maybe, forget. So anyway, there's cross-reactivity, which is actually not too hard to find if you start with a peptide sequence, look for other things in the databases for other. So this was very promising that we could see both the self-reactivity and a potential pathogen, although how often people might be infected with these mycobacteria, we don't know, but maybe there was unknown one that is common here. And so then we went to this other methodology that we actually developed quite a few years ago called peptide MHC tetramers, which is basically a trick for multimerizing a particular peptide MHC and then staining T cells with it, because the affinity is very low. You can't do this with monomers typically. You need a multimeric form. Again, a long story short is that in 10 patients from Jose's cohort, we only found one that had significant T cell staining with this reagent. That was very disappointing. It might be important for this one person, but it's so rare it would be hard to imagine this is the real deal. But there's still hope, because we do see in the tetramer positive cells from 3 of the patients, including the one I just showed you, we have seen some sequences that are similar, and so there's something to pursue there. It's not a home run in terms of saying that, okay, this is something common to many many patients because it isn't. So that's encouraged us to really start up again with actually now a more diverse cohort. And these are patients that have come in into Ron Davis's program, and particularly Julie Wilhelmi, who's a technician that's with both Ron and myself. We've got a whole new cohort of people, 21 diagnosed patients and 17 healthy controls. And now again, we have sequenced now over 10,000 T-cell receptor sequences. We're just now, I'm told, today or tomorrow, we will get HLA typing on all those people, and we'll be able to start up again looking for motifs. And we've done some preliminary work, and we do see some new motifs, and so that'll be the basis of things. These are some of the clonal expansions. But as I say, we also see clonal expansions now in some of these healthy controls, which is puzzling compared to our other experience. But we'll work through that, and we do see sequence motifs that are coming up in the patients that are not coming up in the healthy controls. So at least that's encouraging that we can get back on track in terms of tracking down particular specificities and using the tools that I've mentioned. And this is just a summary of those tools, where basically we can go from single T cells in any situation to sequences, sequence pairs, which is critical for reconstructing a specificity, to analyzing thousands of sequences, or actually millions of sequences now, with a more advanced version of the glyph algorithm, look for shared specificities, and then go after what those specificities are, either with reporter cells, as I mentioned, or these libraries. And we've talked about some of those things in some of these papers in general, although most of this data is not published. So future directions, as I say, we have now a whole new cohort and a whole new set of sequences to work with, and to get more, obviously to get more peptide hits, maybe more MACs than just A2. Also really interested in whether with longitudinal studies, can we correlate some of these T-cell activities with ups and downs of people's clinical experience. And talking to you, Jared, in terms of how this might work. We also would like to look at CD4 cells, because we're now thinking that these CD8 cells might be suppressive, which should be good in terms of possible therapies. But we also, what is the causative T cell? And that's probably in the CD4 neighborhood, as it is in most autoimmune diseases, especially those that are linked to a particular class 2 MHC, or HLA, which describes most people. And we could also get clues from some of the antibody work. We've also started a collaboration with Myalgic, which can survey 5,000 analytes, and they've agreed to look at Jose's patients for a very nominal amount of money. So that's very, very nice of them. And of course, none of this would be possible without a lot of very talented postdocs, students and technicians. And I mentioned Santosh. I didn't mention so much Vamsi, the current postdoc. He's really doing great stuff on this. Huang and Jacob are doing mostly the TB work. But Jacob, as you say, he moonlighted with Jose to get us started in this ME/CFS field. I mentioned Arnold Hahn, Julie, Narisha Salagrama, and some other folks in the lab, and critical collaborators like Jose and Ron, and in the MS study, Jorge Oxenberg and Stephen Hauser, and Chris Garcia has also been huge. And we had a lot of support from agencies, including the Open Medicine Foundation, Linda. And I wanted to close with something completely unusual that I just added, because this is a line out of Africa that struck me. Like all quacks, I had many patients. And this is a warning to the patients here that what you're hearing here is real science by serious people trying to figure this out. There are other people in the universe who will sell you solutions, what they will tell you are solutions, but they don't actually know. And in situations where there is no good medical advice or treatments, there's a natural tendency to seek those people out. Hence this comment. So I just leave you with this because maybe it'll be helpful. Okay, and I'll stop there. Thank you. I don't know what to do.
His time's up, or we still got until it's 5 minutes for questions? They're up, yeah, sorry.
Okay.
So, anyway, that was fantastic.
All right, thank you.
My goodness. Fantastic. What a lot of work. You're out of time for questions, but there is a question and answer period at the end of the day, so save your questions for that. Our next speaker is Daria Benutmas, who's from Jackson Labs. He's one of the directors of one of the new centers. And we're looking forward to hear him talk about the immunologic perspectives that he's bringing to our knowledge of this disease.
I also like to thank Joe Breen and other organizers. This is a very important meeting. Great pleasure and honor to be here. I guess my slides are about to come out. Okay, so I'm a human immunologist, so I'm going to focus on immunology and tell you some of our unpublished results. So our overall hypothesis is that the immune system is at the center of what causes or maybe results in ME/CFS symptoms. And that perturbation in the immune system could be due to a variety of reasons, such as disruption in the microbiome that I'm going to mention, and you heard about the metabolism, and of course, infections, viral or bacteria could trigger that. I'm also directing one of the collaborative research centers for ME/CFS at Jackson Laboratory. This is an NIH-funded application, and in that project, what we're trying to do is take a systems biology approach using clinical samples, doing very extensive immune profiling, metabolomics, and microbiome, and try to come up with computational approaches to make sense out of that. The data that I'm going to show you today actually are from a different cohort that I've started a couple of years ago. That was a more cross-sectional study that we completed at least the first set of analysis, and this is still ongoing. We have this is a longitudinal study, and we're still collecting patient samples for that. And our goal is twofold. One is to identify specific biomarkers that can define ME/CFS, and actually more importantly, I'm going to stress at the end, is to be able to stratify the patients because we think this is a very, very heterogeneous disease. And of course, hopefully that will lead us to novel targets that we can use to develop some new therapeutics. So why immune system? Why this is really important? As most of you know, we really need our immune system to defend against infectious diseases and resolve the inflammation that results from that. That's the good part. And as you just heard, there's also the bad part of the immune system that can result in autoimmunity, allergies, and overreaction of the immune system to infectious disease causes septic shock, causes great suffering and mortality. And there's also an ugly side of the immune system that we don't always think too much, but that is something that we think is extremely important, which is a result of chronic inflammation. It's sort of a subtle type of inflammation that happens, which creates chronic illnesses. And we think that this is really important in biomedicine in general, that this inflammation and immune response perturbation can trigger or contribute to a variety of chronic diseases, including Alzheimer's, cancer, cardiovascular disease, and so on, and perhaps also is involved in ME/CFS in a different manner. Of course, there are different flavors of inflammation, and that's something that we are trying to figure out. So as I said, I'm a human immunologist, and I've been studying a particular subset of T cells that you just heard about from one of the leaders in the field called T cells. And you can imagine T cells as sort of the, let's say, the generals or the regulators of the immune system. And there are many, many types of T cells because there are many types of pathogens and parasites, bacteria, viruses. And for each particular type of pathogen, you need to develop a certain type of immune response. And not only that, you have to regulate this. And we have identified at least one subset of cell called regulatory T cells. There's critically important. If you don't regulate these immune responses, you get autoimmunity and all these overreactions during inflammation. And then you have these subset of cells. You can divide them into conventional and unconventional T cells. We heard about the conventional T cells that basically recognize MHC peptide molecules in the context of MHC molecules. But then you have these unconventional T cells, a little bit less studied, that recognize small molecules. This is a particular cell type I'm going to mention called mucosa-associated invariant T cells that recognize metabolites derived from a riboflavin pathway actually produced by bacteria in the context of a molecule called MR1. Another type of cell called natural killer T cells recognize glycolipids and so on and so forth. But the complexity does not stop there. There are also many flavors of these cell types. Not only we can divide them based on the type of cytokines that they produce, effective functions, but also where they go in the body. And that is mapped by a set of molecules called chemokine receptors or integrins, such as CCR6, CCR4. One of the problems in immunology, there are so many different names and jargon. I know it's difficult to recall these things, but basically think of them as sort of zip codes. For example, cells that have CCR6 tend to go to the gut or skin, or if they have CCR4, they might go to lungs. And of course, having the right immune response in the right location is also critically important. And you have cells that make different types of cytokines, combinatorial effects, and so on. And we're still trying to figure out what is this functional diversity. There's probably dozens of different types of T cells that we haven't yet identified. So there's another set of complexity, and that is the microbes within us. There are trillions of bacteria that live in us, especially in our gut, in our skin, in our mucosal tissues, that really shapes our immune system and our biology in general. And in fact, this microbiome, what we call the microbiota, is extremely diverse. There are different types of phyla and species, and each person has a different set of strains that are sort of unique to them. That also can be dynamic, that changes by different conditions, such as your diet, antibiotic use, and so on. But we are really beginning to appreciate that this is extraordinarily important. And if there is a perturbation in this equilibrium that is set by these microbes, that could result in inflammation and autoimmunity and variety of problems. And this could happen by many reasons. Going to McDonald's is probably not a good idea. Use of high level of antibiotics and so on results in this microbial imbalance that we call dysbiosis. That results in many types of chronic illnesses, and perhaps we think also ME/CFS. And you'll hear more about this tomorrow from Julio from Jackson Laboratory, part of our group who studies the microbes. So this is all great, but as late Richard Feynman, the famous physicist, said, it doesn't matter how beautiful your theory is, it doesn't matter how smart you are, if it doesn't agree with the experiment, it's wrong. So let's see what the experiments and the data tell us. So first of all, I want to tell you how we study the immune system and sort of put a context into the data that I'm going to show you. The key instrument or the approach that we take is profiling the immune cells and their functionality using a machine called flow cytometry. And basically what we do is we label the cells with different antibodies that are conjugated to different fluorochore molecules, and you can identify specific subpopulations using this approach. There are lasers that can detect these fluorescent molecules, and you get this decoded in a computer program, and that will show you different sets of data. An example of this, here shown, we can detect T cells in the blood. This is detected by a marker called CD3. And then you can say, okay, what's the complexity within the T cells? Now we can do 15, 20, even 30 different colors in a single tube. You can see, they're made up of CD4, CD8 positive T cells, and we heard about this again. There are double negatives, and then you can go in even deeper and say what's within CD4 cells. We can divide them based on their these markers that define them as naive cells, as memory cells, as effector cells. Naive cells are the ones that haven't seen their antigen. As they see their antigen, they become activated in effector, and the memory cells are long-lived. That's the basis of vaccines and our memory to infectious diseases. And the same is true for CD8 and CD4 cells. And of course, you can go deeper and deeper and look at their functionality, that I'm going to show some of that as well. Okay, so using this, we've actually performed this very detailed immune analysis, and I'm going to only be able to show, based on the time that I have, very small snapshot from in collaboration with Cindy Bateman here from Utah. Close to 200 ME/CFS patients and about close to 100 healthy controls. Of course, most of them are female, and most have long duration of disease. This is a cross-sectional study. As I had mentioned, the new study that we're performing is a longitudinal study, and we're actually focusing more on the people with shorter term of illness. And so it'll be very interesting to compare those results as well. And now we have also built-in metabolomics and microbiome on top of that. Okay, so what happens in ME/CFS patients? So we've started looking at the T cell populations from the very high level. What's the proportion of the T cells, CD4, CD8, and to be honest, I wasn't really expecting anything particular there because these are very high level analysis, but to our surprise, we actually saw differences even in CD4 and CD8 populations. The frequency of CD4 T cells were higher and the CD8 cells were lower. And of course, this is actually most T cells are made up of CD4 or CD8. So if one goes down, one goes up. And if you make a ratio, sorry, got to go back. Then the ratio, of course, is also higher for CD4, CD8 in ME/CFS patients. So this was very interesting, especially the CD8 population looking lower. So then we said, maybe there's some correlation with age, because we know with age these populations change, and when we look at healthy subjects, in fact, we find that during age, as you get older, these proportions change, and there's also the proportions of CD4 to CD8 also are changing. So I said, okay, maybe this was a kind of superfluous data, but let's look at this more carefully. So we divided the patients right in the middle, sort of right at the 50 age, and looked at those who are older than 50 years old and those who are under 50 years old. And there things start to get pretty interesting. And in fact, anyone who was over the age of 50, we couldn't really see at least significance between the healthy controls who were also over the age of 50. But the under the age of 50, we found that both CD4 and CD8 ratio. So the significance was actually coming from this younger cohort, and the same was true also for the ratios as well. So for those that were younger than 50 years old, the CD4, CD8 ratio was actually changing compared to the healthy controls. And then we went a little bit deeper and asked, so what's the level of memory, naive, and so on. There was no difference in the CD4 memory populations between the controls, but again, within the CD8, there was actually a quite high, significantly increased memory subset. So what does this mean? So basically, if the CD8 cells, which recognize viral epitopes mostly, are activated, they will turn into memory and effector cells. So that could perhaps suggest that, at least in some of the patients, remember this is a heterogeneous condition, that this could be a sort of a viral trigger that resulted in this high level of CD8 activation. And when we looked at the age, again, over in 50 age groups, no difference in CD4 memory, but in the CD8 group, lower than age 50, we find that the memory population was increased. One thing that's a little bit striking is that if you look at the over 50, it starts to look like the under the 50 ME patients, even the healthy controls. So that suggests that perhaps there's an accelerated differentiation or accelerated aging of the immune system in these patients, and that difference starts to get lost as you get older. This is something that we've observed in HIV patients in a reverse manner in some cases, that there is this accelerated aging, quote unquote, in their immune system due to the chronic inflammatory responses. So that was very, very interesting. So another subset of cells that we were very interested to study is called Th17 cells. You heard a little bit about this. These cells make IL-17, and IL-17 is a very important cytokine involved in many different functions. I don't have time to go over most of these things, but they can cause inflammation. It could cause damage or regulation of the immune cells and other epithelial cells and osteoblasts and so on and so forth. In fact, there was a report that IL-17 is even involved in pain in certain contexts. But more importantly, Th17 cells are also very much influenced by the microbiota and the bacteria that live in the gut. They probably regulate the microbiome, and the microbiome regulates these Th17 cells. So based on our hypothesis, we wanted to study this, and this is a population we studied for many years in other contexts, and so we were keen to see what happens in ME/CFS patients. And so to do this analysis is a little bit different than looking at just surface phenotypes. So in order to identify Th17 cells, you have to actually elicit the cytokine they produce called IL-17. So you have to stimulate them with something like PMA and ionomycin, and then you have to stain them intracellularly using antibodies. You have to permeabilize the cell that goes inside the cell and stain these cytokines, IL-17, interferon gamma, IL-22, and so on, so that really truly identifies those that make IL-17. But there's another way to identify sort of cells that has the propensity to become Th17, and that is the molecule called CCR6. This is one of the chemokine receptors that are expressed by these cells. In fact, when you do this type of experiment, you find that almost all IL-17 expression is in CCR6 positive cells. The CCR6 negative cells have negligible amounts, and then you can see that there are different subset of Th17, those that make interferon gamma, that don't make interferon gamma, and so on. And then there's a portion of cells that don't seem to be making much. We think that these are sort of reserve or poised cells that could potentially make IL-17. So doing this analysis, we've, again, showing a snapshot of these data. We looked at the ME/CFS patients, and we've found that there was really a profound increase in the proportion of the CCR6 positive memory cells. So remember that this is where all the Th17 cells, and we said, wow, the Th17 cells are greatly increased in these patients. But when we look at the cytokines produced by these cells, we actually found exactly the opposite, that the IL-17 levels from these cells were greatly reduced. And I have to say that I've been studying this population for many years, and this was probably one of the most profound data that we have seen, such a big difference, perhaps because of the large cohort. But what does this mean? Why there are high CCR6 positive and low IL-17? Now, it could be this doesn't necessarily mean there are less Th17 cells. It could also be that they are hyperstimulated and sort of, quote unquote, exhausted cells that they don't want to make any more IL-17. These are very dangerous cells, and maybe they're being told to shut up and not make more IL-17. But clearly it shows that there's something going on, that something is triggering this population, whether it's the microbiota or bacteria or something else. We don't yet know that answer. And again, when we looked at the age group, this time we saw this disruption. It didn't matter whether you were under the age of 50 or over the age of 50. There was still a lower levels of IL-17 producing T cells in the blood of these individuals. Okay, and the last set of data I want to show you is another subset of cells that we call mucosa-associated invariant T cells, or MATE cells. So you'll hear more about this tomorrow from Julia O's a collaboration that we've done with her, and that's mostly published data. So what is unique about these cells is that, as I mentioned earlier, they're unconventional T cells. They don't recognize MHC class 1 or class 2 peptides, but instead they recognize bacterial metabolites. Their function is poorly understood, but they are very cytotoxic. They can kill cells that are infected with bacteria. They produce pro-inflammatory cytokines. And we think that they are very important in regulating the microbiota, that they are sort of sensors of the microbiome. And the study that we have done with Julia actually provides very good evidence for that. And as I said, they recognize these bacterial products. This is actually vitamin B2 metabolized derived from vitamin B2 pathway that binds to this molecule MR1. And what is also unique about them is that their T-cell receptor is invariant in the sense that their alpha chain is the same. They all have V alpha 7.2 in humans. It's a little different in mouse. But the beta can be diverse, but they still seem to recognize the same type of molecules. Another thing that identifies them is this molecule called CD161. So if you actually join these two together, you can very clearly identify this population. Or you can use, as Mark Davis showed, a tetramer approach. You can make a MR1 tetramer with these bacterial metabolites, and you can stain them, and it's exactly the same population that you will stain. So doing this, we first looked at the frequency of these cells in patients versus control. And there was no difference. But this is actually not surprising because you can see that even in healthy control, this is probably the most diverse, divergent T-cell population that we have seen. There's almost 50-fold difference between donor to donor. There are some people who have about 45% of their CD8 T-cells made up of this one population. There are others about 1.5%. I'm probably right here. I know I have about 3.4% of made cells. But what is unique is that that proportion remains the same. So if you have high levels of made cells, that actually sustains itself for a while. We don't know the reason for this. It could be because everyone's microbiota is different. So this person might have a very different type of microbes that they need a lot of made cells there. Again, this is a speculation that we don't have direct proof for that. But when we looked at the actual activation, or if you like, differentiation of these cells between patients and healthy, and there we saw quite big differences. So we've looked at made cells that lack this molecule called CD27. It's not really that important what it is, but it basically cells that are more activated, more differentiated, will lose this molecule CD27, and that proportion of cells were increased in ME/CFS patients very significantly. And furthermore, the functionality of these cells appear to be highly perturbed as well, that the proportion of these, so by the way, what is unique about made cells, they can also make IL-17. That's very unique because they're mostly CD8 cells. The proportion of them that make IL-17 interferon gamma were again greatly reduced, very similar to what we saw with Th17 population. And in fact, the proportion of total interferon gamma producing cells were also reduced. Again, this could suggest that maybe they were hyperstimulated. It's, again, something that's really bothering them, and they don't want to make any more cytokines, perhaps. Again, this is speculating here, but that's at least our interpretation. This could very much link it to the microbiome. So our hypothesis, again, that really supports by these data, that something is really going on at the gut level. The CD8 data could be very different. Perhaps that's more of a viral origin, but maybe that there's something going on in the gut and the microbiota, and that's really causing this irritation of the Th17 made cells. Whether these are directly linked to the symptoms of the disease remains to be determined, but clearly there are some very profound changes in these populations. And again, Th17 cells are involved in autoimmunity as well as made cells, and perhaps this could suggest some sort of an autoimmune type of a T-cell response in these patients as well. So the last slide that I want to show is that I'm very much passionate about what we call personalized medicine. What is personalized medicine and what is precision medicine? There's actually a big initiative in HIV. This was really described by Hippocrates more than 2,000 years ago. It is far more important to know which person has the disease than what disease the person has. I was trained as a physician in medical school. We were taught to treat the disease, diabetes, cancer, cardiovascular, so on. But now we really appreciate that one size does not fit all in medicine. And you really need to stratify and really go down to the precision level. And not to mention such a heterogeneous disease such as ME/CFS, cancer has been leading this in stratifying the groups based on molecular markers, and now you can really target the type of lung cancer that you can target with particular drug will not work in another type of lung cancer, and so on and so forth. And we think that this is actually important probably in all diseases except a single gene cause rare diseases. And again, we think that there's probably multiple triggers or multiple factors that result in similar type of symptoms in ME/CFS, and we really need to identify and tailor the diagnosis to individual person, and as well as tailor the treatment accordingly. And finally, I want to acknowledge none of this could be possible without the support of NIH. All the data that I showed you are from an R01 grant that we got from NIAID. And as I mentioned, our studies on the U54 grant from NINDS is ongoing, and we'll start soon analyzing some of those data. And of course, Jackson Laboratory has been great support in our efforts here. I want to acknowledge my team. Some people are not here. Courtney Gunter and Stephanie Ranzula are here. They've done great work in analyzing data. AJ Karhan, Lina Kosaya. All of them contributed to this work, and you will hear from Julia tomorrow. They're very happy, as you can see here. They are doing our microbiome collaboration and doing really fantastic work. And of course, none of this would be possible without the patients that were extremely carefully chosen by Cindy Bateman and Susan Vernon at Bateman Horn Center. We're really grateful to have such great clinical collaborators. And I'd like to point out that we have a blog called jacksmecfs.com. You can follow us on Twitter. And Jackson Laboratory actually launched a very nice series of videos and articles about ME/CFS research that you can start to read some of that or watch it from this link. And as I mentioned, Courtney Gunter is also our program manager. So I'll stop there.
Really good. Unfortunately, I think we ran out of the question time, but we do have questions at the end of the day, so hang out. There's a whole period of time for question and answers at the end of the day. So that was really, these are great lectures. I hope you guys are enjoying it as much as I am. So our next speaker is Maureen Hansen, and she's talking about cellular metabolism of immune cells. Is that her topic?
This is the group in my lab that works on ME/CFS. All of them are here except for one. And this work that you're going to hear about was funded not by our Collaborative Research Center grant, but actually by an earlier NIH R21 grant that we had. It was also funded by Cimarron Research, and we collaborated with Dan Peterson's group. His group is also here. And yesterday, one of my lab members, Alex Mandarano, gave a talk at the Young Investigators meeting in which he described a project that is a collaborative research project with the Columbia Center and with the Jackson Lab Center. And this is not the project that's going to be given today, but Alex's work on this project that's the subject of this talk was actually also funded by a private donor who I hope is listening, who gave Alex the gift of time, and that she was able to work full-time on this project as a result of this private funding. And since Alex is here, after having been speaking at the Young Investigators meeting, I decided it was inappropriate for me to give the talk. And I'm going to actually invite Alex to give the talk that she put together, and she will describe the work that she's been doing on this topic.
Okay. So, as we've been hearing throughout this session, and I think all of you are well aware, there's been a lot of research to try to understand how the immune system plays a role in ME/CFS. And we have a lot of evidence to suggest that the immune system is dysfunctional in this disease. But there's also been a lot of research lately and a lot of interest in how metabolism plays a role in ME/CFS, especially with metabolomic studies, which have shown us that there are many metabolites that are differentially abundant between patients and healthy controls. And what I'm really interested in for my work is the interface of these two areas of research, which is known as immunometabolism. So immunometabolism is based on the idea that immune cells, like any other cell in the body, rely on metabolism for their function. But immune cells also rely on the nutrients that are available to them, receptor signaling, oxygen availability, and cytokine signaling to drive that metabolism. And what's unique about immune cells is that they have to cope with all these different environments in the body, like hypoxic inflamed tissue or a tumor microenvironment, and then adjust their metabolism accordingly. And in addition, when immune cells are activated and they have to proliferate, they have to increase specific metabolic pathways to drive that proliferation and then to allow them to have these specialized functions when they differentiate into effector cells. So before I get into what this looks like in specific immune cells, I just wanted to highlight a couple of the key pathways that I'm going to be talking about in our work. So the first energy pathway that we're interested in is glycolysis. It occurs in the cytoplasm. It uses glucose, and it doesn't require oxygen to function. And the final product of glycolysis is pyruvate. And pyruvate can then be used in the mitochondria to drive mitochondrial respiration. And so the second pathway that we're interested in is oxidative phosphorylation in the mitochondria, or mitochondrial respiration, which does require oxygen, and it produces ATP much more efficiently than glycolysis. So in T cells, which are really the best studied example of immune cell metabolism, at rest, the T cell is mainly using oxidative phosphorylation to produce ATP, which is, of course, the most efficient way to do that. And the T cell is also doing very little synthetic metabolism at this point. But when the cell is activated, it increases both mitochondrial respiration and glycolysis to a large extent, but it becomes more dependent on glycolysis to produce ATP, even though that's less efficient. And it's thought that that is so that intermediates from things like the citric acid cycle can be shunted into other synthetic pathways in the cell to build biomass and to drive these new specialized functions. So you see an increase in synthetic metabolism and also in transporters that bring in substrates for these pathways, like GLUT1, which brings in glucose to drive the increase in glycolysis. So you can imagine that because this is so critical to immune cell function, that it's very highly regulated, and that if something goes wrong in metabolism or in its regulation, that it can contribute to human disease states. So this is a very simplified diagram of different metabolic states in T cells and how they can contribute to different disease states. So for example, if you have high metabolism or a hypermetabolic state in a T cell, it can contribute to autoimmunity, where the immune cells are overly active or active when they should not be. But on the other end of the spectrum, when you have hypometabolism or low metabolism in the cells, they are functioning at a lower level and they're less able to respond, and this can contribute to cancer or a chronic infection where the immune system is less able to control that infection or target and clear tumor cells. So we do have some evidence of immune metabolism in ME/CFS now. So for example, that oxidative phosphorylation may be defective in neutrophils. There was a report that there was increased non-mitochondrial ATP production and cristae condensation in mitochondria from patient PBMCs. And then there are a couple of nice papers from Kara Thomas, which showed reductions in mitochondrial respiration in PBMCs from patients. But she's recently followed up on that and shown no difference in mitochondrial complex activity in PBMCs. And there's also a recent report of reduced glycolytic reserve in patient natural killer cells. So I've done a little work on this that Maureen has previously presented, looking at total T cells from patients from our microbiome study. And what we found was that in total T cells from 20 female patients versus 20 female controls, they were using less of their total mitochondrial respiratory capacity. So they didn't have a different capacity for mitochondrial respiration, but they were using less of it. but we still have a lot of questions as far as how metabolism is affected within specific patient immune cells. And we also had another concern about this data, and that is that there is a lot of variability in the percentage of different immune cells in humans. And so Daria just did a great job of talking about the different T cell subsets, but I'm going to focus again on CD8 positive T cells versus CD4 positive T cells. And if you look at healthy human subjects over age and by sex, you see a great amount of variability in the percentage of CD8 or CD4 T cells. And this is a really nice resource that recently came out, 10,000 Immunomes, that has put together a lot of different data from healthy subjects. So we were concerned that when we look at just total T cells, we're not taking into account the percentage of these subsets, and we really wanted to get into at least CD8 versus CD4 positive T cells. So to do all of these things, we needed a new study population. So in October of 2017, I went out to Incline Village to start collecting a new study population with Cimarron. And they have been a great help in collecting these samples and sending them to us since then. So we've actually recently just finished this up. And we have 45 healthy control samples and 54 patient samples. We were really excited to have a fair amount of males in this study population. And you can see that the ages are well matched between the two groups. So the overall design of this study was to start with PBMCs. We're isolating CD8 positive T cells, CD4 positive T cells, CD19 positive B cells, and CD56 positive NK cells. We're studying metabolism both at rest and after the cells have been stimulated so that we can see how they can respond to an immune challenge and potentially reprogram their metabolism. And we do this in a few different ways. So we're using the Seahorse extracellular flux analyzer to look at rates of metabolism in our cells. We use flow cytometry to look at markers related to metabolism and activation. And then we're using confocal microscopy to actually image the mitochondria in our cells. And all of this work since this last summer has been done with the help of another graduate student in the lab, Jessica Maya, who is here today. And so she's been a huge help in doing these experiments because we have a lot of samples to run. So what I would like to do is first go a little more in depth into the methods that we use, and then I will explain our data from mitochondrial respiration and finally from glycolysis. And today, because of where we're at in the project and in the interest of time, I'm going to focus on our T cell results. So our main method in the lab is the Seahorse, and for this project, we use the 96-well Seahorse machine. And we really needed the 96-well machine to run as many samples as we had, but we only had a machine at Cornell that could run 8-well plates instead of a 96-well plate. And so we've been really lucky to have the help of Paul Geyer's lab at Dartmouth Medical College. He invited us to come up and use the machine they have at Dartmouth. So I made a trip last April, and Jessica and I went back this August to run a whole bunch of plates. And we would not have been able to do this without their help. But luckily, in November, Cornell did purchase a 96-well machine that's in our core facility now that we're able to use to finish this project. So the Seahorse gives us rates of glycolysis and mitochondrial respiration in our cells simultaneously. And the way that this works is you seed your cells in a single layer in each well. And then there are these probes that are inserted at different time points. And each probe has 2 fluorophores that are excited at each time point. One is sensitive to pH, so it gives you a rate of glycolysis because glycolysis produces protons. The other quenches oxygen and gives you an oxygen consumption rate, which is your rate of mitochondrial respiration because complex 4 consumes oxygen. On top of that, the Seahorse has 4 drug injection ports for each well, you can see here. And so you can inject up to 4 compounds sequentially into your cells to perturb different parts of metabolism, and this gives you even more information. So we mainly use 2 drug panels in the lab. The first is the mitostress test. So here we're interested in the oxygen consumption rate for mitochondrial respiration. And we first get a measurement of basal respiration. Then we inject oligomycin, which will inhibit ATP synthase. This gives us a rate of ATP production. Then we inject FCCP, which is an uncoupler. So it disrupts the proton gradient in the mitochondrial membrane. The cell compensates by increasing the electron transport chain, and we get a quote-unquote maximal respiration. From that, we can also calculate a spare respiratory capacity. And then finally, we inject rotenone and antimycin A to inhibit complexes 1 and 3 of the electron transport chain. And this gives us any non-mitochondrial respiration as well as any proton leak. The other assay that we use in the lab is the glycolytic rate assay. This is a newer and more quantitative way of looking at glycolysis on the seahorse. And the reason that it's more quantitative is because glycolysis produces protons, but so does the citric acid cycle. So Seahorse has figured out a way to calculate the percentage of protons that are coming just from glycolysis and not from the citric acid cycle. And this gives you a glycolytic specific proton efflux rate. So we first get basal glycolysis, then we inject rotenone and antimycin A, again to inhibit mitochondrial respiration. The cell compensates by increasing glycolysis, so we get a compensatory glycolysis. And then we inject 2DG, which is a glucose analog, to inhibit glycolysis, and this gives us any post-2DG acidification. Okay, so as I said, we're also doing flow cytometry, and I won't go super in-depth on how this works, but to give you a very simplified description, you can stain your cells with antibodies that are conjugated to fluorophores, and you use antibodies for things on the surface you're interested in. But what we also do in the lab is actually use intracellular stains. So for example, we can stain mitochondria with fluorescent stains as well. And then you have these fluidics that will move the cells one at a time through a laser, which will excite your fluorophores. And then you have detectors for each color you're interested in that can quantify the fluorescence for each color. So you get a quantification of, let's say, red versus green in each single cell. And so some of the things that we're looking at are mitochondria with 2 different dyes, which I'll talk about more in a minute. We look at CD69, which is a marker of early activation in our cells. And we're also looking at GLUT1, which I mentioned is the main glucose transporter into the cell. So to go a little more in depth on how we look at mitochondria, we're using a pretty cool technique that's been used by a number of other labs, where we stain the mitochondria with 2 different dyes. One is MitoTracker green, which stains for mitochondrial mass, so it'll stain the mitochondria as long as the cells are alive. And the other is MitoTracker red CMX ROS, which is actually sensitive to mitochondrial membrane potential. So when you treat the cells with something like FCCP, which is an uncoupler, you see a loss in that red staining, which indicates a loss of mitochondrial membrane potential and tells you that the mitochondria are less healthy. And you can quantify this with flow cytometry as well. So for example, in this paper that was looking at T cells after ED infection, they found a population of cells that had green but had lost red. So each of these single dots is a single cell. And you can also visualize these using confocal microscopy and see cells that have green but don't have red staining. And so we use both of these methods. Finally, as I said, we are activating our cells for these assays. So for both our CD4 and CD8 T cells, we are activating them overnight with anti-CD3, anti-CD28, and IL-2. And we did check this method on both the seahorse and with flow cytometry to see that we were properly activating the cells before we ran our experiments. So now getting into our data for mitochondrial respiration. When we look at CD8 T cells, we see no significant difference in basal mitochondrial respiration between controls and patients, either at rest or after the cells are activated. But what I want to point out in this data that's interesting is that we can see the control population increases its basal mitochondrial respiration to a small extent after activation. But the patient cells really don't increase their mitochondrial respiration after activation. And so this indicates that they may be less able to respond to the immune challenge and increase their metabolism. We did also look at the mitochondria, and so we see that there's no significant difference in MitoTracker green staining between controls and patients, either at rest or after activation. So there's no significant difference in mitochondrial mass. However, we do see a significant reduction in the MitoTracker red CMX ROS staining in our patients at rest and after activation, which indicates a loss of mitochondrial membrane potential. We also visualized the mitochondria with confocal. Oh, before I get to that, so you can also plot the flow cytometry data with dot plots. And so this is merged data from all our controls or all our patients. And what you see if you look at the red versus the green is that the patient cells fall a little lower compared to the controls. And so again, they have less red, but they still have the green staining. The same thing is true after activation in this population here. This group of control cells is actually just due to one control. So now looking at the confocal, what we see is that in the controls, both at rest and after they've been activated, the green and the red co-stain very nicely. So you can see green where there is red, and this merges nicely in the image. But in the patients, we find cells where there are areas of green that either have very little or no red. And this is also true after activation, so there's some green here, if you can see it, that doesn't stain red, and there's overall less red versus green. And so this is consistent with what we see in the flow cytometry data. So now looking at our CD4 T cell results, we again see no significant difference in basal mitochondrial respiration at rest between the controls and patients or after activation. But what's interesting about the CD4 T cells is that the patients seem able to increase mitochondrial respiration, unlike the CD8 T cells, although we do have a lot of variation in the activated mitochondrial respiration. And so along with that, there's no significant difference in either mitotracker green or mitotracker red staining in the CD4 T cells, indicating no difference in mitochondrial mass or membrane potential. And we did image these cells on the confocal as well, and we see really nice co-staining of both mitotracker green and red in all of the cells. So to summarize what I've shown you for this part, we see a decrease in mitochondrial membrane potential in our CD8 T cells from patients, and we also see that they seem to be less able to increase mitochondrial respiration in response to activation. But we don't see any significant differences in the CD4 T cells as far as mitochondrial respiration is concerned. So now looking at glycolysis, we see that basal glycolysis is reduced at rest in CD8 T cells, but we don't see a significant difference after activation in the CD8 T cells. And we see a small increase in glycolysis in both controls and patients. And interestingly, there is no significant difference in compensatory glycolysis in the resting cells or in the activated cells. So this seems to be reserved just to resting cells, and if you push them to increase their glycolysis, they can. We did also look at GLUT1 abundance on the cells, and we see that GLUT1 is increased after activation both in controls and patients, as we would expect, but we don't see any significant differences between the groups. But what I wanted to point out is that if you zoom in on the resting GLUT1 abundance, there's a small non-significant decrease in GLUT1 on the patient cells versus the controls. And really the difference that we see in the basal glycolysis rate on the seahorse is relatively small, and so I think this isn't necessarily inconsistent with the GLUT1 abundance. Next, looking at CD4 T cells, we also see a significant reduction in basal glycolysis in our patient cells at rest, although we don't see any difference in basal glycolysis after activation in those cells. Interestingly, in the CD4 T cells, there is a significant reduction in compensatory glycolysis at rest, but there's no difference after the cells have been activated. So again, the differences in glycolysis seem to be restricted to the resting cells. And again, we looked at GLUT1 abundance, and we see no significant differences between controls and patients. There was a lot of variation in our control population after activation, but this is not a significant difference between the control and patient group. So to summarize what I've now added on, we see a significant decrease in basal glycolysis at rest, both in our CD8 and CD4 T cells. And we also see a significant reduction in compensatory glycolysis at rest in the CD4 T cells. But to take this back to the big picture, if we look at our pyramid of metabolism and how it affects different disease states, everything that we see in ME/CFS is more on the side of hypometabolism. And so this would be consistent with some kind of infection in ME/CFS, but it doesn't tell us for sure that there is an infection or what would have caused the disease. But it does raise a lot of additional questions and experiments that I would love to run. We have some things that are in the pipeline coming up. So I am going to look at cytokines in plasma from these same samples in collaboration with Ludovic Gilotto, a postdoc in our lab, and it's his birthday today, by the way. And we do have a lot of other clinical data from these samples that we've gotten from Cimarron and from our surveys that we're just starting to look through and analyze along with this data, and I think that will really help our interpretation. As I said, we're also looking at BNNK cells, and we're moving along with that project as well, so hopefully you'll hear about that soon. And as Maureen mentioned, I'm also working on a collaborative project with the MECFS research centers to look at PBMC metabolism at rest and after stimulation, which I think will give us a lot more information on what's going on in the disease. And so with that, I'll just again thank everybody in my lab, especially Jessica and our collaborators at Dartmouth and Cimarron, and our core facilities and sources of funding. And I'm happy to take any questions. Okay.
So I saw, at least in a couple of your slides, that you had seemed to have more people in the resting group than in the
Yes,
group.
yes.
So what's that about? Do you think that you have enough power to say, and the other question that goes hand in hand with that is the
Oh, they can't hear you.
The PBMC study that you plan to do. This one you're doing single cell population.
Right. I'll repeat it back. I'll repeat it back.
Try to grab one of those two questions.
Okay, so she asked about how we have less cells in our activated population versus our resting populations. And that was just how many samples we had and how many cells we have. The seahorse requires a lot of cells for every assay. So by the time we get to activation, a lot of times we have limited cells to work with, and we do the best that we can. But I would obviously love to have more samples if I could.
Good job. And your planned PBMC study, how does that differ than the one you're doing right now?
So in the PBMC study, we'll just be working with total PBMCs, and they will be either at rest or stimulated with anti-CD3 and anti-CD28. And it'll just give us another population to compare back and also to see if we get the same results as Kara Thomas's paper.
Any other questions? Well, congratulations. You're our speaker of the day for staying on time. Well done. And I want to thank everybody in this session.
I am thrilled to introduce the next session today, where we'll hear about a variety of different topics, amongst them the use of provocation studies to better understand exertional intolerance and post-exertional malaise that we heard from Dr. Bateman's excellent earlier talk can be quite pronounced in MECFS. And our first speaker today needs little introduction. We're first going to hear from Dr. Nancy Klimas at Nova Southeastern University, and we're going to hear about her work accelerating the clinical trials and using modeling to predict interventions. So please join me in welcoming Dr. Klimas.
Thanks. So now I get to be the one that they say, hey, you're talking too slowly, get moving, get moving. So thank you anyway. This is fun to be in this session. I feel a little bit like a fraud because I'm standing up here speaking on behalf of an amazing team of people who could give this talk much better than me. And if I was clever like Maureen, I would say, hey, Travis, come on up right now, man. But I'm going to be showing some slides that are the work of a lot of very good people. We are a very large research group down at Nova Southeastern University down in Fort Lauderdale. In fact, we're 16 faculty members and 60 people dedicating ourselves to MECFS and Gulf War illness-related research across a lot of disciplines. And that was a very deliberate effort to be able to use a systems biology approach and a multidisciplinary approach to try to understand an illness that we've been looking at through different windows for years. And we were so excited about the possibility that we could move this and then put it into place, doing clinical care in an academic center where we could really do translational research all the way through human trials. And that is indeed what we have managed to accomplish in the 6 short years since we started this institute. We are funded from a lot of different kinds of places. We're grateful, very grateful. I don't even begin to look at all the private donations that have funded much of the pilot work here, but NIH, the CDRMP, the VA, and private foundations have helped us quite a bit. We currently have awards, and at least the work I'll be talking about today come from awards to the people listed on this slide. Dr. Nathanson's here, Dr. Craddock, Dr. Fletcher bowed out for this particular meeting. Gordon, I hope you're on the video, on the audio somewhere, because I'll be making your ears burn as we talk here. My disclosures, I don't have any money that I've made off of this. Sorry about that. I've never learned that trick. There are other people who know how to do that, but not me. Anyway, so this talk is to focus on dynamic modeling. And honestly, this dynamic modeling idea came up more than a decade ago at a CDC workshop where I met Gordon Broderick for the first time with a group of other great people, and we got to brainstorming. When, if you know Gordon, you'd know that alcohol was involved for the best part of it. But when it came out, then, because Gordon knows how to facilitate collaboration. He's a two-handed pourer. But he and I and Marianne Fletcher sat together and dreamed up this scheme that we could use exercise as a challenge and measure across the challenge and see if we could better understand the mediators of relapse and the mediators of persistence by doing a challenge. And so we dreamed up a series of studies. We've done 5 studies now from more and more elaborate to get the data we needed to do this dynamic modeling. In those studies, we do a host of laboratory measures, as many as we can know how to do and can reasonably afford to do, and it gets better because we have a biorepository. So as new methods come up, we can pull from those already challenged subjects that we have vast amounts of data on and keep making the models stronger by doing more types of data, laboratory assays and data analysis. And then we use this systems biology approach. I use the we, you know, in the, aren't we all in this together? Because Travis and his team, Travis Craddock and Gordon Broderick, are the computational biologists, and they're leading some amazing young scientists doing this amazing work. As I said, we're approaching these 2 illnesses. This one I don't even have to mention, but this one I'm just going to say, you heard a little bit about Gulf War illness. Gulf War illness is referring to the 1990-91 conflict when we sent 800,000 troops to the Gulf War, and currently roughly a third of them are ill today, 28 years later, with an illness that for all the world you could overlay on top of ME/CFS clinically. So it seemed like a good comparator group, and it also gave us some opportunities for funding that we would never otherwise have had. So we have been happily comparing ME/CFS to Gulf War illness for some time now. Now, initially, we did go through the one lens, one field. So I'm a clinical immunologist. We were looking at immunology a lot early on, and we could see patterns. We could see neuroinflammatory cytokine patterns, things you heard about today. And here, the 2 illnesses overlapped pretty well. They both had NK cell dysfunction. They both had a lot of neuroinflammation. They both had the cytokines that regulate cytotoxicity were diminished. So there were things to see. And using that single lens approach, we could do in vitro studies that we still take advantage of today, where we could try to fix one thing, like NK cell function. In this study, we replaced the missing IL-15, and lo and behold, the NK cells worked again. So that was a good study. We haven't been able to put that into a translational human trial yet because of problems getting access to the drug. But we did make some points that you could do in vitro testing of putative treatments, looking at single targets of treatment. But it's more complicated than that. As anyone who's clinically doing this knows, and anyone that's doing this science knows, it's not a single broken cell kind of disease. So this is our current method. We put people on the bike and we measure 8 different blood draws rapidly over 24 hours. I say we euphemistically because Fanny Collada is sitting back there, and she's the clinical coordinator that puts these guys on the bike and draws all those bloods. So we're grateful to Fanny for all the work she's done to pull this amazing study together. And this is a hard study. We're drawing bloods very, very rapidly on the bike. We're drawing them on the bike, 3 minutes, peak of exercise, immediately after the exercise, and then on and on and on, all the way through, so that we can really get the time course and do dynamic modeling. We measure across a lot of domains, from the intracellular cell population, cell-cell signaling, through into the clinical space. So we can make correlates all the way through into symptom complex and severity. And that's a very comprehensive study. And things shout out at you. These aren't the same illnesses when you do this. They look like the same illnesses. Lots of biomarkers are the same. Lots of the treatable targets are the same. But if you just take this study, this is one that looks at the connectedness across an exercise challenge in various gene modules. And the pink guys over here towards me are the healthy controls. And you can see that there's a lot of communication from one gene module to the next. You saw in Jose's data where one set of genes is connected to a lot of other genes downstream to make a lot of action happen. And if you look at the Gulf-4 group on the far side, that's a dense network. There's far more linkages than in healthy controls. And they're different linkages, and there's a lot of signaling noise. But look at the ME/CFS group in the middle. There's not much communication going on. And when you look at these genes, they're showing a hypometabolic state. There's less signaling and less metabolic gene activation over an exercise challenge. So that stirred us up and said, wow, we got a little something from this method of looking across an exercise challenge. That was just our first little wave of looking. Now, could we do something a lot more exciting with that than say things are different? Could we potentially identify treatable targets? Could we, in a virtual space, do trials, actually do clinical trials? And could we understand, in order to do those clinical trials, we'd have to understand the homeostatic networks in play and challenge homeostasis and ask if we could physically move it from one set point, some comfortable set point of homeostatic network in this sick condition, towards the homeostatic network that we could identify in the well condition. And that has been the focus of much of our work these last 5 years. So and these are straight out of Travis's slide deck from Australia. These are the most updated slides he just presented a few weeks ago on the other side of the planet. And but this is the kind of work that's underway. In this particular study, and I might add that we are doing this in Gulf-4 illness men, Gulf-4 illness women, chronic fatigue syndrome, ME, men and women. We've done the full recruitment of all of those groups and have all this dynamic modeling biology either underway or done or sitting in the biorepository waiting to get completed. So we have what I consider as the clinician in the study, the hard part done. We recruited the subjects and we got the data, the stuff collected. Now, you guys in the back will get me later. I know that. I'm sorry, but that was fun. I know. There's so much work to do. Anyway, this idea is that we could take these data and then see if we could correlate critical findings with symptom burden and symptom complex, and then see if we could actually find druggable targets and the drugs that would do it. So the first thing you can see in this very recent analysis, this is a paper that is in press right now, is that there were some affected modules that really popped out of all of the modules that were in analysis. And some of them you heard today, so I feel like I'm validating through another set of eyes and another very different method. The TGF-beta matters, and the TNF-alpha is an important module, and the B-cell and T-cell receptors are playing a role in this dynamic modeling way of looking at the disease. And they correlate with severity, and they correlate with specific symptom complexes. So this is the B-cell and T-cell receptor clusters. Again, this is a paper about to come out, so I won't spend a long time on it. But the correlates were there, and that's exciting. Same thing with the TNF cluster. You see correlates with physical functioning and pain, mental fatigue, and so on. Oops, help. That was exciting. What did I do? Was that an editorial? Are my people in the back room after I made that snippy comment about the amount of work that this is going to take? I know. I'm sorry I did that. That was funny. This is fun. More fun than you're supposed to have when you're at an NIH conference talking to the top people in the field. Oh, boy. All right, we're back here. Okay, I'm back on the target. This is fun. So anyway, we end up with these putative targets. So now you can say, well, is there something treatable in there? And here, again, this is the work of Travis Craddock. He's very creative computational biologist. And he cross-referenced the targets with the Pharm GKB database to find the gene-drug interaction space, what drugs are approved, what kind of targets are out there, and specifically found these 11 targetable gene products that showed significant differences between the control groups and the ME/CFS patients, and then proceeds to dig deeper. And so these kinds of digging deeper, looking at hormone regulation, looking at the TNF and TGF-beta regulatory space in that way. And then ask the question, can you model the illness by touching one or more of these targets in any particular time course that could potentially reboot or reset the homeostatic networks in play? And that's our big game. That's our, the moonshot of the team, is are you able to reboot homeostatic networks back towards normal and see if you could reestablish health in a chronic illness? I love that this, again, sounds a little bit like a talk we heard first thing this morning about the importance of looking at things dynamically and thinking about chronic disease as a process with a lot of different components that go towards health that might be quite different than how you got there. So this is the going towards health and not how you got there approach to trying to understand, like Dr. Naveau said this morning, how we might go about doing that. So the key systems engaged here, of course, are the immune, endocrine, and central nervous systems. These are systems of crosstalk. They're in balance. And in our virtual trials work, there's no one button that can put them into alignment. There's no single drug treatment that you might consider to realign in these ways. So the way the computational team went about this was to construct models from known regulatory physiology from the literature and create this model of normal, and then simulate the evolution of the model and looking at what's called stable behaviors. What is a balance in a sick or in a healthy way that could occur, and then try in a virtual platform to intervene and reboot or change the way these systems are balanced. And so if you would look at this idea here is these little mountains in the wells. If in health you're stuck in this little well, in health this is your place, you get a little sick, you always roll back into the well. You don't climb up and go into a new space. Should you climb up and go into this new space, you're in a new space, and that's chronic, and you're not getting out of it unless something dramatic happens to push you back out of it, because that's a new space and it's unwell. So the idea here is that strong or severe external factors can force you the perfect storm of events from one state of homeostatic wellness into a state of homeostatic unwellness. And when we look at Gulf War illness and chronic fatigue syndrome, they're different wells. They're not sitting in the same spot. We're constantly trying to improve on the model. So the model we have is from a physiologic state that we're getting from peripheral blood measures and other measures. But there is a real effort to improve on the model to include the brain environment as much as you possibly can, because it's critically important. This is a neuroinflammatory disease. And so just recently, just very recently, a couple months ago, Travis published this paper looking at the linkages of the neuroinflammatory system in this type of regulation. And subgroups emerge. And subgroups emerge that are based on gender. Women and men are different. It's shocking. I know you all are very surprised that men and women actually physiologically can be proved to be different creatures. It's pretty cool. And postmenopausal women and premenopausal women are different in these models, in our models of wellness and unwellness. And in the Gulf War model, high stress and low stress flips into separate models. So people with comorbid PTSD, for instance, and Gulf War illness will physiologically track out to be different. In fact, we're going to have drinks because stress really matters. And we're not talking about stress as in, I'm up here giving a talk and the slides aren't working, but rather stress as in cortisol levels really influence the outcomes of these models. And then in the modeling, we're looking for steady states, a balanced state. Where is the state where it's stable and it would stay that way? Can we model a way to get that way? And that is certainly what Travis is doing. Now, Gulf War illness is our best example of what we've accomplished to date. In Gulf War illness, all this work was done in men and women, high stress, low stress. And the high stress men group looks a lot like the mouse model that we have for Gulf War illness, because it's not a big surprise you stress these mice to make them sick. So in the Gulf War mouse model, you either give them an organophosphate exposure or serum, which is another organophosphate, but one of the exposures that the Gulf War veterans had in theater at the time that they were in a high-stress state. Cortisol levels presumably went high. So the mouse, you hit them with a neurotoxin in a very tiny amount, the amount the veterans were exposed to, and you hit them with the cort level, an amount that normal physiology can get to under stress, and you can create this chronic illness that perpetuates for the life of the mouse. Then we can put the mice on a little wheel and dynamically challenge the animals, and we can try to align all of those measures. And that's what we did. We aligned all the measures, found the best of the animal models for Gulf War, and then tested this example of a virtual trial in that mouse. In this virtual trial, you had to reduce neuroinflammation and then block the adrenal axis with a glucocorticoid receptor antagonist, and then you would reboot the HP axis of everything in the animal. And so basically that's what happened. We all did the happy dance about 2 years ago when this study was completed, and indeed the animals who were treated with a TNF receptor antagonist, Entarecept, for just one dose in an animal, it's a long time in a human, and then one dose of mifepristone, which is a glucocorticoid receptor antagonist, to follow. And the animals rebooted back to normal their neuroendocrine, autonomic, and immune measures. So we were very excited that we seemed in our very first optimistic go to have something, and we were funded to move it forward. So we actually are today in the middle of our phase 1 clinical trial. Again, Fanny, thank you, Fanny, for recruiting subjects. I think we have 6 subjects so far that have received this treatment. We're going to complete it with 20. I don't have any preliminary data to share with you yet. It's too soon. But it's an open label trial that we got to move along. I will also say that in the modeling, this is not the only model of a treatment for this type of complex illness. We had other models. This was a simple one. We picked an easy one first. But there were 2-hit models, 3-hit models, repeated hit models. And so, but we're excited that we've moved this along. And this is my cartoon. I don't know, the guys never use it, so they must not like it. But the idea is that we took our human data, measured everything we could, found a mouse that paralleled the human, did it all over again with the virtual trial that my supercomputing, chaos theory, thinking, computational biology, amazing team put together. Treated the mouse, found out it worked, moved on to the human, and we're hoping for the happy ending. It's our moonshot. We'll see. So where we are now then is we've learned a lot. We've learned that differential expression, doing one biomarker at a time, is very helpful, but it doesn't give you the complete picture. Methods that look at structural reorganization give us a better picture. Using an exercise challenge really ramps up the signal in being able to understand what's going on in the sick person, as well as understanding health better. The time course data gives us the ability to do dynamic modeling and looking at things flowing through networks, and looking at models that come out and subgroups, biologic subgroups that emerge. which is very exciting that that can be done. And this concept of homeostasis in virtual trials came from that. So now we are actually in human trials testing this. We're still doing our virtual trials. We're trying to develop an animal model for Gulf War illness, knock on wood. That's got some money to work on that. But at least we're using repurposed drugs. So I'm feeling pretty confident that if in our virtual models we have something, and then in the in vitro in-lab testing, as best you can do without a whole animal, we've got something that makes us feel like we're on the road. If we're using safe drugs and reasonable procedures, we'll move on to human trial. And so we were funded by a bunch of funny things that I'd tell you over drinks tonight. But anyway, we got funded privately by several different sources. But basically, let's just say we bartered our knowledge for money in another disease so that somebody else would pay for our study. But anyway, we're now in this phase 1 space for ME-CFS. It's in front of the IRB this month. And we anticipate that we will be starting a ME-CFS clinical trial using this same kind of modeling in the coming months in postmenopausal women and in men, because we have clean models and some money for that. And in premenopausal women, we don't have enough money to do every single subgroup that popped out yet. We need to do some more fundraising or find some grant support to press on in the premenopausal women group. So this is our huge team, amazing people. 10 of us are in the room right now. And Lubov and Travis, I used a lot of your data and pretended like I was channeling you. Marianne Fletcher, who's not here with us today, is the director of the Biomarker Discovery Laboratory, where much of this happened. Christina and Maria Brew and Christina Enley are in the back, who do all the immune and many of the biomarkers. Malav, who's our bioenergetics guy, had his day yesterday in the young investigator group. Aman's joining our group now to start doing some nutritional sciences work with us. But we have an amazing group of people, and the clinicians that are able to move it forward. Maria Veras, we're here with us today. Dr. Bested joined our group from Canada. We stole her, I'm sorry, Canada, but she's amazing, and she's directing our clinics. So that's our team. That's what we're doing. I want to say one other thing. Dr. Fletcher is retiring later on this year, and she has been a member of our group and in this field since the first day. She should be our hero. So she's amazing. All right. Sorry, I didn't totally run out of time. That was not bad. Do we got time for a question? Or? Got time for a question. How about that? Usually I don't talk that fast. Any questions? We have one question coming to the microphone.
So I'm kind of new to this area, but I understand there's a very large sex difference in ME-CFS in particular, and I'm not sure so much about the Gulf War illness, but I was curious, since you've studied both men and women in both diseases, since it's a very difficult disease to diagnose, do you think there could be different responses to similar triggers that lead to the disease being underdiagnosed in men? Because maybe the constellation of symptoms are a little bit different, or the severity, or do you think it's really, that dramatically different in men and women in terms of frequency?
So I have a bias. When you create a disease around a case definition, you get what you get, Mm-hmm. So there is a problem when you have a clinical case definition and we don't have a common biologic biomarker that would define the group. So in every disease, not just this disease, that's always been the case. Nonetheless, women get immune diseases far more often than men do, and in inflammatory diseases, and it's no big surprise that women would be in much higher prevalence than men in an illness like this. It's just exactly what you would expect. So I think the guys are out there. I think they're probably underdiagnosed, but I think that the women are always going to be the significant majority of the cases. All right. Yeah, you know, we need to we need to talk. Thank you very much.
Thanks so much, Dr. Klimas, for that fantastic talk. And next up, we will be hearing from Dr. David Systrom from Brigham and Williams Hospital and Harvard Medical School. And we will be hearing about Dr. Systrom's work looking at the pathophysiology and treatments of exertional intolerance in ME/CFS.
Oh, yeah, thank you. Thank you. They got to flip over to my Mac, Andrew. Oh, that's great. Yeah. Awesome. Yep. Right. Thank you very much, Andrew, for the kind introduction. First, a couple of disclaimers. One, I think you'll do fine with. The other you might not like. The first is that I am a lung doctor, go figure, doing ME/CFS. And the second is that I'm from Boston. This one you will hold it against me, I know. Sorry about that, but we can't help it. It's not all bad being from Boston. We don't have a Dr. Angstrom, don't have that in our history, but we did have a Dr. Henderson who did the Henderson-Hasselbalch equation back in the day, and he established this place called the Harvard Fatigue Lab, and it actually put many of the basic tenets of exercise physiology that we now know to be true on the map back in the 20s and the 30s over by the Charles River and the Harvard football stadium. So here's a table of contents about what I'd like to cover over about 20 minutes. I'd like to tell you about something called an invasive cardiopulmonary exercise test, and it's nice going after Dr. Klimas because it's perhaps related. It is. The basic part of the exercise test is related. What we add with the invasive variety is the placement of radial and pulmonary artery catheters before the exercise test, and then they roll around the corner, the patient, from the catheterization lab to the exercise lab, and we get a lot of data. The way I got into this business as a pulmonologist and critical care doc was initially developing this test at Mass General to detect early heart disease, early pulmonary vascular disease, but along the way, what we found were patients with or underexplained exertional intolerance coming to us, many of them ending up with ME/CFS with a clinical diagnosis. So I think we have something to offer with this test that was developed initially to detect other diseases. So if this works, I'll just show you it a little bit in action. This is in the basement of the Shapiro building at the Brigham and Women's Hospital, where we do about 10 of these a week for a variety of indications, but over the last 3 or 4 years, about half of them for patients with ME/CFS or variants, unexplained fatigue, lightheadedness, and dyspnea. Here are some of the key numbers that we get out of this test, and I'll come back to all of these during the course of this. One is non-invasive. That's the maximum oxygen uptake at the end of incremental cycling. It gives us a gestalt for how ill the patient is. I will tell you right now, if you're in the business of doing this, many patients with ME/CFS end up with relatively normal VO2 max. It can be surprisingly normal, 70, 80, 90% of predicted. They should not be written off as not having any pathophysiology, as I'll show you in a minute. Two other key things that we get with respect to ME/CFS. One is the filling pressures, and in particular the right atrial pressure. That's the filling pressure for the right heart, which we have found to be pretty uniformly abnormally low during incremental upright exercise. And I emphasize upright. If you do this type of exercise supine, you miss the signal. The other one that we have found, and I will discuss here, is the difference between arterial and mixed venous oxygen content at peak exercise. This reflects oxygen extraction in the periphery and the muscle, and we have found it to be abnormal in a majority of cases. So we'll come back to all of that. So here's what you should do if you're normal. In the green, a little cartoon for VO2 max going up during incremental cycling. And if you're sick, and this could in theory be heart, lung disease, muscle disease, circulatory issues, the VO2 max falls. And our friend, the Fick principle, helps us explain that depressed VO2 max, and this is really where the pulmonary artery and the radial artery catheters come in. We can calculate a fit cardiac output by measuring the VO2 and then the difference in arterial and mixed venous oxygen content every minute during exercise and at peak exercise. So then we end up with the determinants of VO2 max. Cardiac output, as you see, is deficient in some of the patients with ME/CFS, and impaired systemic O2 extraction is the other pattern that we found. So this is what they look like. This would be a low flow state, and this is one of the patterns we have found, as you'll see. And this is somebody with impaired systemic O2 extraction, where the major abnormality in terms of the VO2 max is impaired systemic O2 extraction. They fail to depress the mixed venous oxygen content. The difference between the two is too high at peak exercise, and there is a depressed VO2 peak. Here's a quick example. This is a patient, this will resonate with some of the patients we have here today. She was, and she's given me permission to discuss some of her personal details. She was a cardiology fellow over at Boston Children's. She was a competitive cyclist, and she came to us, "Doc, I was fine until I got the flu 2 years ago. Since then, I've not been fine." And she was actually investigated for fatigue and orthostatic intolerance and some dyspnea. About $1 million spent on her, which is not too unusual, as many of you know. At good hospitals in Boston, no answer. We did a non-invasive test, and her VO2 max was 50%. It should have been 150% as a competitive cyclist. And what she had was low filling pressures. So this is it here. The right atrial pressure in magenta here fails to rise normally during incremental cycling. It should go from about 3 to 10 millimeters of mercury. There was no hint of augmentation. So based on her and many other patients we saw anecdotally, we did the following published study from 2 years ago. It's a little busy here, but what I want you to take away is these are 616 invasive cardiopulmonary exercise tests at the Brigham, and we ruled out everything under the sun first. This is pulmonary hypertension, heart failure, inadequate effort, anemia, etc. And then what we ended up with were 77 patients. A cadre of them were normal. For all the world, they came to us with symptoms, but we couldn't find anything wrong with them. The VO2 max was normal, the peak cardiac output was normal, and systemic O2 extraction was normal. We used them as a comparator group. And then there was this other very interesting group. This was the impaired group. Their VO2 max was less than 80%, but they didn't have the usual reasons for it: heart failure, pulmonary hypertension, lung problems. So we asked the question, what was underlying their impaired VO2 max? And the answer was low filling pressures, and especially at peak exercise, shown here for the right side, the right atrial pressure, and for the left side, this is the pulmonary capillary wedge pressure, an index of the left atrial pressure during exercise. This seemed to be the theme that explained the low VO2 max in these patients. We attempted to relate those low filling pressures here, the right atrial pressures, to the impaired VO2 max. The lower it was, the lower the VO2 max. The lower the left-sided pressures were, the lower the VO2 max. And the mechanism here was largely impaired cardiac output. So we call this preload failure. It's a colloquial term we use in our lab. We then did an interventional cohort where we gave acute normal saline boluses in an attempt to get the right atrial pressure up normally at rest on the cycle ergometer, and we asked them to pedal again, and lo and behold, everything was better. So right atrial pressures were better at peak exercise. The wedges were better. The stroke volume response to exercise was better. The cardiac output was better, and the VO2 max was better. So we published this and went back and retrospectively looked at the demographics of the patients, and most of them had evidence for ME/CFS. So that kind of got us into this business. So I'm now going to tell you about some exciting new data. All of this is about to be published, so you're the first to know here. The first one is this, something called small fiber polyneuropathy, which some of you may know. And first, a little special call out to Ann-Louise Oaklander, who's here in the audience and whom you'll hear from tomorrow. Neurology at Mass General, a close collaborator with ours. She has really established this test and established normal fiber density in the epidermis. And if you can see this, there is a little brown thing here, which is the small unmyelinated neurite that innervates the skin, the epidermis, which we sample. It's a minimally invasive punch biopsy right above the medial malleolus. And please note that this little nerve fiber travels with a vein and it travels with an artery. It also innervates sweat glands, shown over here. So we can sample these things, and Dr. Oaklander expresses them as a centile, basically the nerve density as a centile compared to normals. So the next bit of data is again borrowing from our invasive cardiopulmonary exercise test. In this case, 1,500 patients in whom we ruled everything else out in the world, identified preload failure as their major problem, and then ruled out the patients who had not, for whatever reason, had a skin biopsy. So we're left with a cadre of patients, 223 patients, who have had a complete invasive CPET. They don't have anything except preload failure, and they have had an Oaklander skin biopsy performed over at MGH. Here are the demographics for these patients. There isn't too much important here. I think maybe the medications are semi-important. There is a paucity of things like venodilators, calcium channel blockers, and diuretics, so we don't think those were the answers to the preload failure in most of these patients. The associated diagnoses will be very near and dear to this group here today. So we went back and interrogated charts, and we interrogated patients with IRB approval on the telephone to determine whether they meet the Institute of Medicine definition for ME/CFS, and the majority does. 72% of these patients I'm about to describe. And then, as all of you know here, major overlap with postural orthostatic tachycardia syndrome, fibromyalgia, mast cell activation disorder, and many of them gave a history of a sentinel viral infection. What was their exercise phenotype? I'm going to present this slightly differently from that first paper I showed you. This is a bit different. Here what we have identified is a high flow and a low flow state. High flow over here on the red, low flow state. And you do that by doing cardiac output slope versus VO2. A normal slope is somewhere around 5 ml, 5 to 6 ml per ml. So this is kind of the middling slope. There's a high slope here and then a low slope, and I'm going to go through the differences between them. Here are the cardiac outputs at peak exercise. One I want to emphasize is that the high flow group, meaning higher cardiac output than expected for level of metabolism, have de facto impaired systemic O2 extraction. There is a hint of lower systemic vascular resistance. So we think some of the arteriolar resistors perhaps are open in the periphery, and there is a high flow, a de facto left to right shunt going on. We know it's not at the level of the heart. It seems to be microscopic. We have data from the resting right heart cath that proves they don't left to right shunt at the level of the heart. And then, as I said, we went back and determined how many of these patients had true ME/CFS. The answer is a majority of them. That's here in the red by the Institute of Medicine definition. And then we additionally asked what was the prevalence of small fiber polyneuropathy with Dr. Oaklander's biopsy in this group, shown over here confined to the ME/CFS group, and the answer is a little better than 40%. So the first, I think, perhaps new notion here that emerges from these data is that there is a high prevalence of small fiber polyneuropathy in ME/CFS. This is a frighteningly similar prevalence to things like POTS, that's been published, and fibromyalgia, that's been published. We then additionally attempted to link some of our invasive cardiopulmonary exercise test variables to the nerve density in the skin biopsy. And we're viewing the skin biopsy as a view into the interior of the organism. Neurology meets vascular biology. And unfortunately, we didn't find much. These are all scatter plots. What we've got here is the peak exercise cardiac output, the peak VO2 as a percent predicted, that extraction problem that I mentioned, and the right atrial pressure, the filling pressures. So there's a high prevalence of small fiber polyneuropathy, but when we look at the neurite density in the skin, it does not correlate tightly with the exercise pathophys. So I think it's permissive, but it doesn't explain it all. And perhaps, and this is speculation, It's not only the nerves, whether they're there or not, that's the anatomy, but it's the small fibers and their function, which aren't measured, obviously, by a skin biopsy that might be playing a role here. Right, so I'll shift gears here slightly, and I'm going to describe one kind of dedicated pathway that we think has some potential to explain both fatigue in ME/CFS, but also potentially could have a link with the small fiber polyneuropathy, whose prevalence is pretty high here. So something called TRAIL. I found myself at a meeting here in this lovely city about a year ago, and there was the intramural NIH group here. Rebecca Fang is here in the audience, and she and I and her colleagues started chatting, and they had a hypothesis that fatigue and autoimmune disease might be mediated by this pathway. So TRAIL is interesting. It's a cytokine, as some of you may know, the TNF-related apoptosis-inducing ligand. It's a ubiquitous cytokine secreted from most cells in the body when the body is perturbed. I'll tell you what it does in a second. Here are some of the things that provoke it. Might be of interest to ME/CFS because there's a laundry list of viral syndromes that are known to provoke TRAIL. Now, why should TRAIL be linked at all to fatigue? Well, one reason is that there is activation by one of the pathways and two of the TRAIL receptors of NF-kappa B and the whole pro-inflammatory cytokine that cascade that ensues from those receptors being stimulated or the ligand with TRAIL. There is also a dummy receptor or a decoy receptor shown over here. This does nothing. It binds TRAIL and therefore tamps down potentially both apoptosis and inflammation. Now, the interesting thing about nerves, and we think this is true both of peripheral nerves and central nervous system, is that they lack the decoy receptor. So this is a potentially neurotoxic pathway that can be stimulated by virus and a variety of other environmental insults. So this paper got our attention. This is the intramural group, Dr. Fang et al., whom I mentioned. They studied this and published this about a year and a half ago in the setting of fatigue induced by XRT or radiation therapy. What they were able to do was to show two groups after radiation therapy followed longitudinally. One developed fatigue by a questionnaire and cognitive decline, and the other didn't. And what seemed to differentiate the two, at least in some of the measurements they made, was TRAIL. And take a look here just for a second at the concentrations in peripheral blood that they saw. This is 10 picograms per milliliter here in the non-fatigue patients and sort of 30, 35-ish for those who are fatigued. So we got the bright idea that perhaps the acute exercise perturbation that we're doing at the Brigham might provoke TRAIL that had not been published before and might play a role in both acute fatigue during exercise, but maybe even post-exertional malaise. So here are those data. This is our group with ME/CFS undergoing the invasive CPET, and these are TRAIL concentrations measured in arterial blood, not yet mixed venous blood. And there is a bump. This scale is a little deceiving, but there's a significant bump at peak exercise compared to rest, and then 1 hour into recovery, it disappears. We then asked, could TRAIL bump during exercise at all inform our discussions or our findings about small fiber polyneuropathy? And sadly, there seemed to be no difference in the TRAIL bump to acute exercise with, in the green, or without small fiber polyneuropathy. So more on that. We've got many more bloods and normal controls running. Actually, they arrived, the assays arrived yesterday here at NIH. Finally, I wanted to give you a little off-label treatment, perhaps tantalizing data, which we're just looking to get published as well. We have trialed a variety of medications in the clinic with ME/CFS, largely borrowed from the POTS circulation, POTS literature. Blair Grubb in particular has been particularly helpful for us. So one that we have had, not all anecdotally, most luck with is pyridostigmine or mestinon. This is an FDA-approved drug for myasthenia gravis. So I'm going to give you a little bit of data of follow-up of patients with non-invasive exercise testing treated with pyridostigmine, and I'll tell you in a minute how I think it might work. So these are 62 patients with ME/CFS and preload failure on the invasive cardiopulmonary exercise test. We took a look at them at baseline with the invasive test and then at about a year out on average with a non-invasive exercise test called INACOR, which allows us to measure VO2 max and a non-invasive rebreathing cardiac output. And the average Mestinon dose was a little bit high, at least compared to the myasthenia indication, 231 milligrams. And here are the pertinent Fick principal variables at baseline and then at about 1 year out on Mestinon. The INACOR gives us the peak VO2, which had improved significantly, and interestingly, more through improved systemic oxygen extraction than by cardiac output. And what we think potentially might be happening here, because this is a cholinergic drug, it inhibits the breakdown of acetylcholine at the synapse, is that at the sympathetic ganglion, it may be facilitating adrenergic outflow, in this case to the arterioles that are dysfunctional, many times associated with small fiber polyneuropathy. So that's essentially what I have for you, just in the way of a quick review. I gave you 2 invasive cardiopulmonary exercise phenotypes in ME/CFS. One is a low flow, that was the Oldham paper, gets better if we tank them up and seems to get better to a degree with pyridostigmine, and then the high flow where there seems to be potentially left to right shunting in the periphery. A high prevalence of small fiber polyneuropathy, and the linkage between these two things we're still working on. Trail is interesting to us because it's potentially neurotoxic, goes up with acute exercise. We'd love to know ultimately its relationship to small fiber anatomy and function and post-exertional malaise, and then finally a bit on treatment. Quick future directions. We are keen to know whether this is true left to right shunting in ME/CFS, but plausible is mitochondrial dysfunction in the limb skeletal muscle, and I know that's part of the mission of the NIH group addressing ME/CFS. It is for us as well, and we have just begun to do muscle biopsies in addition to a potential seahorse assay in the blood. We're keenly interested in knowing how all this acute exercise physiology, pathophys, relates to post-exertional malaise. Really quick shout out to Philip Joseph, who's a fellow at the Brigham. He's commandeered much of this, Rudolph Oliveira, Carlo Rodriguez, Donna Felsenstein, an infectious disease doc at Mass General, Rebecca and Leroy, both here at Intramural NIH, Aaron Waxman, who puts in our PA catheters, and Anne-Louise Oaklander, and I thank you very much for your attention. We have time for a couple of questions.
It's a great presentation.
Thank you.
Do you think that the patients that had this high preload, the high proportion that you have found, has to do with the fact that they were screened through the exercise testing because they had some symptoms? And if you were to do the study in a larger universe without necessarily having symptoms leading to the exercise testing, it would be different. And how do you connect the physiology between the preload failure and the small fiber neuropathy?
Right. So the latter I get and is easily answered. The former, maybe we just have to come back to for a second. So Dr. Oaklander has taught me, like the little cartoon showed, that the unmyelinated small fibers there are different populations physiologically. They're adrenergic and they're actually vasodilatory, some of them through CGRP. And they're wrapped around blood vessels, both veins, and so we view that as probably inadequate venoconstriction, priming the pump in the upright position, and then arteries, whose job during exercise are to divert that cardiac output to the mitochondria in the muscle. The first one I sort of missed, the first question about symptoms.
Yes, so would you extend the findings to patients with ME/CFS who will not have the symptoms, who would have led them to do the exercise testing? Is the finding of the preload you think is universal for ME/CF, or those who have been self-selected?
So it's a really good point. We have certain referral patterns, and by virtue of what I do, those are unexplained exertional intolerance flowing through our system. You're right. So would it be different? I don't think so, honestly, because I haven't found one yet who hasn't had vascular dysregulation with ME/CFS.
Hi, Dr. Systrom. Thanks for your work. I've actually corresponded with you and Dr. Oaklander. I'm Lily Chu, and thank you for answering some of my emails. My question is, earlier you heard Dr. Berquist talk about autoantibodies to muscarinic and adrenergic receptors, and Dr. Scheibenborgen from Germany has also done the first papers on that. So is there any thought about testing for these autoantibodies in your sample?
Right. So we routinely in our dyspnea clinic at the Brigham screen the patient for at least a limited number of autoantibodies, including the Mayo Clinic paraneoplastic autoantibody panel. Buried in there, I would say the most frequent hit, and that's probably 10 to 15%, is an antibody, acetylcholine receptor antibody, ganglionic variety, which is really interesting because it's really myasthenia of the ganglion, and then if mestinon works, maybe we know what we're treating. And then there are a variety of others as well. I've not done the adrenergic autoantibodies. I'm aware of the work you alluded to, and I think that's probably a great area for collaboration. Sir?
Okay, I'll go. So, any correlation between right atrial filling pressures and left ventricular isovolumetric relaxation times in diastole?
Good question. We don't have imaging. I would love to have it. We just have pressures during the exercise test, and then a natural thing to do these days would be cardiac MRI, and that's been suggested. But the problem is, you put them supine for that, and then you lose all of this. You have to have gravity in the patient in the upright position to see everything. So, and echo, of course, is difficult in the upright position during exercise.
I just asked because IVRT delays have been published as a finding in patients with ME/CFS.
Okay, no, great thoughts. Thank you. Sir.
Very interesting presentations.
Thank you.
I'm relatively new to ME/CFS, but was trained in exercise intolerance and chronic disease. And when I first look at this literature, this is circulatory control problem until proven otherwise. And so one of the things that I find needing to be done is normalizing circulation and looking also at one-legged exercise, because and I'm curious if you've tried to look at that, because the simplest explanation is actually poor vasoconstriction in the non-active vascular bed, preventing circulation getting to the exercising muscles. And that is the probable explanation for the low AVO2 difference, which I find somewhat analogous to a wide AA gradient in pulmonary physiology.
Agreed with all the above. So yes, our suspicion is that what we are demonstrating is left to right shunting in non-exercising muscle perhaps, but other organ systems like skin and gut. We agree totally. Fascinating question, and I think the one-legged exercise would give us some read into what is going on. It's been done in congestive heart failure, it's been done in bad pulmonary disease to look at flow limitation. So great suggestion. Thanks.
A quick question, David. So I guess any sense of why the kidney doesn't kick in to retain more salt and bring the preload up, and what would be the difference in someone who's extremely deconditioned?
Right. So in deconditioning, the major hit with the Fick principle is to cardiac output, which in turn is LV/EDV. And that's been shown by many groups, both invasively and non-invasively. So this extraction problem in high flow is not a feature of deconditioning. The other question, Walter, was, the kidney. Yeah, so much of what we're describing, of course, is acute exercise. We know in POTS there's a hypovolemic form. Maybe there is an issue there, and there's a neurogenic form. I think we've got a lot of that at least half the time. So great question. Thank you so much.
Thanks so much for Dr. Sistrom for presenting such fascinating data. Next up, we will hear from Dr. Betsy Keller from Ithaca College, also on her work looking at exertion intolerance in ME/CFS.
Thank you. It's a pleasure to be here. I'm very excited to share this information with you, and I'd just like to say what Dr. Sistrom just said. Are there any questions? Because he pretty much just put a more specific period on the sentence that I'm going to write here with this presentation. I'd like to begin by thanking first the 200+ patients I've tested over the years using the 2-day cardiopulmonary exercise test protocol. Without that information that we've gleaned from those patients and their willingness to do this, I don't think Cornell University and Ithaca College would have this collaborative research grant right now, because they have helped us to get there. I'd also like to thank my co-author, Joe O'Hare, who frantically put together a couple of slides for me regarding some physical activity data that we have just collected. It is an extremely preliminary, so no judgment there. And I'd also like to thank Kristen Treat, who basically is my lab and clinic partner and does all the testing with me as well. So my alternative title for this, which was a bit long to put in the program, was a math problem. And I thought at 4:30 you can either do your 7th inning stretch, or you can give a little cognitive challenge here and try to solve my math problem and focus. It basically serves as my presentation outline, because what I'd like to do is focus not on everything in the math problem here, but on 4 of the constituents of this math problem, and see if you guys can solve the problem. And maybe a few of you already have solved it by reading the math problem, but we're gonna kind of wade through this in the next few minutes, and I'm gonna move quickly because I have more slides than minutes. But I need to begin by starting a little bit of an explanation about the relationships, very simple relationship that we know all very well in exercise science and exercise physiology, between heart rate and workload, or heart rate and oxygen consumption. It's a linear relationship that we're all very familiar with, and we've used that many, many times to predict what maximum oxygen consumption might be in an individual when we just do a submaximum effort test and collect heart rate. And with this relationship, we can simply, I'm going to see if I can, no, that's not it. I'm getting a pointer here. Okay, so with this relationship, we can actually do a submaximum effort test, collect heart rate during that test, and before they hit maximum effort, well before they hit maximum effort. Typically, this test ends around 70 or 75% of their maximum effort, but yet extrapolate that heart rate relationship, because it's linear, up to where their maximum oxygen consumption or workload would be. And so that allows us to do an exercise test on an individual and then predict what their maximum values would be, so to speak. And this is well established, it's well validated. The interclass correlation for this relationship is quite high, and it's been used for decades in our field to do just that, predict from submaximum effort what maximum values would be. And we've used it with studies of ME/CFS patients over the years, and you can see here we've got several studies where we've looked at physiological responses to exercise, cytokine responses to exertional stressors, brain imaging, and we've measured patients during these tests submaximally and predicted what their maximum effort might be or their maximum heart rate might be. And so during these tests, these patients were compared to controls by having them exercise at 70% of their age predicted maximum effort. The problem is that what we have found over testing many of these patients, particularly with the 2-day protocol, is that oftentimes the exertional stressor alone provokes what we call chronotropic incompetence. And chronotropic incompetence is seen more commonly in heart patients. And in essence, basically, the heart rate, these patients are unable to drive their heart rate up to the levels that we would expect of them during incremental exercise and up to maximum effort. And so when we started seeing this in ME patients on a pretty regular basis, we were concerned because we know that some of the studies out there have made some conclusions based on matching patients with controls using submaximal data. When we started doing this 2-day CPET protocol, or cardiopulmonary exercise test protocol, where we do an exercise test, we measure their baseline oxygen consumption, we get their anaerobic threshold, we get hemodynamic information during incremental exercise, ventilatory data, everything that Dr. Systrom gets except for the stuff that you get by sticking those needles in your patients. And we also provoke post-exertional malaise. And when they come back on the second day, we measure them again to compare whether or not their oxygen consumption at peak effort changed and whether that altered their anaerobic threshold and the other pieces of information that we can look at. And when we look at ME/CFS patients compared to controls, so this is now 99 ME/CFS patients compared to 20 controls, we see that their oxygen consumption on day 1 for the controls is very similar from day 1 to day 2, and there is a little bit more than an 8% drop-off in this particular population of patients from day 1 to day 2. When we plotted heart rate against oxygen consumption in the controls, we saw what I showed you in the very first graph, a very nice spread of data that we expected where heart rate increased incrementally with oxygen consumption. And when we looked at the ME/CFS patients, we saw somewhat of a nice linear relationship, but we also saw this clustering of heart rate down in low levels of heart rate values. So we had far fewer ME/CFS patients who were able to drive their heart rate up over 150 beats per minute. So we looked at the ability of our control patients to meet what we would predict to be their maximum heart rate during test 1 and test 2, when we found that of our 20 controls, they were able to achieve age-predicted maximum heart rate. Here's their observed heart rate. Here's their age-predicted maximum heart rate. And also, again, do that on day 2. In contrast, what we saw with the ME patients is on day 1, this was their observed heart rate during the exercise test. This is what we would have predicted them to achieve based on their age. And on day 2, it was a little bit worse. They were less able to drive their heart rate up and even further from age-predicted maximum heart rate. And so ultimately, what we found in this population was that about 95% of the control patients were able to achieve heart rates at maximum effort over 150, whereas only about 66% of the patients were able to do that. And when we brought them back on day 2, all of the controls achieved maximum heart rates over 150, and fewer, only 60% of the ME patients were able to drive their heart rates up. So in comparison, let's go the other way. When we looked at just the ME patients here now, the 99 ME patients, their age predicted, 70% of their age predicted maximum heart rate, which is typically used when we read these studies where they've done sub-maximum heart rate prediction to match workloads between MEs and controls. For this population, that would have been around 124 beats per minute. In reality, for this population, their age-predicted maximum heart rate was 177. On test 1, they achieved 158, and on test 2, they achieved 153. When we looked at 70% of the actual heart rate that they achieved, it was 110 beats per minute on test 1, whereas they were predicted to have been at 124 beats per minute. When we looked at their actual 70% heart rate during test 2. It was even lower at 107 beats per minute, yet from their age prediction, we would expect them to be at 124 beats per minute. So in reality, these patients on test 1, if we were assuming they were at 70% of their age predicted maximum heart rate, in reality they were at 80%. And on test 2, they were at or over 100% of their maximum effort while thinking that they were only at 70% of their maximum effort. So the Workwell group actually has some unpublished data in 179 patients where they've shown this as well. And so it's quite common in this population. And if we think that our predictions are accurate in terms of using submaximal data to predict where our patients should be exercising, we should really be concerned about that, because what we're finding from this analysis here is that they're actually exercising at a much higher percentage of effort than we would assume they would be at. So low exertional heart rate is something that we're seeing quite commonly in this patient population, and is one piece of the profile that we see all the time in these 2-day cardiopulmonary exercise test results. The next thing that we tend to see in these patients is ventilatory issues. So here I just selected one of the patients we studied recently, because this is a pretty good example of what we see quite commonly in this population. And this is a 39-year-old female who performed the 2-day cardiopulmonary exercise test protocol. Now, she actually repeated her data quite nicely. Her VO2 peak was a little over 10 milliliters per kilogram of oxygen per minute, which was 38% of what we predicted for her age and sex. And she produced that again on day 2. Her maximum heart rate was 120, which was 66% of predicted for her age. And on day 2 was 122. Her ventilatory anaerobic threshold she repeated as well, just so you know that anaerobic threshold is akin to about sitting in a chair at a desk. That's her level of effort when she gets anaerobic, or increasingly anaerobic. And that occurred at a heart rate on day 1 of 84 beats per minute. However, on day 2, her heart rate at anaerobic threshold decreased to 77 beats per minute. So looking at this, you might say, well, this is an ME patient, and did she really work hard? Was she a slacker? I mean, nothing changed from day 1 to day 2. She actually kind of looks like our control subjects. However, these numbers are very, very low. And in reality, she worked very hard for us. When we looked at her respiratory exchange ratio, we see that she achieved respiratory exchange ratios, which are an index of how hard somebody's working. It's one of the pieces of information we look at during these exercise tests. And her respiratory exchange ratio was over 1.1, which is what we would like to see as evidence that they worked very hard. On day 2, it was even higher, 1.21. Her perception of effort during the exercise test, or RPE, rating of perceived exertion, was 19 on day 1 and 18 on day 2. That's out of a scale of 20, where 20 is the absolute maximum effort one could exert. She was obviously working very, very hard. And signs and symptoms at the end of both exercise tests, especially after exercise test 2, was extremely lightheaded and overall exacerbation of her generalized pain. And when we look at her ventilation values, what we see is that during both tests, her maximum ventilation value at peak exercise was 22% of what would be predicted for age and sex. So her ability to drive up her ventilation to eliminate carbon dioxide was extremely limited. Her ventilatory equivalent of carbon dioxide was over, the slope of that ventilatory equivalent was over 40. Normal for her age and sex would be about 25. So indeed, she was not very effective at blowing off carbon dioxide during this exercise test. So we see low exertional ventilation in this population quite commonly as well. What was also interesting with this particular patient, and also unfortunately not uncommon, was that her systolic blood pressure during test 1, low to start with. I think we'd all agree that at seated rest, she is hypotensive with a systolic pressure of only 97. Now, a normal, quote unquote, normal systolic blood pressure response to incremental exercise is that systolic pressure should increase about 10 millimeters of mercury for every 1 MET level increase in work. Well, that's a lot of gibberish, but basically what that means is that this number should go up about 10 millimeters of mercury from seated rest to 30 watts of exercise, which she did. And then from 30 to 60 watts, it should go up another 10, which she did, okay? And this is all I have because she hit her max value after that. She maxed out. She couldn't continue the test at 60 watts. When we brought her back on day 2, as you can see, still hypotensive, yet she couldn't drive her systolic pressure up at all. And in fact, it actually went down very slightly. So she had a very attenuated blood pressure response during exercise throughout the entire exercise test. No effective increase in the driving pressure of blood leaving the heart to the peripheral vasculature. And I'll draw your attention to systolic blood pressure during recovery here on day 2. It also was quite low. But again, where is it going to go? After minute 1 of exercise here, we lie the patient down, raise their legs, and we were able to get the blood pressure up a little bit. It's not uncommon for us to get the highest blood pressure of the day, including exercise, after they're done exercising, when we lie them down and elevate their legs. That is when we may see the highest blood pressure, including all of their exercise blood pressures. Not unusual in this population. So low exertional blood pressure, another common finding in this patient population. So let me talk to you for just a couple of minutes about some activity data that we've been collecting as part of the collaborative research study that we're doing at Cornell University. We are using what's called an actigraph accelerometer. It's a triaxial accelerometer that can be positioned on the wrist. It can be put on the waist or on the thigh. And because we knew we wanted to measure for a prolonged period of time, we wanted to measure 10 days before exercise, which is what we're doing, and then 10 days following the 2-day cardiopulmonary exercise test. We first opted for a means of data collection that would be most adhered to by our patient population, which is why we went with the wristwatch device. They're waterproof. You can't go scuba diving with them, but you can wear them in the shower. You don't need to take them off for anything. And most of the patients have adhered very nicely to wearing this device throughout the entire 10 days before we bring them in for the exercise test. There's a lot of data you can get off of these devices. These are research devices. The way we have it programmed is that there are no lights or sounds or numbers or anything that appear on the watch. We don't want to encourage the users to interact with the watch in any way. So there's nothing that shows up. We program the watch to turn on a specific time and date after they've received it in the mail, and then we program it to turn off as well. And again, there's a lot of information, and I'm just showing you, and again, read my lips, very preliminary data that I'm just showing you, mostly because I wanted to sort of emphasize some of the issues that we are experiencing early on with this means of collecting accelerometry data. And so what I'm going to show you next, that very preliminary data, is some of the activity data from these patients. The blue would be our CFS patients, and the orange, or whatever color it appears up on the screen there, are our controls. And I'm not showing you this to have you start thinking about, geez, nothing's happening after exercise here for these ME patients, because it is. But more to the point, I want to illustrate some of the problems that we're starting to see with the wrist-worn device. And I know some of you are interested in gathering accelerometry data on patients before and after exertion. And so this is just some information that I think is important for you to be aware of. So these data here are unfiltered data. So when you set this accelerometer up, the default is the default is for what's called a low frequency filter to automatically be on. And what we decided we wanted to do was take the low frequency filter off, which we did because we wanted to capture low frequency movement since we're measuring a low active population. And here, this is activity counts, which are arbitrary units, but you can see we have very high numbers here. You probably shouldn't think of these as steps because they're not, but this could get you a lot of counts, okay? So without filtering out the low frequency movements, we captured everything here, and you can see we have quite high numbers. When we filtered the low frequency movements, the absolute values of these counts for both patients and controls decreased quite significantly, and you can see that the patients before their exercise test, on average, were lower active than the controls. I didn't show you their VO2 max data, but I can tell you that these 7 controls have a lower average VO2 max than the 7 patients. So we have a very low active group here. But the data is actually is quite messy and of some concern, because what I think is playing a role in some of the messiness that we're seeing is not whether or not this device is validated for low active individuals. It is, but you want to make sure you selected a research device that is validated to use on low active individuals. But with the wrist-worn device, we're actually seeing the influence of a population that spends a lot of time on keyboards or devices. And so we're getting a lot of wrist movement that is probably influencing some of these values. So something to think about. If I had my druthers, I'd love to see this worn on the waist or the thigh. Honestly, I didn't think we would get 10 days of adherence on the waist or the thigh, but it's something for you to think about if you're going to measure for a shorter period of time. But they have been very adherent wearing it on the wrist. And with this device, you can actually get physiological correlate. Well, you can get heart rate, but that requires the patient or the subject to wear the polar heart rate strap on their chest. Not going to do it for 10 days. It's not going to happen. So we're not getting heart rate data, which I would love to have in conjunction with this activity data, but unfortunately, we knew that wasn't going to work well. But it is an option with this device. So back to my alternative title here. We looked at low exertional heart rate or chronotropic incompetence, low exertional ventilation. We see quite often in many of these patients. Low exertional blood pressure, also very common finding. And I might add that in both cases, in all cases, heart rate, ventilation, and blood pressure, we may not see this on day 1, but when we bring them back on day 2, unlike the patient I showed you, we provoke these responses. So they may appear as just a normal, low-fit individual with normal physiological responses to exercise on day 1, but after the exertional trigger, they come back and show this to us. Or we may see this on day 1 and day 2, like you just saw with the patient I showed. And exertion intolerance, pretty much across the board. So in summary, I would like to just point out that chronotropic incompetence is something we see often in this patient population, not 100% of the time, but very, very, very often. And it needs to be taken into consideration, especially if you're considering doing a submaximal effort test to use data to predict any maximal effort indices on these patients or predict a workload for them. And that we commonly see abnormal exertional responses in heart rate, ventilation, blood pressure, and exertion intolerance. My own personal preference is to relate this to a blood flow issue Thank you, all of the speakers who have previously implicated that. While we have not measured it, we also always measure pulse oximetry, and we have normal pulse oximetries in these patients, and yet we have these abnormal physiological responses outside of that. So any guesses as to what I think this formula is telling us? Anyone? Okay, to me, this smacks of autonomic dysfunction. When we look at all of the symptoms that we see in these patients over and over and over again, I have to look at autonomic dysfunction as a sort of the common denominator in what they're telling us with their exercise responses, their patient medical history, their family history, et cetera, et cetera. We see this all the time. And the interesting thing about exercise testing these patients is the heterogeneity that you see at rest in this patient population all of a sudden shrinks to show us these abnormal responses over and over and over again. So my picture of an ME/CFS patient is this, in contrast to the huge diversity that we see when we collect all of their other data. And I want to finish by just mentioning a couple of studies that have been done recently and previously, or reported recently and previously. And one is reported only a mere 30 years ago, Cardiac Function at Rest by Montague and colleagues. And this graph should now look familiar to you. Heart rate data during incremental exercise, normal healthy people, ME/CFS patients, chronotropic incompetence. And Montague concluded that, in summary, the results of the study indicate that patients with chronic fatigue syndrome have normal resting cardiac function, but a marked limitation of exercise capability. We weren't doing ICPETs at this point, of course. And went on to say that although inconclusive, the data are compatible with latent viral effects on cardiac pacemaker cells or their autonomic control, skeletal muscle that are unmasked by the stress of exercise. Further studies required to delineate more precisely the pathophysiology and etiology of this not uncommon and disabling syndrome. 30 years ago, not uncommon. Lily Chu and colleagues at Stanford just published a nice epidemiological overview that I concur with 100%, having taken histories on 200 of these patients. I would have to agree that when we look at the overall response, human stress response, autonomic nervous system response, and autoimmune histories that these patients have, that they have done a very nice job in characterizing in that article that just came out. In terms of future directions, I think, of course, we're all going to continue to look at what might explain the etiology of this disease and search for that elusive biomarker. And now you'll hear my own personal bias, because I think at this point we need to continue doing that, but we also need to, and the patients deserve, that we focus on management of this disease and helping patients to mitigate the symptoms that they experience and we're so busy studying. So I would urge you to pay attention, clinicians, to the relevance of the low normal patient, the blood results that don't really go outside of those high and low markers, but they're consistently low or they're consistently high, when they also accompany an individual who is reporting all of these symptoms that we now know comprise ME/CFS. And I'll be maybe the sixth person today, and this really does my heart good to be able to say this, the sixth person today to encourage a much more individualized, precise, nutritionally guided approach that's based on the underlying genetic vulnerabilities we see in these patients, life stressors and events that contribute to who they are now. In other words, their epigenetic influences that have made them what they are today with this illness, as we think about how we want to help manage the symptoms that they experience. Thank you. I can take a few questions. As long because they're not hard.
I was wondering if you could comment about how your patient population differs from patients that have more typical symptoms of POTS with exercise-related tachycardia, and what do you think the relationship there is?
You know, it's interesting, and I can't. We have certainly tested patients with POTS, and when we exercise stress them, it's not unusual for us to see. Oh, I'm not doing that, right? Okay. It's not unusual for us to see their blood pressure sort of snap into line with what I showed you today. And the heart rate variability that they experience at rest attenuates, actually. So I've seen that, and not in a data set that I can report to you, but I can tell you that we have tested quite a few POTS patients who are diagnosed with POTS, and we actually see exercise in some weird respect kind of normalize their cardiovascular response. However, their exercise capacity is overall attenuated.
Thank you. Joe John, Charleston, South Carolina. You know, in the office, we have so many things to face. So these issues of autonomic dysfunction raise the issue of, you know, where in our set of priorities do we put them? In view of the fact mentioned earlier also that exercise testing itself may induce post-exercise malaise itself, and we may not want to subject our patients to this. Can we substitute Fitbits and their mobile devices into determining that they are unable to increase their heart rates, they have autonomic dysfunction, focus on that, give them that diagnosis, maybe ask for help from cardiology or pulmonology consultants, and move ahead that way? The underlying question is, how often are clinicians doing exercise testing in these patients, and where would you estimate its value now?
Well, I think that's a good question, but I thought where you were going with that was what, as a clinician, can I do to provide guidance without a lot of fancy tests and exerting tests? But so often my disclosure is that I do these tests most often, because patients seek me out to do it because they need objective evidence of impairment. And I pretty much every time I present, I usually start out by saying I look forward to the day where I never have to do an exercise test on an ME/CFS patient again. But their reality is that their financial means will be cut off if they don't provide some objective evidence. So people, you need to give them objective evidence without us having to exercise them. In terms of exercise guidance for them, however, what I tell them, if I have not exercise test them, is I have some guidelines that I'd be happy to share with you, but in general, to wear the Fitbit or the other device, realizing that if they actually do know their heart rate at anaerobic threshold, which is what I use to provide an exercise prescription for them, if they do know that, to be aware that the Fitbit may not be as accurate as the ECG I had on them during the exercise test. And if they find that they're adhering to my heart rate at anaerobic threshold guideline and they're still experiencing post-exertional malaise, that they need to downregulate their heart rate guideline. If you don't have that information and you don't want to exercise test somebody, then what I would tell them is to live at a level and keep a journal such that later that day or the next day, if they're experiencing any post-exertional symptoms, then they need to downregulate to the point where they don't experience post-exertional symptoms, recognizing that post-exertional symptoms can be brought about by physical, emotional, and cognitive stressors. And so they need to do a little record keeping and say, what I did yesterday really trashed me today. I can't do that. I've got to lay lower, or I've got to take more frequent breaks. Short exertion, 3 to 4 times that amount of exertion time as rest. Does that help? Yeah.
There's some time. We'll have
Yes.
to end there with the last. Sorry, everyone. Sorry to cut off this excellent discussion, but in the interest of keeping on time, that off to the last question. But hopefully anyone else that still has questions, we can continue the discussion in the Q&A session in a moment. And thank you so much, Dr. Keller, for another excellent talk. And next up, we will hear from Dr. Alain Moreau about his work looking at the role of circulating microRNAs in ME/CFS pathogenesis. So please join me in welcoming Dr. Moreau.
Thank you very much, Andrew, for your kind presentation. I would like to thank Joe Breen and Vicky Whitmore for their kind invitation to present today our unpublished data. So you will see probably this is the first time today that you will hear about circulating microRNA. So this is another type of beast that a bit special but very powerful. So I hope to convince you about their clinical utility at some point. So here are my disclosures. So I thank the CBLIC Foundation for their support, and also the Canadian Institute of Health Research for the Planning and Dissemination grant that allowed us to organize last year the very first collaborative research conference in Montreal. So I would like to talk to you today about some current challenges. So I decided to start with the challenges because you will see where I'm going. I will introduce you to the Quebec ME/CFS cohort, which is actually the largest ME/CFS cohort in Canada, and also our, I would say, unique approach to profile ME/CFS patient using circulating microRNA, and where this can lead us. And I will finalize with the next step. So what do we know and not know about the etiology of ME/CFS? I would say a lot of things on both issues. So, and this cartoon really illustrates not only ME/CFS, but probably most chronic diseases. So it's clear that there is a predisposition of some initiation genes that will increase the sensitivity toward different environmental factors. It could be viruses, bacterial infections, but could be also some hyperchemical sensitivities that will trigger a disease onset. For a few of the patients, they may have a partial or complete remission, but most of them will continue, unfortunately, so that I'm referring here as a disease progression. And this had the complexity of to identify biomarker for ME/CFS because in the real life, there is no pure entity called ME/CFS. There will be ME/CFS with other comorbidities that will add the noise to identify biomarkers. So this is in the real life, and I think if we do research, we need to develop pragmatic assays that will adapt our findings on the way that we search for biomarkers to this real life and to be more pragmatic. And of course, we can also look for disease modifier or progression of genes and other factors that will further exacerbate the condition of some patients that will bring to a severely affected ME/CFS individual. So the first challenge, of course, and I think the topic has been well discussed so far, is the clinical heterogeneity of ME/CFS, how to select and compare. So you may have different type of apples, different type of colors, but some can disguise even try to disguise the apple with some other another fruit. So it's maybe more complicated. And past, present, and eventually future clinical definition will benefit of the progression or the development of more objective biomarker. One problem also is the fact that often we used to work with small cohorts with different ethnic background, and of course, different omic approach are very powerful methods, but they are very expensive too. So we need to adapt and combine those data, and also pay attention to increase the size of the cohort and to define are we looking for severely ill patients versus early stage patients, because in both cases we might learn a lot of data that we are missing right now. And of course, the presence of comorbidity, influence of sex hormone, and aging will add to the difficulties to really define clinically useful biomarker. Plus the fact that the disease is triggered by different factors, so it's sometimes difficult to understand or to capture at the earliest as possible the cause and the response of the host of those factors. So one of the challenges is to all with this genome or omics era is to how we integrate all those data together. So unfortunately, it's difficult to allow patients to visit our labs or clinics, and we pass through them to the different battery of tests that we have a more complete pictures, but we can send samples, and samples can travel relatively easily. Data can certainly travel, and we need to work together at some points to have a better integration of those data, because we can miss some opportunities to discover key findings. So at the end of the day, we will end up with what I'm referring here as a molecular signature. And are we talking about molecular signature to define the risk to develop ME/CFS or to develop a severe form of ME/CFS or some symptoms? So we need to work together, because we will continue to discover during the last 10, 20 years genes, variants, different factors that will be involved and highly associated with ME/CFS, but we need to find actionable therapeutic targets. So this is, I think, the most important thing. Something that can be not just a biomarker, but a clinically useful biomarker, and eventually some of them could be also actionable therapeutic targets. So we put forward, as many of my colleagues, different hypotheses, and we agree that ME/CFS will involve immune function, energy metabolism, and physiological stresses, but we think that one key factor could be the microRNA, which are non-coding small RNA that can bridge genetic predisposition and environmental factors and the phenotypic differences that we observe in ME/CFS. So our primary objective of this research program is to identify circulating microRNA linked to the disease, allowing us to better stage or stratify patients and symptoms across cohorts. And eventually that will lead us to better understand the etiology, determine the molecular, epigenetic, and genetic mechanism associated with the disease, with the ultimate goals to find actionable therapeutic targets. So this is a cartoon that shows you how powerful are microRNA. So microRNA you can detect them in many biofluids, including the blood, of course, and they used to attach to the messenger RNA in the 3' UTR, and doing this association or attachment, they will block the protein translation by creating a duplex that is very stable. And unfortunately, one single microRNA can target up to 200 different genes, and one gene could be a target of more than one single microRNA. So very small molecules, but very powerful, and they are involved now in molecular medicine in different diseases. So to really go and capture the most relevant circulating microRNA, we decided to develop a non-invasive method, or the least invasive method, so using blood. And we developed a test that can reproduce post-exertional malaise. So that was a question that many patients debate and honestly guide me to, if we need to develop a test, can we develop something that can reproduce one of the cardinal symptoms of the disease? So we developed a portable machine, which is machines that provide a therapeutic massage, which is authorized by Health Canada. So this is a machine that normally are not creating any stresses, but on ME/CFS patient, this machine during 90-minute stimulation will create enough stress that will reproduce on a safely manner post-exertional malaise, and I will show you some data about that. So we are taking blood tests before the stimulation and every 30 minutes. And you can see here a diagram that shows during the test, and this is a very recent results. We use a smart vest called Exoskin that allow to measure different physiological parameters, including heart rate variation. So you see heart rate variation during the stress test, and in orange, this is the patients, and in blue, the LT subject. And this very first pilot trial with the Exoskin smart vest, we tested identical twins discordant for ME/CFS, so which allowed us to test our system if it was doable to do it. So this machine is an inflatable cuff that give a very gentle massage. So it's not like a cuff that takes you blood pressure, okay? We're talking about 0 to 4 PSI. The machine that gives you the blood pressure is 30 PSI, that crunch your artery. So very different. And this is a machine that's been vetted as safe by Health Canada. So this is the typical demographic and clinical data of a Quebec cohort. So we are testing females and males. We are using the same technology with controls, which is a bit demanding because we're asking people to spend 2 hours with us. And more than 85% of our patients are severely ill, so they are homebound. So we are sending clinical nurse at home. And this is the reason to have a portable machine. So the machine is relatively cheap, easy to have an access, and we can test and retest. So, and of course, we are using the traditional standardized questionnaires to evaluate their health status. So in the first part, we use, in our discovery cohort, so we use few patients to determine the most relevant circulating microRNA using the plasma of the patient. So we use the microRNA array Agilent. So we probe over 2,500 mature microRNA, and we end up with 32 differentially expressed, and so far 12 of them have been validated to a large cohort, which is something very important. So this cartoon illustrate the process to do the validation, and of course, because it's very difficult to normalize microRNA, so we spike in with artificial microRNA from cell ligands, so to make sure that we have something relevant to mention, because I'm not really believing that we can use other endogenous microRNA to do that, because most of them can auto-regulate themselves, so it could be difficult to do that. And the fact that we can use quantitative PCR, this is a tool that can use in any diagnostic lab. So this is, again, a pragmatic approach that if we need to eventually bring on the market a test that can stratify patients, let's use common tools that can be easily be applicable in all clinical labs, private cabinet, or even in the hospital-based setting. I will show you some examples to demonstrate that we have been, I would say, quite successful so far. So we identified the MIR 127-3P, which is highly expressed, has been discovered before in ME/CFS Australian cohort. So we replicate in the Quebec population, and we confirm the relevance of this circulating microRNA. And this is what you can see at baseline on the A panel and also after stimulation during 90 minutes. Interestingly enough, this microRNA and the B panel show you ingenuity pathway analysis. So we can identify known and predicted target of this microRNA, and this one indirectly will regulate interleukin-10 through a regulation of BCL6, which is a negative regulator of interleukin-10, and this interleukin is upregulated in cerebrospinal fluid of ME/CFS patients. As you can see, it's also involved through interleukin-10 in the regulation and development of different regulatory of T lymphocytes, so which is something relevant also for ME/CFS. Another example, and this is probably would be very provocative, so I'm the provocation part, but I think I can be provocative as well. So for the MIR 145P, because this one is targeting a membranous receptor called CD20, which is the target of rituximab. So of course, if you have an elevation of this microRNA, you will downregulate CD20, which will reduce the response to rituximab. So one thing is, so far I just present you the data about ME versus control, but at unstimulated or after stimulation. But if I show you the next cartoon, you see the results. So the blue bar is unstimulated at baseline, and the purple one is the one stimulated. So you see we have different type of response. We have, for instance, for the first patient, we have a very low expression of this circulating microRNA, while some other patients, like patient number 34, with a very strong fourfold expression at baseline, but a drastic reduction after the stimulation. And we have also the opposites for the patient 85, who have low baseline expression and very strong expression. So if you took all the patients that overexpressed with or without an effort, so 2/3 of them are predicted to be non-responder toward rituximab, which bring us about 1/3 of patients could respond to rituximab, which is what has been shown so far. So again, stratification must be also not just include and pool all the patients together because they are not similar. Another microRNA, the MIR-10505P. I'm sorry for the name. There's always MIR something with a number. So this one is specifically upregulated after stimulation. And we saw that the higher expressors, so the patients that express very high level of this microRNA, are the ones that present a better mental fatigue score. So as you can see on the B side, as compared to high or normal expressor. And we were very excited about, wow, we have something that improves health. So at least on the mental fatigue aspect. So, and through the Ingenuity pathway analysis, we discovered that this microRNA targeting SLC682, which is a multipass membrane protein that is responsible for the reuptake of norepinephrine. And we also rediscovered a study by Arnold et al. That they tried the drug duloxetine in a clinical trial because this is a known SLC682 inhibitor, and they end up with a different cohort, of course, and using the same tool, the MEF20 questionnaire, that indeed the drug targeting the very same gene improved mental fatigue. So 2 different approaches targeting the same gene in different cohorts end up with the same conclusion. So again, for us and for the research community, that should be accepted as a kind of replication of past results. This MIR, the MIR-374B5P, is very intriguing because it has been shown as a very low expression in fibromyalgic patients and is inversely correlated with pain threshold. And we saw the opposite in ME/CFS. We are going completely in the other spectrum. We did our own testing in fibromyalgic patients in Quebec using the Carthagène Biobank available to us, and we confirmed that indeed in fibromyalgia patients we have a very, very low expression, but we have a stronger expression in ME/CFS compared to age and sex match control. This microRNA, and again this is a cartoon with EPA analysis, is targeting many interesting genes that are involved in ME/CFS. And I will give you a few examples. So we talk about celiac disease, we talk about the transport of vitamin E. So as you know, vitamin E or alpha-tocopherol are downregulated in ME/CFS patients. It's involved also in the regulation of some genes that involves in mitochondrial disorder, cognitive impairment, anxiety, secretion of dopamine. So now, for the very first time, whatever is your favorite genes or mechanism, we can correlate them or relate them to circulating microRNA. And this is only one. We have 32 like that. So we probably be on the right path, and we need to figure out. So if you see one of your favorite genes in those lists, please come to see me. We are open to collaboration. The last 2 microRNA are very intriguing because they are associated with endurance athlete. So endurance athlete possess the higher whole blood level of this MIR-186-5P compared to LT control. And again, under stimulation, I create post-exertional malaise. So I'm stimulated like I'm doing exercise or forcing patients. But the patients are sitting in a chair, relaxing, receiving a massage. But they are already showing like they are running a marathon, but they are doing nothing. So again, their system is overreacting and mimicking the net result of someone doing a very powerful exercise. So this is, again, very interesting because if you look in the panel B, this MIR is controlling, again, many genes involved in mitochondrial disorder, EGE response, which I think could be relevant for some patients, the transport of some metals like magnesium, cobalt, and copper, which could be important for many metabolic function. So again, this is very interesting. If not, this microRNA is also triggered by exposure to mercury. So again, you can reach Roma by different roads. Okay, so we need to pay attention that you may trigger something. Here, in that case, because baseline are relatively low, I don't think those patients being exposed to mercury. But in other occasions, patient may be overexposed to mercury, and overdosing or chronic exposure to mercury may leads to the same phenomenon. Okay, so we need to keep that in mind. Another one, and don't worry, I won't go through the 32 because that would be too long, but just again to show you another microRNA associated with endurance athlete. So again, this one is only showing up when we stimulate, so we are stressing the subject, and this one is involved in different aspects. So some of your favorite cytokine, the trafficking of T lymphocyte, riboflavin transport, regulating of sleep, which is, I think, very relevant, as well activation of B lymphocyte, export of acetylcarnitine. So whatever is your favorite gene, I think we can figure out something that we can establish some collaboration. Why those microRNA? How can we use them? So we can use them to have a different stratification. So the blue and orange color here mean a different response between the stimulation after 90 minutes and at baseline. And as you can see, you don't need to see the number, but just showing the colors, you see that we can classify or stratify the patient in 5 subgroups. Those subgroups that are associated with different comorbidities. And you see sore throats are increasing over time, especially in subgroup 4. And we have different symptoms. So for us, it would be very interesting to identify other predisposition factors that are associated with some symptoms associated with ME/CFS. Also, as the symptom reported after the stress test, those patients behave differently, especially subgroup number 5, where we have mental fogginess, vertigo, dizziness. So different behavior, different type of response using our 9 microRNA so far that we use as a selection panel. And I will show you how powerful this classification is so far. So for instance, we can use about different delay activities. So the lowest one is in group 1, the highest one is group 5. You can check for general fatigue, mental health, using the DSU cognitive. So there's a significant difference in some subgroups. In terms of, we reanalyze all of our biochemical data using those patients, and we observe, especially by comparing the group 4, the one that's showing the less symptoms, as opposed to the group 5 that present, the only one present mental fogginess, vertigo, dizziness, which is very specific for this subgroup of patients. And we look about a well-known molecule called thrombospondin 1, which is an anti-angiogenic factor. And you see the drastic elevation of thrombospondin 1 as opposed to group 4 going in the opposite direction. And we think that in that group, the effort, the stress that we impose to the patients induce a vasoconstriction in these patients. So we are following that because if it's proven, we can eventually figure out the way to block this effect using inhibitor for CD36 or CD47 or one specific integrin. So they have 3 receptors to target. So knowing this new molecular stratification can open the door to more specific therapeutic approaches, knowing that we are now entering in the era of precision medicine for ME/CFS using this new stratification eventually. So just to finalize quickly, we play around with the plasma, and this is that I'm referring this experiment. This is a brand new experiment, a Ron Davis-like experiment using cellular electroscopy assay, bioimpedance, where we apply the plasma and we look if the plasma itself can trigger abnormal response. In that case, we use a cell line, jerk-cut cell line, which are immortalized T lymphocyte. And you see in this panel that when we use control plasma, we have not much change. Same if you use plasma from idiopathic scoliosis patients. But when we use ME/CFS, we have a nice dose response. So we tested, and this is, of course, N-1 experiment by picking up patients from each of these functional subgroup that we developed with the microRNA. And you see there's 2 that are above control in black, and they have 3 below. So we don't know yet what we are what is really responding, but it's quite unlikely that would be antibodies or autoantibodies, because when we apply the stress, so the stimulated plasma give us a different response. And it's impossible that the antibodies are disappearing after 90 minutes of stimulation. So this opened the door to use this platform to screen for eventually possible therapeutic compound when we will know what we are doing. But again, that replicate in part what Dr. Davis have been previously shown, that there is something in the plasma, and we fully agree with this comment. We did the same thing with twins, identical twins, and as you can see, we worked so far with concordant and discordant twins, and we saw a difference between the identical twins based on questionnaire and, whoops, sorry. So, and you can see, although they are identical, they are not part of the same microRNA subgroup. So, which explain also the difference in terms of symptoms, which make a lot of sense. With the concordant twin using the exoskin, you see the change before, so pre-test and after the test. So it's hard to say that we really changed something on the heart rate variation, but we observed that a strong decrease in the post-stress compared to the pre-test in the REM sleep time. So we don't know yet what it is, but we presume that this is really induced by the post-exertional malaise that we apply to the patient using our stress test. So what are the next steps is, of course, we need to perform more validation. We will be happy to collaborate with all of you to test your own patients and to provide our samples that if you are interested about metabolomics, proteomics, our samples are available to further complement what we can learn and know. And eventually working together is I think, the only solutions to bring forward and find solutions for ME/CFS. So finally, I would like to acknowledge the participant and the family, because this is a very demanding test. It's not obvious to ask, especially on severely affected patients, even though that they open the door, their home, that we perform the test. We are doing also retest of the patient, and even if they experiment and they know that the test will induce a post-exertional malaise, they are willing to participate. So we never put anyone in the hospital or needs to call 911, but nevertheless, we induce a post-exertional malaise. And I would like to thank the support of the CBLISA Foundation, CHR, a lot of ME/CFS organizations in Canada that support us, also patients across the world, because we are lucky to obtain support from donation as well as participants, and also all my team members and my collaborators. Thank you very much. Okay.
Thanks so much, Dr. Moreau, for another excellent talk. And thanks so much to all of our speakers in this session, which I thought was really fantastic. So another just big thanks to all the speakers. Next up, we will have a group discussion that will be moderated by Terry Wilder. So please join me in welcoming Terry to the stage.
Good afternoon. Is everybody as wiped out as I am? Great. So I just should probably start by saying that I don't think I'm mistaken, but I might be the only person at the podium today who actually is living with ME. So thanks for this opportunity. What we wanted to do in this last half hour was have folks be able to ask any questions or bring up any topic that they wanted to discuss in the larger group. We have half an hour. What I would like to ask is if you are a presenter today and you kind of are in the far back, if you want to kind of come up to the front in case someone comes up to the mic and asks a question that's related to your presentation. That way we can make sure that we're able to get the mic to you quickly. So we're going to open it up, and if we can just be respectful of the time in case there's a lot of people who have questions or want to bring something up. So if you want to go ahead and line up at the mic. Yes.
I'm wondering how often collagen vascular diseases or connective tissue disorders might underpin some of the pathology you all see in your research, if that's even looked at.
So can you tell us who your question is directed
Well,
to?
initially I was going to ask it of two presenters ago. I apologize, I can't remember her name, but I'm happy for anyone to answer that.
So our presenters from 2 times ago.
Dr. Keller, maybe?
Dr. Keller. So if Dr. Keller wants to come up,
Thank
and
you.
Joe can hand the mic to Dr. Keller.
Hi, thanks for that question. In about 200 patients we've tested, I see it in a significant number of them. I can't give you a percentage, but it's not unusual. And, you know, Ehlers-Danlos, not necessarily, not always in the patient, but in the family history for sure. So it's not unusual. I have tested at least 2 that I can think of off the top of my head who were either before or after our testing diagnosed with small fiber polyneuropathy as well. And so, and in both of those cases, those individuals reproduced their exercise test normally, actually, but very, very low function because of it.
And maybe this is something you're going to get to tomorrow, but what about those who get treated with IVIG? Do you see an improvement globally in your research, or that's not something you can speak to?
I can't answer that because I don't see these people over time.
Okay.
Great.
Thank you.
So I'm going to kind of go back and forth. So the gentleman over here. Oh, sorry.
That's okay.
Okay.
You know, we're low. Get
Yeah.
high.
So I could address
Oh, sorry.
that latter question. So as part of our initial evaluation, we routinely screen for connective tissue disease. Part of it is with an eye toward the small fiber polyneuropathy, knowing that intravenous immunoglobulin is one option if you get a hit, a rheumatologic hit. Sjogren's is the most common of the connective tissue diseases associated with small fiber polyneuropathy, and therefore in our camp when we evaluate NE-CFS, that would be the most common hit. Much more often, though, I think is kind of undifferentiated rheumatologic flavor to the patient. You suspect maybe something's there, the ANA may be middling, that sort of thing, but there's no definitive diagnosis that's more common. Dr. Oaklander tomorrow, she has published on treatment of small fiber polyneuropathy with intravenous immunoglobulin, so I think we'll hear more then.
Great. Over here.
Hi, my name is Colleen Steckel. I've been sick for 29 years. I'm on the lower end of the spectrum, and I'd really like to have, it's been brought up a couple times today about the stratification of the patient community. And so often we run into that those of us at the lower end of the spectrum respond in much different ways to any medication that's tried. For instance, the POTS community. So I'm diagnosed with POTS, and I do that in quotes because the cardiologist that I saw, the EP cardiologist, he said, you have all the symptoms of POTS, but you don't actually have those symptoms as a response to the same thing as a normal POTS person. I don't have pooling in my legs, whether it's the, low blood volume or whatever. So the medication that works for me is Korlanor. But he was very clear that if he tried to give me the normal POTS medications, it would make me feel worse. So that stratification conversation, to me and the people that I talk to all the time, we really want it at a higher level and like top of the conversation in all the research, so that when a research paper comes out and we're reading it, it's the information from that research talks about which symptoms we are dealing with. And we're looking for the more specific symptoms, like, something that you found could explain the paralysis or any of the other more difficult symptoms that the severe community is dealing with. So I guess my question is, Dr. Moreau brought up about stratification. So in that those different stratification groups you had, I think you said that one of those definitely reflected the more severe. And so that's really what my question was.
Can Dr. Morris respond?
So for sure, this is what we are finding. So the next step that would be logical is to do brain oximetry, for instance. So for those that have mental fogginess, dizziness, so by testing first all the patient in this subgroup number 5, because this is the only subgroup that showed that. So again, this can be done with very complex machine in the hospital setting, but can be done also with portable machine. So for us to prove the principle is, let's see that if we can see change in the brain oximetry, but not at the periphery. So we can do that and see with the other subgroup that are not showing mental fogginess, they have no high level of thrombospondin after a stimulation, a stress. They don't have change in their brain oximetry. I'm not saying that there may be other problems with the brain blood flow, but at least we may have the beginning of something to work with. And this is going through what I'm referring to personalized medicine or precision medicine. I think more closer to precision medicine, because by definition, medicine is personalized. Should be, at least.
So is that group 5? I mean, is there a way for a patient like me to look at what you've done and say, yeah, I would be in group 5 by the symptoms, or would I need to go say, can you please do these tests on me to see if I fit group 5?
We would like to offer the test, and as I said, the test is available to any group. So I don't know which group of researcher in your region you are working with.
Okay.
So ask them to have the test.
Okay.
And we will make sure that the methods, the machine will be available.
Awesome.
Great.
Thank you.
So I'm going to go to the gentleman over here, and if we can just try to have our question be succinct, no more than 30 seconds, so we can get through everyone.
Sure. It seemed to me that the animal model, like the organophosphate exposure, was pretty useful for the Gulf War illness, and I haven't really come across many animal models for ME/CFS, so I was just curious for all the speakers whether you think one can be developed and any ideas as to what might be useful.
Do you have a particular speaker that you would like to have jump in?
I guess one thing that I was curious about in Mark Davis's talk is he was looking at these signatures where he identified a couple mycobacterium and the FGF21 and some of those things. So I was wondering if maybe some of those findings could be exploited to induce immune signatures similar to ME/CFS.
Great. Is Dr. Davis still in the room?
Yes.
No?
So I think that animal models are good to initiate or generate hypotheses, but I think we have learned both in the good and the hard way that the immune systems are really quite different. And many things that were predicted in mice that have not been found in humans, and that are essential, for example, toll-like receptors that are receptors for innate immunity that are present in mice that really are not present in humans. So how far we can go in mice, I think we have to be careful, and particularly when it comes to exploring therapies. So I think to initiate something that could generate like a hypothesis in humans may be useful, but we have to really be cautious when it comes to therapies. We can only go far, and I think that actually Ron Davis published a beautiful paper, something like titled like "Mice Are Not Men," and so and we see that over and over. So it would be ideal. It would give us further, but it can lead us really in the wrong direction.
Yes, over here.
Hello. My name is Sydney Brumfield. I'm a clinical researcher at Mass General Hospital up in Boston, and I would like to thank, first off, all of the people who presented today. They were absolutely wonderful talks, but my question revolves around what efforts are being made. This is to all of the speakers. What efforts are being made to diversify the patient population that is typically being researched on, of the people who presented data on the demographics of the patient population. It seemed that mostly the people who were tested were middle-aged Caucasian women, and I feel like that seems very limited in the possible people who we could research. So if anyone would like to go at that answer,
Yeah, thank you for bringing
very much
that up.
appreciate that.
That's a super question, you know, and it's Nancy Klimas, and we're from South Florida, where we have obviously a very large Hispanic population, and happily our demographics reflect that. But we're also VA investigators, and I'll say the VA is a very good place to get a demographically diverse and socioeconomically diverse population for recruitment into studies, and I'd strongly encourage people to look at that, because many of the private practice clinics, you know, I mean, they obviously are either out of reach, some are only cash pay clinics, some are, you know, you have to travel many miles, so catching people that are in the lower socioeconomic classes into any of those groups is highly unlikely. I'd also say that you really get a handle on this when you do big surveys of you know, like CDC national surveys. What's the CDC survey? The one that they do every 5 years. Yeah. I mean, anyway, the point is, if you could do the large population-based surveys, then you get a handle on who you're missing, and we get a better sense of whether or not we should generalize our findings the way that we tend to do. So it's a great point. It's an important point, a point that I think we're all really aware of, and we struggle to try to find ways to better reflect the population. I think I should say that studies by Dr. Jason and by the CDC and the Chicago and Wichita cohort show that we're clearly missing the boat. That the higher risk is in the Hispanic and African American population and in the lower socioeconomic groups. And that's not who we're recruiting from mostly into our studies.
Thank you. Thank you for bringing that up. I really appreciate it. For folks of us who are in the community of living with this disease, we talk about it a lot. So it is definitely a problem, and it needs to be addressed. We know that when we look at research historically, when we see that research is done just on white men, it's problematic, and we have to be thinking the same way with this disease as well. Dr. Mack.
Hello, my name is Dr. Ami Mack. I'm from the Stanford Genome Technology Center. I'm the new Director of Translational Medicine and Patient Relations. My question is, well, first of all, I would like to add that I'm also a person living with ME. So this is personal as well as an academic and scientific endeavor for me. My question in particular is for both Dr. Systrom and Dr. Keller, and any of the other clinicians that are managing this can feel free to step in. But my question is there any measurement going on simultaneously because of the low blood pressure at baseline and all the other orthostatic problems of cortisol levels or other neuroendocrine hormones, such as, you know, we've noticed reverse T3 has been low in the patients, and I think that may be interesting to look at in terms of supporting blood pressure and those kind of issues.
I think back in the day, which was about 3 years ago, I was doing court stims on every one of the patients that we saw with preload failure and was not coming up with anything. You know, obviously there are time-honored issues of real autoimmune diathesis and perhaps other markers of adrenal insufficiency. Should put that one on, but it wasn't very high yield across the board. With respect to thyroid function, I'm a pulmonologist. I don't get very much further than the TSH. There we do find oftentimes Hashimoto's is, I think, a marker of autoimmunity. I don't know. We've had a couple of cases of hyperthyroidism with a hyperdynamic circulation where symptoms improved. We didn't do the repeat invasive testing, but they had a high output state with hyperthyroidism and a low TSH. But beyond that, I can't take it much further.
I'll just quickly mention that I'm not in an environment where we can do that easily, but for the study that we're working on currently, and the way that we're recruiting patients, that we're testing routinely for TSH as part of the recruitment. But if you read the IOM guidelines, it's not just a matter of following that nice algorithm that's on page 12 or 10 or whatever, but it begins by ruling out any other illnesses or diseases that might explain the symptoms. And then you follow the algorithm. Every step of the way you have to rule out, so it's routinely something that's tested for and ruled out thyroid function before an ME/CFS diagnosis is made.
Okay. I'm just looking at this as a long-standing chronic illness, and euthyroid 6 syndrome being as something part of it, or subclinical hypothyroidism. And I was just wondering if that affected any of the hemodynamics. So thank you.
I can just comment a bit, Jonas Bergqvist, Uppsala, Sweden. We are doing a steroid profiling of quite a few patients now, and our preliminary data show that pregnenolone is really changed in many of the patients, so that's what we are going to follow up on. And on the thyroid hormone regulation, we are setting up a new method. We just set it up basically for 7 different metabolic markers of thyroid hormone regulation, so we're going to use that to address this.
Rivka. Hi, my name is Rivka Solomon, and I'm with the Massachusetts ME/CFS and FM Association. Short comment and then a question. First of all, thank you, everyone, for being here and for speaking and for your research. So in Massachusetts, we just held an event with the MGH Institute of Health Professions, and we had over 650 healthcare professionals and healthcare students in the audience. The whole event was focused on ME, and I would urge the NIH and the CDC to take the lead in doing these events as opposed to the advocacy organizations. We really need your help. So that's my comment. My question is for Dr. Klimas or maybe Dr. Navio. So I've been sick 29 years, and in the last couple of years, what's happened is I've now experienced a semi-paralysis that others have talked about. It just comes on, and all of a sudden I can't move my legs or my arms very much. And I feel like I'm going to die. Like literally, my body feels like it's going to die. And I'm wondering what's happening when I'm in that place. And I'm not alone. That's why we call it a living death. So I was wondering if Dr. Klimas had any thoughts, or Dr. Navio, or if anyone, and obviously if there's anything that can shift that. I've noticed that Ativan can sometimes shift it a little bit. Ativan, which is an anti-anxiety medication, but it's not anxiety that I'm experiencing. It's like a body shutdown.
Yeah, sorry, it's a hard question to answer because you really need to know a lot more about the patient to try to postulate that kind of thing. It could be anything. It could be a mitochondrial thing. It could be, Ativan has a lot of different effects on different neurotransmitters. It's not a very specific drug, but it's interesting that it helps because it does suggest there's a neurotransmitter thing going on. But I would be hard pressed to guess. Does anyone clinically have an idea?
First question, do you know what your pulse is at the time?
I'm on atenolol already, a beta blocker, so my pulse tends to be pretty steady.
Do you break out in a cold sweat?
No.
Do you have any abdominal discomfort?
No.
No butterflies?
Nope.
Then my vagal theory doesn't have much support. So,
a couple of real odd ones out there. Channelopathies, once in a while remotely related to mitochondrial disease. can come and go. There's hyperkalemic and hypokalemic periodic paralysis where extremity weakness can come and go. And then there's one other odd one. Is there any hypertonic component to your weakness at the legs? Are they stiff?
What is hypertonic?
Stiff?
No.
Okay. Well, just another odd one. It's called stiff person syndrome, and it's diagnosis by EMG, nerve conduction, and actually benzodiazepines are given during the nerve conduction that fix it. Just some wild thoughts.
Thanks. Okay. And we'll let this person have the last question, and then I'll give some closing comments.
Hi, I'm Diane Bean, and I'm the mother of a patient who's been sick for 20 years, and she's also pretty severely ill. She has been seeing an immunologist for a while, and one of the things, he's also an allergist and works with pulmonologists. He's out of National Jewish in Denver. One of the things that he has found is that she has an alpha-1 antitrypsin deficiency, but her pulmonary function tests are fairly normal. So I guess this is for Dr. Systrom and Dr. Keller. So she doesn't have COPD. He tried to get the insurance company to approve Prolastin. And I wondered if in your work you have seen that in your patients or tested for it?
So, there are various kinds of alpha-1 antitrypsin or protease deficiency, homozygous variant that pretty uniformly does cause COPD, even in non-smoker, never smoker. But then there are other variants, so I'm not quite certain which one that is. Interestingly, we just saw a patient in Boston with that combination, but I'm not smart enough to link it to any of what we've got here. It's not traditionally thought as autoimmune in nature.
Great. So in closing, we have about a few minutes before we head over to the poster. This has been a long journey to get here. Many of us were on the planning committee, and we've been working on it basically since last year. And while we're excited to be here and hearing about science that will hopefully get us to not just to treatment, but to a cure, my dream is that, much like in my professional life and working in HIV, where we're talking about ending the AIDS epidemic and finding a cure, that is what I want us to be going to, that we're looking for a plan to end ME, and that we're ultimately going to have a cure, and that all of us get to go back to our lives. At the foundation of everything that we're discussing today, we have to recognize stigma. There is very severe ME-related stigma in the world. We are not a monolith. We are not a group of people who are difficult to deal with. We are not individuals who are bullying scientists out of this work. We are fighting for our lives. And we have to demand, and I have to challenge you to please think about the language that you use when you're talking about us. We are people living with ME. Please don't medicalize our lives, because it reproduces and it sustains stigma, and people discriminate against us because of the perceptions that they have about us. I'd encourage you to Google the Denver Principles. The HIV community in 1983 came out with a document in which they asked the world to please condemn labels like victims, a term which implies defeat. And remember that we are only occasionally patients when we're in a medical appointment. Patient historically is a term that implies passivity, helplessness, and dependence upon the care of others. Please refer to us as people with ME, just like the AIDS activists demanded that they be referred to as people first living with AIDS. Please support us in our struggles. Fight against people who would fight against us, try to evict us from our homes, fire us from our jobs, keep us from the disability that we deserve so that we can live, and absolutely do not scapegoat us for this disease. This is an epidemic, It is something that has been going on for decades and decades and decades, even before my diagnosis in March of 2016. So as you're fighting hard in your laboratories and in your medical appointments to try to help save our lives, please help us fight stigma so that we're not discriminated against. Thank you.